Can you check the live stream?
Yep. So it's small currently.
What is so small?
Oh, so now it looks better. It's full screen, I guess. It takes up the entire YouTube window, I mean. I think we're also playing through the live, by the way.
Let me hear. Is this working? Is this working? Is it working?
Yeah, it looks good.
Hey, is the resolution good in the live?
Yeah, I think all good.
Okay. Anyways, we can just stop cameras, mute ourselves, and just be standing in case something happens. You are not muted, just in case.
Hello, this is Anthony Francis of Robotics at Google, and I'd like to welcome you to the Embodied AI workshop at CVPR 2021. Deep learning has enabled amazing advances over the past 10 years through big data, through big compute, through the many researchers who have applied algorithms old and new to translate languages, to understand speech, to determine that this complicated set of pixels is actually a cat. Well, once we start interacting with the world, we need to do more than just tell that there's a dog in the picture. We need to execute a sequence of actions, take the consequences, and decide whether or not the policy that was executed is a good one. Embodied artificial intelligence is the discipline of creating agents that learn to solve tasks which require interaction with real-world environments. These involve embodied navigation. They involve rearrangement of objects. They involve social navigation around people. They involve interactive navigation, where we have to move objects in order to reach our goals. They involve object navigation, where we use visual images to help find things in an environment. And auditory navigation, where the sound of the voice of a friend or of a fire alarm prompts our next action. And they also involve visual language navigation, where a sequence of instructions helps us decide where to go in a complicated environment. The Embodied Artificial Intelligence Workshop Series brings together researchers tackling these and similar problems. They involve seeing the world, listening to the sounds of the world, grounding conversations in the world, reasoning about the consequences of actions, and performing actions to perform tasks. At today's workshop, we'll have invited speakers talking about the motivation behind embodied AI, embodied navigation problems, robotics, and sim-to-real transfer. We'll have workshop papers presented in a poster session, and then we also will be talking about the results of some challenges that we have put on in both navigation and interaction problems. In the beginning of today's schedule, we'll have invited speakers talking, followed by the speaker panel at 11, and a break at noon for lunch. At 1 p.m., we'll have a poster session for the accepted papers. At 2 p.m., the navigation challenge results will be presented, followed by a Q&A panel of the challenge organizers. And at 4 p.m., the interaction challenge results will be presented, followed by a panel with their organizers. Our speakers will include Haiwan Jiwan of Stanford about motivation for embodied AI research, Peter Anderson and Sandra Faust of Google for embodied navigation, Anka Dragan of Berkeley, Chelsea Finn of Google, and Akshay Rai of Facebook AI Research talking about robotics, and Konstantinos Busmalis of Google and Sandra Fiedler of NVIDIA talking about sim-to-real transfer. The speaker panel will be at 11 a.m. PST, followed by a break. At 1 p.m., we will have a poster session for the accepted papers. Following this, the Embodied AI challenges will report their results and discussions. First, we'll start with embodied navigation challenges with the results at 2 p.m. and a panel at 3 p.m. These challenges include point navigation, moving to a metrically specified goal, object navigation, navigating towards a visually specified object, multi-object navigation, going to several objects in sequence, interactive navigation, where it is required to move objects to succeed at your goal, social navigation, where you're penalized for invading other people's personal space, vision and language navigation, following instructions, and audio-visual navigation, reacting to cues in your environment. Several challenge organizers have tackled these problems, including AI2 Thor, Habitat, Gibson, Multion, RXR Habitat, and SoundSpaces. The environmental interaction challenges the results will be presented at 4 p.m. with a panel at 5 p.m. These include vision and language interaction, semantic slam, and rearrangement. ALFRED, robotic vision scene understanding, TDW transport, and AI2 Thor are the challenges that have tackled these tasks. Finally, I'd like to acknowledge all the people that helped put on this workshop, including my fellow organizers, Cheng-Shu Lee of Stanford, Herman Ross of Intel, John Trong of Georgia Tech, Yuka Weiss of AI2, and Eric Leemans of Georgia Tech. We have a scientific advisory board who have been helping us, and a larger group of challenge organizers. For more information, including the full schedule, the accepted papers, links to the challenges, and more, please check out embodiedai.org. Thank you very much.
Okay. Hi, I'm Hyo-Kwon, and I'm very excited to be a part of this workshop today. Perhaps unlike other speakers, I study humans, and especially how infants and young children learn in social contexts. So as many of you today might be looking towards cognitive science for inspirations for building more powerful, flexible, socially intelligent, embodied AI, I hope that some of the work that we're doing and the way we think about how humans learn and help others learn can lead to new ideas and directions for research. So first, let's take a look at how humans learn. So many of you may have seen this video, and most likely you saw this as an example of a curious human learner who actively explores the world and generating new data, learning how the world works. However, what's not captured in this field of view are his caregivers and family members who are probably just nearby, who created the safe environment with a lot of things to explore. And as humans, from the moment we're born, we're surrounded by other people. And we're incredibly curious, not just about the world and about objects, but also about other people and their actions, what they're thinking. We're also taught from people and by people who want to help us learn. And as humans, we also have created all kinds of environments to promote learning from others, from daycares to schools and even conferences and workshops. So these are just many examples, just some of the examples of the ways in which we learn from others and help others learn. So perhaps learning actually looks much more like this. Let's take a look.
See this? What is it? This is a blicket. What's a blicket? See that? All right, I'm going to give you a bunch of blickets to play with while I write something down, okay?
So she just saw a blicket that sticks to the block shown by this adult, and then we're given a bunch of other blocks to play with.
It's still not sticking. How do these stick? Just let me know when you're done playing. Oh, they're not sticking. That's weird. I think there's no stickiness anymore. Come on. These are not working. Maybe I can build something. Just let me know when you're done playing, okay? You can. Ethan wants to help me build a tower.
So what did you see? She observes others' actions and she imitates what others do, but she's not just blindly copying. She was imitating the adult's action because she generalized what she saw and expected other blocks to stick too. And when the first one didn't, she went ahead and explored all these other blocks too, trying to explain what's happening and communicating her thoughts to the adult as well. And at some point, she even generates a new goal of building a block tower with the help of her brother. So all of this is happening in parallel in less than a minute. So think about what this means for a child to be doing this for a lifetime. So the guiding question for our research program in the lab is what makes human learning so powerful, distinctive, and smart? And of course, this is a question with many potential answers, but the one that I want to focus on today is the fact that we learn from others and help others learn. And in the context of this workshop today, I also want to ask how we can use insights from human learning in order to build better embodied AI. However, unfortunately, the way we typically think about social learning tends to be rather limited. We tend to think that social learning means to copy or imitate expert demonstrations or follow others' advice, which sounds very different from individual learning. So we tend to think that individual learning and social learning are two different things, rely on different mechanisms. We also think social learning is different from teaching. Teaching is what teachers do, and learning is what learners do. They rely on separate kinds of processes. So what this means for this particular community is that despite a lot of progress in implementing social learning, we still have machines that are trying to learn from others without understanding why. Why did the person do what they did, and why is it useful to learn from others? And therefore, these machines can't decide when to learn from others, what to learn from others, or whom to learn from. So what I would like to argue is that this way of thinking about social learning vastly underestimates its power. And what I'd like to do today is to try to paint a different picture of how we learn from others and help others learn, and present examples of studies that support and extend this picture, and try to lay out challenges for building intelligent machines that learn from, interact with, and help humans. So in the past couple of decades, there's been exciting progress in formalizing human learning as probabilistic inference from observed evidence over abstract structured representations. And the idea is that humans have rich priors and draw powerful inferences from even small amounts of data that comes from learners' observations and exploration. And consistent with this, developmental psychology has also found evidence that infants, like this one over here, engages in exploratory play, test hypotheses, and learn from self-generated evidence. And so, for instance, this learner might come across a toy, play with it, and discover how the toy works. But as I emphasized earlier, children are rarely alone, and often they observe other people interacting with the world. So the idea behind inferential social learning is that humans learn by drawing inferences, not just from evidence they observe on their own, but also from evidence generated by other people. So does this mean that individual learning and social learning are basically the same things? Well, yes, because it draws on the same inferential machinery, but also there's important differences, because when people generate evidence, they do so for a number of different reasons in a number of different ways. So actions can be incidental or accidental without any clear goal, or instrumental with a self-serving goal. So the person might simply want to play with the toy. However, in some cases, and often in what children observe, is instructional or pedagogical actions with a clear communicative goal. For instance, actions done with the intent to teach the learner how this toy works. So by considering how the information was generated, by whom and how and why, learners can draw different inferences even from seemingly the same data. And such learning can be especially powerful when the evidence comes from teachers who are trying to select the best set of evidence to help the learner learn. So in my picture of social learning, learners are not just imitating or passively trusting what was given. They're trying to interpret the data by considering how the data were generated. And communicators, they might act with different reasons and different ways. Often, what they do is to act as helpful teachers who are selecting the data by considering how the data would affect the learner. That is, how they might help the learner achieve their goals, revise their beliefs, or increase the learner's utilities. So what does this mean? Both learners and teachers are trying to achieve their goals of learning and teaching through a generative model of how the other party thinks and plans and acts. So how does this lead to more powerful, effective learning? We can think of at least 3 different ways. First, learners can draw flexible inferences based on how the evidence was generated. Second, learners can evaluate teachers based on whether they generated helpful evidence, whether other people generated helpful evidence. And third, learners can become teachers. If they understand what it means to generate helpful evidence, they ought to be able to do the same for others to help others learn. So let's first take a look at the first hypothesis. So imagine a box that looks like this, with many blue toys, just a few yellow toys. I might reach inside the box, draw this blue toy, squeeze the toy, which makes a funny squeak sound. I do it again, I do it again. And the question for the learner is whether the yellow toy squeaks too. So I didn't do anything with the yellow toy, so what would you learn from these 3 blue toys? Well, in this case, there's nothing special about the fact that I took 3 blue toys out of the box. The sample is quite probable given the composition of the population, which might suggest random sampling. Perhaps I might selectively sample them, but it's not clear. So if you were a baby, well, the yellow toy comes from the same box. They kind of look the same. So there's no reason to not try squeezing a few times to see if it squeaks. However, if the same sample came from this kind of box, the sample is very improbable, which suggests strong or biased sampling. And why would I sample just these 3 blue toys out of a box that's mostly yellow? Presumably because only the blue toys squeak and the yellow toys don't. So if the baby understands this, they might not try the squeezing the yellow toy as many times. They might just try to do other kinds of things. So what we have shown across a number of conditions is that infants draw different inferences depending on the probability of the sample given the population, and they try to squeeze the toy on average different numbers of times depending on whether they expected the yellow toy to squeak. And what this shows is evidence for a graded inference about the property of the yellow toy depending on the probability of the sample. And these responses are well predicted by a simple Bayesian model that infers the property of the yellow toy based on the sample and priors over different sampling hypotheses. So what this means is that even babies can draw different inferences from seemingly the same kinds of data from just seeing a few blue toys. And in older children, how they manifest is through different ways of exploring even the same toy, given the same kind of demonstrations. For instance, if a teacher demonstrates one function of a toy by pulling this tube out from this toy, the toy makes a squeak sound. But if it's a teacher who knows all about the toy demonstrating how the toy works, what the children infer is that this is the only way that the toy works. And when they're given a chance to play with the toy, they mostly play with this part of the toy. Compared to children who saw pretty much the same evidence, but by somebody who's never seen the toy before, and she accidentally discovers how this toy works. And in this case, what children do is they not only play with this demonstrated part, but also they explore the toy broadly because they have no reason to think that the toy doesn't do anything else. And in what children did in the left pedagogical condition is that when teacher shows just one function, they understood that it likely means there's no other functions, because if the teacher knew that there were other functions, she would have shown them as well. Now, let's think about the teacher who showed how the toy works and taught you just one function. And imagine you were the child who actually found out the toy can actually do many different things. How would you feel? So in principle, the teacher didn't do anything wrong. She showed something true and interesting about the toy, but she clearly wasn't providing you the best set of evidence that she could have because she omitted a bunch of other things. So the second hypothesis is that in these cases, learners should be able to evaluate teachers based on whether they generated the most helpful evidence or whether they provided under-informative pedagogy. So what we have shown across a number of studies is that children understand when a teacher was under-informative and rate a teacher as less helpful when the teacher shows only one thing out of a toy that does multiple things, compared to a teacher who showed the same thing but on a toy that doesn't do anything else. And they understand that if the teacher omits something, not because she knew and didn't show, but because she didn't know and therefore couldn't show, they tend to exonerate such kind of omission. And they also can evaluate teachers who are overly informative by repeating redundant information or providing more than what the learner needs. Now, the third hypothesis is that children ought to be able to provide information that is maximally helpful for the learner too. So in this study, what we were trying to show is that whether children can prioritize teaching what maximizes the learner's utility. Can they choose what to teach based on how their teaching affects the learner's utility? So an example is, imagine you are stranded on an island, and after days and weeks of trying really hard, you finally learned how to make fire. But then if you encounter somebody else who also doesn't know how to make fire, but also stranded on the same island, you really would want to show this person how to make fire because you understand that this person would struggle without your teaching. So what we have shown with Sophie Bridgers, a former student of mine, and Julia Hara-Ettinger at Yale, is to try to show this experimentally by showing them a pair of toys and asking them which one should be taught. So imagine this toy that has one button. It's really easy to figure out or discover how it works. And if you press this button, the toy plays music. This is what we call the low reward, low cost toy because it's low cost to discover. And the reward is interesting, but not as rewarding as this high reward, high cost toy. So this toy is incredibly difficult to discover without being taught because the way it works is that you have to press this button and this button at exactly the same time. But when you do, it does generate a pretty rewarding function that children really like. So children played with both toys. They learned how they work. They were able to demonstrate back to us. And then the experimenter asked them a key question. So the experimenter says, I have a friend who's going to play with these toys all by herself later. Which toy should I teach my friend? So this is a decision for them to teach one toy and let the learner explore the other one. So what teaching does is to ensure that the learner can activate the top toy and reap the reward without having to pay the discovery costs. So you can think of this choice of what to teach as choosing one of two teaching plans that has a higher utility for the learner. So if you consider the top toy here, if you teach this one, then the learner would learn this toy, but would really struggle with the bottom toy because it's really hard to discover without being taught. So in this case, it's beneficial to teach their own, and the learner will have to explore the top toy, but this one's pretty easy to discover on their own, so they would also reap that reward as well. And doing it the other way around, teaching the top toy would not be a wise choice. And what we have done is to ask the same question with not just with this pair of toys, but with a number of different pairs of toys. For instance, matching the reward and varying the costs, and matching the cost and varying the rewards, but also using this toy to be compared against other toys that differ in their relative costs. So what the model predicts by considering all of these variables shown here is a choice that looks like this. And what we have shown in different groups of children is that their choices look very close to what the models predict. And we have shown that other models that don't include all of these variables don't provide as good of a fit to human behavior. So what this suggests is that children are already thinking about what would be rewarding and what would be costly for other people to learn and learn from exploration and learn from their teaching. They're not just choosing what's rewarding, and they're not just choosing what is hard or cool or difficult. And they're thinking about the expected utility for other learners to decide what to teach. And even when it's clear to teach, there's decisions about how much evidence is necessary for the learner. So for instance, if there's a toy that has 20 buttons and only 3 buttons work and the rest of the 17 buttons don't do anything, if you are this child who has to teach a learner about how this toy works, would you press just 3 of the buttons or all 20? Well, the decision depends on what the learner knows. So if the learner already expects a few buttons to work because the learner's already seen similar toys before, you can do away with just showing 3 buttons that work and it would be fine. But if the learner has never seen toys like this before, showing just 3 would be misleading because the learner might think that, well, everything might work the same way. So it's incredibly important to show every single button, even the inert buttons, even though they might be costly to demonstrate all 20. And that's exactly what 5-year-old children do. They press different numbers of buttons to teach the same toy, depending on what the learner understands and knows and expects. So what we have shown overall is that children consider what the learner wants and knows and provide the right kind of information and the right amount of information for the learner. So what I have shown you so far is that learning from others means much more than imitation or passive trust. Learners are interpreting the meaning of evidence based on who did what and why. In teaching is much more than providing what's accurate or novel or rewarding or cool. As teachers, children are already considering what the learners know and want and maximize their utilities. And what this means is this is possible because humans can engage in these interactions as learners and as teachers through a model of how people think, plan, and act. And what this suggests is a role of theory of mind in a broad sense, that is reasoning about others' goals, desires, and beliefs, as well as their expected utilities. So now it might be natural to think, well, implementing these kinds of thinking about others through a model of others is really hard and intractable. And why would machines really need to think about others' minds anyways? But what I would like to try to do in the rest of my talk is to try to provide specific examples where this kind of learning can really augment the scope of what children can learn and what they do. First, this kind of learning allows you to use emotion, even emotion, as information. So what does this mean? We're familiar with the role of prediction error in learning, and of course, even infants tend to explore more when they see surprising events. But learning from prediction error requires the learners to know enough to generate a prediction in the first place. But what if learners can capitalize on other people's surprise, for instance? When somebody has access to parts of the world that's hidden and looks surprised, we might immediately wonder, hey, what's over there? And infer that there's something unexpected happening. But in order to do so, the learners must have a causal model of what makes people surprised. So in this study, what we were asking is whether infants can infer hidden states of the world by using others' surprise as vicarious prediction error. This is work with Young Woo, a postdoc who's actually starting next year at U of Toronto, Scarborough. And so take a look at this person who has a box full of mostly red balls and just a few white balls. She randomly draws one and puts it inside a small black box. So what do you think is inside the little box? You would think that presumably the red one rather than the white one, and you would understand that the white one would be quite unexpected. And this is exactly what infants understand as well. They look longer at this unexpected outcome of white ball compared to the red ball. And what we have done is to replicate this finding first, and then we did a series of other experiments with a small tweak. So let's take a look.
I got one. And I put it in here. Okay, I'm going to take a look first. Look what I got.
So now what do you think is inside the box? So by using this person's surprise as information, what you can do is to revise your expectation about what is inside the black box. Now, the unexpected outcome becomes the expected outcome, and expected outcome becomes the unexpected outcome. So what we were trying to do is to see whether we can reverse the pattern of infants' looking time by using emotion, by providing this surprise expression. what we have shown is that's exactly the case. So infants look longer at the expected outcome because they think it's unexpected given the surprise compared to the white ball. However, they revert to the original pattern when the person isn't surprised and she just looks smiling at the outcome here. So in this case, they look longer at the originally unexpected outcome. And what we have done is to try to replicate this finding across a number of experiments. So theories of social learning often focus on learning from actions or learning from language. And also in machine learning and robotics, there's been progress in imitation learning, often from expert demonstrations or learning from human speech. But once you think about social learning as inference from others' behaviors, pretty much any aspect of behavior can be information when you understand how these behaviors are generated. So what if we had machines that can learn from all kinds of social signals, including emotions? This kind of ability would be particularly useful for embodied agents that must assist humans in complex environments, especially if they can take expressions, not just indicators of feelings, but also as information about the world and their internal mental states. So there's a lot of progress in formalizing such reasoning as inference problem, working backwards from emotion expressions or speech or actions to infer the actor's mental states or hidden states of the world. And I look forward to more efforts that bridge AI with progress in cognitive science in this direction. Second, reputation matters. And you might think, well, AI doesn't need reputation. What do we need it for? But perhaps you'll change your mind after seeing this example here. So in this study, children were presented with two toys, and there was this experimenter who says, we're going to play with these toys, and Sarah, a naive observer, she's going to watch us play. So Sarah's sitting here in this room as children are playing with the experimenter with these toys. So let's take a look.
Yo, isn't that cool? Those lights are really cool. You try.
1, 2, 3, go.
Let me see what this one. Are you ready? 1, 2, 3, go.
So the child is failing while Sarah's watching.
For this toy, you have to push this and this at the exact same time. Okay, I have to go now. I'll see you later.
And now Sarah leaves the room.
This one, you try.
1, 2, 3, go.
And then the child finally succeeds. And then afterwards, the child played with the green toy, again failing twice and succeeding the third time, but Sarah was outside of the room the whole time. So what Sarah observed is the child failing twice and without seeing the child's final success on the red toy. Now, the child has a chance to show Sarah one of the two toys, and by showing her the green toy, the child can show Sarah something new that she's never learned because Sarah doesn't know how this green toy works. However, if a child understands and is capable of reasoning that, hey, Sarah thinks I can't make the red toy go, then they might want to show the red toy because in order to show that he can actually do it, even though Sarah has already seen the toy multiple times. So what do children do? Let's take a look.
Show our friend Sarah one of these toys. Which one would you like to show her? This one or this one?
This one.
The red one? Why do you want to show her the red one, Lucas?
Because I can do it.
Because you can do it?
So in a nutshell, what we have shown across a series of experiments is that children, of course, they prefer to teach someone about a new toy over something that they have seen already, especially when Sarah left the room after seeing the child's success. But just like in the video you saw, when Sarah leaves the room before the child succeeds, they're more likely to choose the red toy that Sarah saw them fail, just like what this child just did, so that they can communicate to Sarah that they can actually make the toy go. And this tendency is even stronger when Sarah already knows how the toys work, so that there's no competing motivation to show the green toy. So There's been a lot of progress in developing agents that are motivated to learn, that is, maximize information gain or minimize error. And many AI algorithms can perform better than humans in tasks with clear end states and reward structures. However, human behavior is also driven by a range of social motivations like competing or cooperating and even impressing other people. And so what if we had machines that can learn about the self, like how did I do, or care to change what other people think of them by showing, hey, I can do it. So even though reputation management may sound like a very human thing, they're powerful drivers of learning and self-evaluation and self-improvement. And this process, what we have done is to reconstruct this process as mental state inference and communication of information that corrects others' beliefs about the self. And there's models that have formalized a theory of mind in many ways, in ways that can make this kind of problem more tractable for implementing in machines. And perhaps machines can benefit by virtue of such motivations, especially embodied AI that directly interact with humans. Finally, for machines, failures are failures or errors, but for humans, failures mean much more than errors. So although I won't show you the details of exactly what we did in this study for the sake of time, what I have shown in my earlier study is that infants can infer the cause of their failures, and depending on whether they think it's the object that's failing them, they can't activate this toy because the toy might be broken, they try a different toy and explore. But when they think it's me, I did something wrong, and that's why I can't activate this toy, they readily seek help from other people, for instance, their parent. Similarly, when other people fail, they don't simply do what they did or try to do something. They do something that's meaningful by reasoning about why other people fail and thinking about what they can do in order to help. So when this person's failure suggests that she's working on a broken toy, then they give the experimenter the working toy by going across the room. However, when it suggests that she's working on the wrong side of the toy because she doesn't know how the toy works, they flip the toy over to show the correct button. So let's take a look at this child. There's two identical looking toys. One's working, the other's broken, and the parent has no clue. And the 20-month-old must use his prior knowledge in order to figure out what to do.
I'm going to try this toy. Can you help me play music?
Until the father fails, there's no way to tell which one's broken or working. But this child immediately figures it out and says, no music, and goes over to the other one to show the toy that works. So some of you may have seen this video of a toddler with a man whose hands are full of books. This child understands that when there's something blocking others' goals, you should remove the obstacle by opening up that cabinet door. But when there's somebody's ignorance is leading them awry, it can be much harder to figure out how to help because you have to pull your existing knowledge to problem solve on others' behalf. But what you just saw is that children can even do these kinds of helping behaviors when others' ignorance is making them fail. And even when they themselves fail, they just don't fuss out or give up. And especially when the failure indicates they're doing something wrong, they readily ask for others' help. So one of the most remarkable aspects of human intelligence is that we use our own failures and our own intelligence in order to diagnose what went wrong, and we try to figure out what to do, not just for ourselves, but also for others. So there's been a lot of progress in trying to make machines that are able to navigate the world and manipulate objects and make sense of sensory input. But what's still missing in embodied AI, I would say the ability to interact with other people. And this is especially important for building agents that can perform real-world tasks in real-world environments with real people. And as I said, humans have a model of others' minds. They see actions as more than targets of imitation or reward predictive cues, and they learn through inferences about contents of other minds. So can we build machines with minds that are equipped with a model of others' minds so that they can make sense of the social input, even from emotion expressions, reason about what others think, even about the self, knowing what to do next, even after failures for both self and others? And of course, the remaining question is what makes them motivated to do so? And as we have expressed in this short opinion paper with Natalia Velez, who's starting at Princeton in 2023, social learning through the lens of reinforcement learning has been rather limited. And beyond the scope of social learning, reinforcement learning generally provides a powerful framework for designing agents that are motivated to do things, but specifying the objective function is a non-trivial challenge. And humans, even though humans may have a general intrinsic motivation to learn and connect with others, there's a range of context-specific motivations that are often competing against one another. And humans are incredibly good at figuring out what they should do now or later over a long time horizon and balance different kinds of competing goals. So learning, at least in humans, doesn't look like this or even this. It looks more like this, and it occurs naturally in social context. And even in these contexts, it's important to remember that social learning is not about the behavior itself. It's about how others' behaviors can change the world so that the learner can do the same thing. And this requires an understanding of how other people think, plan, and act. And this provides the bedrock for powerful, flexible learning, communication, and cooperation. And these are precisely the kinds of things we want in the next generation of embodied AI that can truly understand and connect with and help other humans. So thanks for listening, and I look forward to the panel discussions and other talks in this workshop today. Thanks.
Hi folks, my name is Peter Anderson. I'm a research scientist at Google, and this talk is about massive data sets for language-guided navigation agents and where to find them. Recently, we've seen a redefinition of what's possible for state-of-the-art vision and language models. And I'm talking in particular about models such as DALL-E and CLIP from OpenAI and the Align model from Google. And what's particularly amazing about these models is that they're proficient at multiple tasks. They have zero-shot capabilities. So, for example, a model such as CLIP can achieve very good results for classifying images from ImageNet without using any of the ImageNet training data. And these models are also surprisingly compositional in the way they are able to combine fine-grained concepts. So if we look, for example, at an image retrieval task using text and image embeddings from the Align model, we can see that the model clearly distinguishes between very fine-grained concepts such as a Van Gogh Starry Night details versus a Van Gogh Starry Night in black and white or on a canvas or in a dark wood frame, which is very impressive. If we look further at compositionality, here we're doing an image retrieval task using a combination of an image embedding with a text embedding added or subtracted. If we look at the example in the second row, the image embedding of a butterfly on a purple flower, if we subtract the text embedding for flower, we can retrieve an image of just a butterfly. Or we can change the color of the retrieved image by subtracting the text embedding for orange. And we can even add the text embedding for rose and retrieve an image of a butterfly sitting on a rose. So this is really quite remarkable. And the reason for these advances is not so much new modeling techniques as simply using much, much larger models and much, much more training data. How much training data? So for the Align model, it's trained on noisy web images, image and text data. So you can see from these examples here, the text data is actually, really quite noisy, but the training data consists of 1.8 billion image text pairs for the English-only version of this model. And so the power of these models really comes from the huge amounts of data that are used to train them. And so you might well ask, why am I talking about this in an embodied AI workshop? And the reason is, well, first of all, my particular interest is in language-guided embodied agents. And so one problem that we work on quite a bit is language-guided navigation agents, or vision and language navigation, which is this sort of task that you see demonstrated here. We want to provide a natural language instruction, such as exit the bathroom, turn left, and exit the room using the door on the left, wait there. And what we want is to be able to train an agent that can follow these grounded natural language navigation instructions in a photorealistic and previously unseen environment. And the observation that I want to make is that the training data for tasks such as this is really very limited. And if we just had billions of instruction trajectory training examples, I think it's very, very likely this task would be much easier. And although this observation is quite flippant, on the other hand, it's actually quite serious, because many of the limitations of the current models, such as overfitting to the training environments and poor generalization to unseen environments, a lot of these problems would likely just evaporate with more training data. And so the question is, well, should we not, consider, is there a way that we can stop mucking around with data sets with thousands and tens of thousands of examples and, look for hundreds of thousands or even millions of training examples, and how would we possibly do this? And this is the research program I'd like to talk about today, guided by this question. How can we use the available resources we have to generate massive data sets for training language-guided navigation agents? So my argument is that there's 4 parts to this research program. First of all, we need to generate more environments. And one possible way of achieving this is by converting static images and videos of places, which are available at huge scale, into interactive training environments that would allow an agent to somehow move within the image or the video in order to learn navigation. Secondly, if we create these hundreds of thousands of new environments, we would need to annotate them with training tasks, which means generating high quality navigation instructions from a model. Thirdly, using model generated instructions, we naturally need to figure out a way to evaluate those instructions for quality, to ensure the quality of the training data. And finally, even though we want to generate these environments and generate these instructions, we obviously still need to collect quite a lot of high quality human annotated navigation instructions to sort of bootstrap this system, to train the instruction generator and to evaluate the navigation agents that we train. And so this is a research program to look at ways that we can scale the training data for language-guided navigation agents far, far in advance of what's available currently. And today I'm going to talk in particular about these 3 aspects of the problem, beginning with the problem of generating environments. So first of all, what's the kind of current situation? So typically for training embodied language agents, there are different simulators and different data sets, but they're typically based on underlying environments from data sets such as Matterport 3D. And there are some others such as Gibson as well, but generally they have they're at a similar scale. And Matterport 3D contains 90 environments, each reconstructed with a Matterport camera. And as a consequence, I guess, of the relatively small number of environments, what we see when training vision and language navigation agents is that there's a lot of overfitting, that performance of these agents might be quite good in the training environments, but it drops significantly in unseen environments. And so the concept I would like to investigate right now is whether we could take images and videos of places that are readily available at massive scale. Even looking at internet videos, there are hundreds of thousands of real estate walkthrough videos on the internet. And my question is, can we take these static images and fixed videos and somehow make them interactive and convert them into interactive training environments where an agent could learn to navigate? And so what does this look like in practice? Let's walk through it using this example on the right-hand side. Suppose I had, as an example, just a single image as an input, which is image 1 at the top left. And now I'm training an agent that wants to move in such a way as to follow the yellow arrow, which is moving to position 2, shown in the floor plan view at the top right, which is only indicative and not used by the model. What we'd like to do is generate the image in the second row, the prediction of what the view would look like from that new position. And so on, if the agent moves again, following the yellow arrow to position 3, what we would like to do is generate a prediction of what it would look like from that position. And then what we've effectively done is made this image interactive. And so we have actually proposed a model that can do this. The predictions in position 2 and 3 are the outputs of that model. And you can see how they compare to the actual ground truth on the right-hand side. One fairly interesting aspect here is that in the ground truth, in this real environment, the ceiling of this kitchen is actually painted with a fresco of clouds. Now, a model has never seen that. This is an unseen environment, and so the model does not predict that. But nevertheless, it comes up with a fairly plausible prediction of what it would look like to follow those arrows and to move and see inside the kitchen area. So that's the proposal that we're making, to take static images and potentially videos and convert them into interactive environments. And so what we're really proposing is actually a world model for indoor navigation. So typically world models or model-based RL has previously been explored in the context of game environments such as Doom and Atari games. Here, as I'll show with a video, here we're taking this same concept and applying it to indoor environments. So here's a video showing some of the outputs of our model, which we call PathDreamer. Each of these outputs is generated from observations at a single point, and then by allowing or providing some trajectory to the PathDreamer model, and the PathDreamer model then generates observations along that trajectory. So here's a new example. This is the starting image, and these are the predictions from the model as we move in different directions around this building, including around the corner. So we tackle this sort of room reveal problem of what things might look like if we go around the corner. And certainly you can see the model does a fairly nice job of generating consistent and plausible outputs of what this might look like from different parts of this building. One thing you can see, and we're sort of deliberately showing, how far you push this model before it starts to break down. And in general, it takes around 4 or 5 meters before the model starts to break down in its predictions. So one comment I want to make as well is that we've motivated this world model, this PathDreamer model, using the idea of data augmentation, turning static images into interactive environments and using them for training. But world models can be used for many other purposes as well, not least of all is sampling-based planning. So, for example, an agent equipped with a world model can reason about the consequences of its future actions before it takes them, and use this to come up with better plans. So let's dive in and have a little look at the details of this model. It's based on 2 stages. The first stage is a structure generator that deals with the segmentation and depth components. And so the model actually takes in segmentation images and depth images as an input. Now, these could be predictions from another model, but in this case, in what I'll show you today, we're using ground truth, depth, and segmentation inputs. And we then represent these depth and segmentation images as a 3D point cloud, which is reprojected into a guidance image based on the motion of the trajectory. From there, an encoder-decoder stack is used to infill the guidance images, and we also condition on random noise vectors in order to try to capture some of the variability in areas of the image that are completely unseen, for example, when the model looks around corners. The second stage of the model is the image generator. Again, we use a point cloud representation reprojected to a guidance image and a stack of multi-spade blocks in order to generate the hopefully photorealistic RGB predictions of the model. So let's have a look at another example of how this works. If we're given these three images from a single observation point as input, so we have the depth image, the segmentation image, and the RGB image. And by the way, all of this data is 360-degree images in equirectangular format. We can then do a rollout of predictions along some planned trajectory, 1 step, 2 steps, 3 steps, and so on. And you can compare the RGB predictions of the model in row 3 to the ground truth of the actual environment, which is previously unseen in the bottom row. And in general, the predictions from the path streamer model are quite plausible. One area where I can highlight a mistake is in terms of the ceiling rafters, where the model does not actually realize that a rafter must go all the way across the ceiling in order to actually carry any load. So that was an example of a rollout. I want to show some examples as well of the kind of plausible alternatives that the model can produce by sampling different noise vectors. So on the left-hand side here, we see the guidance images that are the reprojected point clouds used as input to the model. What's important here is the black regions. These are areas where the PathStreamer world model has not seen any part of this environment. It has no information about what could be there. And so these are the areas where sampling different noise vectors will produce different results. And so you can see the PathStreamer predictions on the far right-hand side. For a particular noise vector, it's predicting a window, a chair, and a table. If we sample a different noise vector, it can predict a bed with a cushion and a chair, or a different type of table without a window. So you can see there on the right-hand side, these kind of different plausible outcomes that can be produced. Finally, I want to just briefly introduce a small experiment we've done for using the PathStreamer world model as part of a sampling-based planning approach in the context of vision and language navigation. So what we do here is we roll out using the VLN agent to kind of plan ahead out between 1, 2, or 3 steps into the future by either interacting with the PathStreamer model or the ground truth, which is the actual environment, effectively looking ahead, or a baseline, which represents using the information from the navigation graph, but without any visual properties. And so what we can see in these results here is that the green baseline improves performance with forward planning over 2 or 3 steps, because it can use some information about the structure of the navigation graph, about the structure of the navigation possibilities that are there. The PathStreamer model does significantly better, though, by providing plausible visual observations that might be seen in the future. And the PathStreamer model closes about half the gap to the ground truth in this example. Right, so I've talked about how we might use the PathStreamer model to generate environments from images and videos. I won't be talking about generating instructions today, but I do want to discuss our work on evaluating instructions. So to put this in context, when we talk about an instruction following agent, we're talking about a mapping, a model that maps from instructions through to some trajectory in a photorealistic environment. An instruction generator performs the inverse operation. It takes some trajectory represented with visual and possibly geometric representations and converts that to a grounded instruction that hopefully a person could follow. Now, while evaluating an instruction following agent is at least conceptually quite straightforward, we just compare the agent's path to the reference path. Evaluating an instruction generator is more difficult. In theory, we can compare the generated instruction to some reference instruction, but what's not clear at all is what metric we should use for that. And so in this work, this is the question we investigate, is how to evaluate model-generated navigation instructions. So our first step is to assemble a large pool of navigation instructions of varying quality and styles. So we begin with human instructions, and we also perturb those human instructions in various ways by swapping directions, such as left and right, by swapping entities, such as in this example, replacing kitchen area with door and door with kitchen area. And we also swap phrases by reordering them in the instructions. This creates a variation in the quality of the navigation instructions. To this group, we add navigation instructions generated from two existing models, the speaker follower model and the environmental dropout model. And finally, for even more variation, we add template-based instructions, which we call crafty, to this pool. And here you can see an example of a crafty instruction. These are based on the ground truth object annotations in the Matterport dataset. And so these should be factually correct, but they're quite long, which can make them difficult for people to follow. So the next step, given this large pool of different navigation instructions, each describing the same paths in the Matterport environments and based on the paths from the room-to-room data set, we now perform human evaluations. To do so, we use Pangea, which is a panoramic graph environment annotation toolkit that we recently open sourced, and we collect 3 human evals per instruction. So for example, here you can see the interface that the human wayfinders are using as they attempt to follow these instructions. They're able to kind of look and move around in these environments, attempting to follow the instruction at the bottom of the screen, which in this case is leave the room and turn left. With the wooden door behind you, keep walking straight, stop after you go down a few stairs. You can just see the few stairs in view now. So using this, we will basically evaluate the quality of the instruction based on how well our human wayfinders were able to follow it. And we measure that using navigation error, the difference between the goal reached by the navigator and the actual goal location, and also success rate, what percentage of times that navigation error is less than 3 meters, and so on. And so here are the results. And what's interesting is, first of all, to look at the performance of the existing instruction generators from previous work, the speaker follower model and the environmental dropout model. And it's interesting because the quality of the instructions that these models are generating is actually only slightly better than Crafty, the template-based approach, although it must be said that Crafty has the benefit of using the ground truth object annotations. The existing instruction generators are much worse than even the adversarially perturbed human instructions, and far worse than the gold standard human instructions. And the reason this is quite interesting is that these existing instruction generators have already been used very, very successfully for data augmentation, typically improving the performance of instruction following agents by around 5%. And so that's somewhat surprising, given that it turns out that compared to human, the quality of these instructions is quite poor. And so that does suggest there's substantial headroom here to improve not only the instruction generators, but also the quality of the VLN instruction following agents when these generators are used for data augmentation. Now, the primary question of interest here is what evaluation metric we should use for generative instructions, for navigation instructions. And so now that we've established a large pool of navigation instructions of varying quality, and we have human evaluations, our aim is to identify which evaluation metric out of the automated metrics will closely correlate to human performance. And so these are the automated metrics that we look at. We consider textual comparison metrics such as Blue, Cider, Meteor, Rouge, and Spice. All of these metrics require some reference instructions for comparison. We also consider a model-based approach based on BERT score. Thirdly, we consider using vision and language navigation agents as instruction followers and consider evaluations that are based on the instruction following success of these computational agents. The advantage of this approach is that no reference instructions are needed, only the reference path. And finally, we consider a compatibility model, which we propose in this work. And the compatibility model is effectively a dual encoder. It encodes in the one stack a visual and geometric representation of the trajectory, and in the other stack the textual instruction. And it's trained with contrastive loss and large batch sizes to learn to associate which trajectories and which instructions are matched. And so this can then give us a score, which we consider as an alternative evaluation metric. So let's look at which of these metrics correlate with human wayfinding performance. And there's two ways of looking at this. Firstly, we consider a system level evaluation. So this is for when we're wanting to evaluate an instruction generating model. And so we aggregate the scores for each model. And as it turns out, the only one of these scores that has the desired correlation with human evaluations is the SPICE metric, which is negatively correlated with navigation error and positively correlated with success rate and other quality measures such as SPL. And quality here refers to the quality of the instructions as assessed by the annotators on a 5-point scale. So this is a surprising finding because it turns out that Blue score, which is typically considered for many text generation tasks, turns out to have no value here whatsoever. And so for evaluating instruction generation models, i.e. system level evaluation, the SPICE metric should be used. Now, the other question is, what about at the instruction level? What if we want to evaluate the quality of an individual instruction as opposed to a model? And in this case, we don't have the ability to aggregate our scores over many, many different instructions. And so the variance of the evaluation metric is much more important. And so it turns out that in this case, the best approach is to use a compatibility model, like the dual encoder that we proposed earlier. And almost as good as this would be to actually use a language-guided follower agent. And it turns out that actually at the individual instruction level, SPICE is not effective, and neither are any of the other textual evaluation metrics. And there's also an additional advantage of using computational models and navigation agents for scoring these instructions, and that's the advantage that they don't require reference captions. So overall, I think there's a bit of a warning here for the creation of new tasks. Very often we see new multimodal language generation tasks are being proposed, and automatically Blue score is considered as the evaluation metric. And the results here, which show that in this particular case, Blue score has no value whatsoever, suggest that we probably should be deeply suspicious of any new tasks that are evaluated with Blue score unless a human evaluation has been done that shows that Blue score actually correlates with the scores from human evaluation. So having talked about our work on evaluating grounded navigation instructions with some firm conclusions, I now want to talk about the final aspect of this program, which is dataset collection. So recently we collected a new dataset, which we call Room Across Room, or RXR. And this is effectively what the data collection interface looks like. On the left-hand side is the view that the annotator has. They're able to move around and control where they move as they're following a navigation path that's marked with arrows and spheres in the environment, which you'll see. As the annotator moves around, they record with their voice a description of the path that should be taken. I'll show you at the bottom the transcribed text as that description is described. And on the right-hand side, you can see out of the full 360-degree view which parts of the environment the annotator actually looks at, which we also capture. So let me play this annotation example now.
Now you're standing in front of a closed door. Turn to your left. You can see 2 wooden steps. Climb the steps and walk forward by crossing a wall paint which is to your right side. You can see an open door to your left side. Enter into it. This is a gym room. Move forward and walk till the end of the room. You can see a grey colored ball to the corner of the room. Stand there. That's your endpoint.
So that's the interface that we use to collect a large-scale data set. And so you might wonder, well, why do we need a new data set for vision and language navigation? So there's a couple of reasons, a couple of things that motivated this work. Firstly, the majority of work in this language-guided navigation or vision and language navigation space is English-centric. So we wanted to create a data set that was multilingual. In this case, it includes English, Hindi, and Telugu. Secondly, hopefully this has been well motivated by now, but we wanted to increase the scale. And so the RXR data set is around 10 times the size of similar data sets. It includes over 100,000 instructions and something in the order of 10 million words. It also contains fewer path biases in terms of the way the paths are constructed, and the viewpoint coverage is more uniform compared to previous data sets such as room to room. Fourthly, we include a follower demonstration of every single path, which is a nice way of ensuring the quality of the data, but it also provides additional signal in terms of a human blow-by-blow description of exactly how a person follows that path. And finally, hopefully this was clear from showing you the annotation interface, but we capture this spatio-temporal grounding. So by recording voice and transcribing it to text, rather than using text input, which was used by the previous data sets, we're able to align every word in the instruction with what the annotator was looking at as they recorded that instruction. In order for that to work, there's a neat idea that we borrowed from previous work on the localized narratives data set. And so basically, in order to get the alignment between each word in the instruction and the pose trace, which captures what the annotators were looking at, we first perform an automatic transcription of the voice recording, and then we compare that with the manual transcription created by the annotator. And by aligning the two, we're able to propagate the timestamps from the automatic transcription into the manual transcription. So ultimately, the output of this setup is a manual transcription that's timestamped to match the pose trace, indicating what the annotators were looking at. And by the way, our complete annotation toolkit called Pangea has been open sourced, which performs all of this work. So to put that in perspective, here's another view of that same annotation, which shows the path taken by the annotator in the context of a 3D mesh of the environment, and the color coding between the arrows and the light cast by the annotator's camera view aligns to the words in the text instruction shown on the right-hand side. So this is exactly what the spatio-temporal grounding that we've collected can look like. We can also look at this in terms of image space rather than a 3D mesh. So it's very interesting to see when we follow the movements made by this annotator and look at which pixels at each point in time of the 360-degree image, which pixels they actually looked at. You can see a nice alignment here between, say in the second image, the wall painting, which is seen in the image and then mentioned in the instruction, and so on. And so this is a really nice alignment between image and text, which we hope will be useful for training in various ways. And you can see a very similar alignment. So this is for the follower task, where a separate annotator is charged with following this navigation instruction. And again, we see a very similar alignment between the vision and the text. Just to briefly survey some of the interesting linguistic phenomena in the RxR instructions, in this case, in comparison with the R2R dataset, because the instructions and paths are generally longer, we see quite a lot of co-referencing. There's also a lot of sequencing in terms of an ordering that's provided to the instructions. We see a lot of mentions of allocentric relations, such as a window with a black folding table under that. So the position of the table is described with respect to the window as opposed to the observer. And there's this interesting and fairly new phenomenon for these data sets, which is we call state verification, where the annotators will frequently describe nothing more than what you should see at this point, and that can be used to verify that the instruction's been followed correctly so far. So based on this data set, we've released a number of interesting challenges. The RxR challenge is a multilingual vision and language navigation challenge using the RxR data in Matterport 3D environments. And in this challenge, the agents navigate through a graph-based environment, which is the kind of typical approach for these styles of data sets. We've seen some interesting advances on the leaderboard, and this is open for ongoing submissions to try to close the gap to human performance. Now, as well as the RxR challenge, we've recently also released the RxR Habitat Challenge. And so this uses the same RxR data and the same environments, but in this case, it combines with the Habitat Simulator, which allows for a low-level continuous motion in the environments rather than using graph-based environments. As you can see from this example here, this is a very, very difficult challenge because it involves not only multilingual language understanding and grounding, but also low-level control of the agent. To help get things started, we do provide starter code in PyTorch, and there's a leaderboard as well, which is available on an ongoing basis. So thank you very much. I hope the talk's been enjoyable, and certainly hope that other people have found this research program exciting. And I would like to finally acknowledge many of my awesome collaborators who've worked on the 3 projects that I've outlined so far. Thanks very much.
Hi everyone, my name is Alexandra Faust. I'm a research scientist in Google Brain, and today I'm going to share with you our recent progress on robot navigation in real world. In the United States alone, there's 12 million people, which is entire population of New York City and Los Angeles, that cannot leave their homes without any assistive device. Pandemic taught us that all of us can be in that situation, and having robots that can deliver goods, grocery items, food and medicine, and so on, can make a huge difference in all of our lives. But what is really that we need to achieve that picture? Well, we need autonomous robots at scale, in real world, on real robots. What do I mean by that? So let's look at this example here. We have a robot that we started at one point, and it's trying to get to the sink, and we repeat this scenario over and over. There are people around, things are changing, environment is changing, and that is real world. Now we have a person standing here in front blocking the way, so robot needs to go around the table, person coming in. That is what we mean by real world. This is, by the way, fully trained, reinforcement learning policy, trained fully in simulation and transferred in real world. Here we have a janitor. We did not stage this at all. So in this case, the robot observes the environment with a LiDAR sensor. It controls itself with the angular and linear velocity, and it just needs to get to the goal and deal whatever it needs to deal in order to get there. It doesn't need to know where it is in environment, why is it going there, and so on. It just has a goal and needs to get there. On the other hand, we have robots, and robots come in all shape and sizes, and their sensors, their dynamics, their bodies, and even onboard compute determine their abilities. They determine how they move and what they're capable of, and what is exactly, all of them can go from A to B, but how they get from A to B, that motion varies very much. So, for example, the little quad rotor can fly overboard. The fetch robot and freight robots move on the ground, but freight robots, because it is shorter, can go under tables and so on. So we like to have safe and feasible motion in this dynamic world where they need to operate. And ideally the same methodology that we can train any type of robot to perform to the best of its own abilities. So classical approaches generally do not scale. And classical approaches consist of the standard perception and SLAM, and then goes motion planning and control. It's modular, it's great, it does not scale. And the reason it does not scale, there are two reasons. There are many, but for the purposes of this talk, one is because as we kind of transfer between the robots and the environments, each layer does not know about the strengths and the weaknesses of the previous layer, and then we can design different heuristics to make them work. And the second reason it doesn't work is a classic pipeline treats every instance of the problem as a new problem. There is no method that takes the experience from all previous examples and so on and kind of summarizes them. That heuristics is called human engineer, right? But in terms of the classic pipeline, there is no learning. So, but we can do that. So can we borrow a book from biological systems and see how biological systems handle that? So just an example, one thing we know is that we always observe with sensors and we always express ourselves with emotion, and whatever happens in that box stays within box, right? So first thing that happens with biological systems is that the evolution determines what is the system capable of. It determines the hyperparameters of the system, if you wish, that is tuned to the environment and the tasks that the system is going to perform. Now, once we have the system, we then interact with our environments. This is my daughter learning to walk and interacting with the environment. And we practice the skill until we get better at it. And then finally, once we have some competency, we reflect on our experience and we learn from it. And we know how to predict in the future that certain things work or might not work and so on. We call this intuition. But real intuition is our prior experience fit into a predictive model. So can we learn some of this? Can we take the inspiration from the biological system and apply them to the robotics and navigation specifically and see how we go? So one thing that we first need to ask is what are the basic skills that we interact with the system, and then how that can be a building block for the larger, more complex things. So from that perspective, in the rest of the talk, we'll ask first question, how to get to a goal, how can we learn these policies like we described earlier in the talk, where robot is just reacting and going from A to B, dealing with the real world. And then in the second part, we're going to talk about how we determine what the goal should be. In that case, the robot needs more context and so on. And the caveat here is that finding the goal not only needs to be optimal for the task that's being solved, but also needs to be feasible for the robot, for the competency of the robot. So the first question is how to get to a goal, and here we're learning the goal condition, obstacle avoidance control policies. They don't need to know where they are, they just need to get where they need to get. And that kind of lends itself very nicely to reinforcement learning. And one way to learn that is that our robot, the observations are goal and the noisy LiDAR observations. The actions are linear and angular velocity, like I mentioned earlier. And then we train the environment in a small static environment. The key here is how to design the simplest environment that we can to have the zero-shot transfer from sim to real. And then the objective or the reward should be whether the goal is reached or not. However, that is sparse objective and not conducive to training. So we end up having to do lots of engineering to find the right reward that's conducive to that training. The second design choice that we need to make is around neural network architecture. And again, this is very human-intensive process, and how to create a simulator, as I mentioned. So in order to get these policies to work easily and scalably, we first approach the automation of the rewarded neural network architecture. And the way we do this is it's a two-step process. The observation is, the insight is that for the rewards, learning intrinsic rewards is, we have generally a good intuition what the relevant features of the intrinsic reward are, even though the objective is sparse. So in this case, this might be things like, I don't know, the distance to the goal, the velocity of the robot, the angular, the orientation, and so on. So the first step, we learn the intrinsic reward. And in the second step, we learn the neural network architecture. So our intrinsic reward is parameterized features. And we initiate population of agents, each with the different parameterized reward. We train the agents, we evaluate their performance within task objective, whether it completed the task or it did not. And then the mutator proposes the new reward based on the performance of the previous one and spawns a new training agent. And we keep repeating that loop for a while until we find the reward that fits the learning task and makes it tractable. Once we have the reward, we repeat basically the same process for the neural network architectures. So the parameterization here can be the number of layers, the width, and the depth of the networks, and other hyperparameters of the neural network architecture. And again, same process, randomly initiate, train, evaluate, except that this time we're evaluating with respect to the cumulative reward. Propose the new mutation until we're happy and we find the policy. And just as a side note, we also asked how general really is this reward search? Is it working only in navigation, or does it work across the other environments? So we did a benchmarking across several reinforcement learning algorithms and several benchmarking environments. And we found out that reward search helps in more complex tasks. The more complex and difficult task is, the automation works better. The second finding is that it really doesn't make sense to create complex objectives, that the simple sparse here we reach there, or go as fast as you can, works almost as well without any hand engineering of the skills for the task objective. And finally, we found out that on a fixed training budget, if we're starting with the reasonable hyperparameters, the training budget is better spent on learning the rewards then tuning the hyperparameters of the model. So back to the navigation. So to get the navigation in this zero-shot model working, we first initiate the training in simulation with a noisy sensors, actuators, and kinematic model, basically adding as much noise as we can. And we initialize, we randomize initial and goal conditions. These two lead to policies that are resilient to noise on the real robots, and are capable of zero-shot transfer. And then we train via this automated RL process that use 2 steps, learning the rewards first and then neural network architecture. And that steps ensures the competency of the system. And then we just use the off-the-shelf algorithm. Once we have the policy, we do zero-shot transfer, and it runs on real environments, even with the people around, or other static environments, and so on. Again, this is reactive policy. It doesn't know why it's getting, it just kind of goes and adapts. The same methodology works across different robots, and that includes robots with the kinodynamic constraints, with the noisy sensors such as asteroid dynamics and so on, which is basically producing approximate solution to two-point boundary problem. And that's exciting. Now let's look at now into another robot that is also capable of navigation, and this is joint work with Vijay's Reddy's lab at Harvard. This is a crazy fly nano drone that has only 33 kilobytes of available RAM, weighs 33 grams, and costs under $300. How do we train and make this robot autonomous and do something useful? We train these models on high-end hardware that has GPUs and so on. And then the onboard hardware is Raspberry Pi that is much cheaper and so on. And in fact, when we plot the 2 trajectories that are run on one and the other hardware, they look very differently, which in this context actually poses safety concern. So to avoid this problem that damaging the robots, we developed air learning, hardware-in-the-loop simulation environment, where it builds on top of AirSim. We can add randomized environments and whatnot to create photorealistic scenes, and then be able to plug in the target processor directly and run policies and evaluate policies on the target processor, even though it's still running in simulation. And that is much safer. And not only that, but we can also observe and calculate the latencies that are resulting from these processors. For example, inference latency on Intel Core i7 is 3 milliseconds, whereas on Raspberry Pi is 68 milliseconds. And we can kind of build into the simulator and train policies on GPUs that are capable of running on Raspberry Pis. So to that end, then, one of the useful applications that we can do is source finding, or in this case, finding a light for the crazy fly, basically building an autonomous moth that if it senses the light and it's going to go towards light. And to do that, we equip the quadrotor with a light sensor and the 4 laser readings. We really want the sparse information, so the network needs to be compact to be able to fit on board. And in simulation, basically build a model out of observing the lights in the environment, and train in simulation using this technique with a hardware in loop, transfers zero-shot on the real crazy fly robot. So we talked about learning control policies here. These are the reactive policies. And we saw that training them in simulation and addressing all the sources of the sim to real gap are enabling us to do a zero-shot transfer to a variety of the real-world scenarios. And learning hyperparameters of the reinforcement learning models such as the rewarded neural network architecture and so on, with evolutionary and reinforcement learning together, leads to the competency, increases competency of the policies. And then domain randomization adds the resilience. Now, in the rest of the talk, even though we have these good policies that are promising and so on, they're not going to be perfect. So the question now is how we should place the goals such that not only they're leading to the higher level goal, but they're working with the imperfect policies and they're producing reasonable goals, because that's the other way to how to close this in the real gap. So the idea is, can we practice our control policies that are taking observations, telling robots what to do and interacting with the world, reflect on that experience and get better? So to get the goal selection policies, basically this is the policy that's going to tell our control policy what to do. And for that, we connected basically that selection policy should also work on the same information that control policy does. So have the same observations, and also should be able to have the access to the prior experience and see how the robot behaved in the past. And now once we have that experience, we can practice and collect the data. And via self-supervision, we can learn the predictive model that associates the observation now with the future performance of the system, or how the goal is reachable and whatnot. And then in the unseen environments, we can use that model to predict the goal selection. In naive words, for example, I don't need to go and roll out a policy if I see a wall ahead of me to know that I'm going to hit the wall, even though I haven't encountered that particular example before. But something similar happened before, and we can kind of know that that's not. So in the rest of the talk, I'm going to show two examples. One is on cooperative avoidance task, avoiding humans, and the second one is a cooperative rendezvous task. So this is joint work with Claire Tomlin's lab at Berkeley. And what we want here is, how do we do visual navigation around humans? So imagine having a mobile robot, and we want to basically put in any environment around humans and have the robot safely avoid humans and reach the goal. What are the challenges here? This is a CVPR conference. I don't need to tell you that zero-shot transfer from simulation to reality with the visual policy is difficult. So one choice is that we just train this in reality on real systems. However, that poses safety risk to humans, and also raises questions of the privacy and diversity of the human subjects. So if we do this in simulation, safety is not a problem. We have a photorealism to deal with, but then privacy and diversity of human data set is probably more manageable. So let's see how we address that. We know that there are data sets of human models, surreal, and we also know that there are data sets of the scanned realistic buildings, 3D, such as Stanford Large 3D Indoor Spaces dataset. And in this case, we combine the two, and we parameterize humans on the scene, that we can place them anywhere in the environment. We can parameterize their gender. We can parameterize their texture, clothing, skin color, facial features, and so on. We can parameterize their body shape, whether they're tall, short, etc. And their motion, are they moving straight or they're following different trajectories and so on. And then we can render what that scene would look like. And that gives us a really nice and rich playground. Then we can sample a bunch of scenarios and create a data set, avoiding any of the privacy and safety and diversity concerns that we might have had working with real human subjects. So here is an example what the humans placed in this data set look like, or the environment. So how do we go about training? We practice in the known environment, so they are placed in We randomly generate and place the humans, give them initial poses and behaviors and the goals where they need to go. And then we solve this problem with MPC, which requires knowledge of human trajectories in the environment, but that's okay, this is a training environment, so we know how this is going to roll out. And then to train, we collect a data set where we kind of propose this bunch of waypoints and we evaluate how each one of them does with respect to the rollout policies. And at that point, we associate the visual input with the optimally placed waypoint. So if I see this, this is where I should place the waypoint. Once we have that perception module, we put it in a system, so it receives image, it produces the waypoint goes in a system, and then the controller drives the robot there, and here we go again. And let's see, compared to the baselines that are not trained with humans, we get 80% versus other baselines without humans going under under 70%. And then looking at a couple of other scenarios, we see that, for example, in this case, when the robot is static, this would be the dashed line, the robot actually goes in front of the person. But when a human is moving, that's the red line, it actually goes behind the person. And that's kind of nice. This is the static human, this is the dynamic human. Kind of behind the scenes, seems like it kind of learns that the position of the legs is determining the motion and the speed of the human. In the second, compared to the baseline, we see baseline is the dashed line here, that it goes and it cuts off the human, whereas our method, when it's trained with the humans on the scene, actually goes behind nicely. It also, we demonstrated that also, even though it's not trained, it has some ability to handle multiple humans. So in this case, there are two humans on the scene, and the robot kind of goes and weaves between them. So let's see how this looks on the robot. Interesting part here is human is coming, and the robot is going to veer on the right. In simulation, was trained with a camera field of view 60 degrees, and on the robot, the camera field of view is only 45 degrees. And it still transfers, which is interesting. Here's another experiment, and the human is going to come behind the corner, and the robot goes around. In both of these scenarios, the baselines would actually collide with a human. So the second example is a cooperative task that I want to mention today. Let's assume that we have two agents, two robots. They need to meet, perform cooperative tasks. They're not directly communicating with each other. Basically, the only information they have is what they can observe with their sensors, because that's how we coordinate as well. And each one of them is equipped with some control policy, like one of these point-to-point policies, that can be different, and there are no assumptions, or that the planning module does not know anything a priori about them. So the question is, how do we train the models such that they can meet? And the idea is that we propose waypoints that are both feasible to each one of the robots and kind of will drive them towards the meetup. Now, to be able to do that, it would be very useful to have a model that can predict where I am going to be, where ego robot is going to be, and where the other robots are going to be. So FI is a model, ego robot model, that says, okay, here are the observations, and here is where I'm going, and responds with a pose where the robot is going to be in time delta t. And F minus I is model for the other robots. So given what ego robot can observe, where the robot teammate is currently and where its thing is going to predict where the robot is going to be in time delta t. So how do we train these two models? Well, we initiate the simulation environment. We randomly place the robots and randomly place the goals and let them run. And then we observe these trajectories and collect the data set that contains current observations, end goal, because that's where they ended. So observation, end goal that we're thinking, and where the robot was in time delta t. And that gives us a predictive model of behavior, so we can basically observe and learn how the robots are moving. And here are the loss functions for self-prediction and other prediction model. Not surprisingly, the self-prediction is better because we have better sensor observations. And then the other prediction is also slightly more error, but still working. And then to do the planner, which proposes where the robot should go next, we use model-based RL. Basically, we propose a goal, a first goal in the middle between two robots, and then each robot does this separately. So it goes and rolls out how the scenario might look like using the predictive model, and evaluates a bunch of these goals and finds the most promising ones, reduces the region, and finally selects the goal. The other robot does the same thing, and then they kind of keep going toward each other. This transfers zero shot to real world environments as well. And compared to the baselines, both learned and standard planning methods, actually drives the robots closer together than the compared methods. So here is an example. This is a COVID special in simulation, but we had the experiments on robots as well. In these scenarios, they meet. This is the baseline. They end up kind of in this local minima where they chase each other. This is another baseline. In this case, again, they actually keep running away from each other. In this scenario, again, they reach each other. And the baseline, again, comes in the local minima and they chase each other. So we covered two examples here about learning the goal selection. On two examples, one on the avoidance and the other one on the cooperative task. In both cases, we can observe the motion and learn predictive models. And then using these predictive models, apply them in new environments. So self-supervision and reinforcement learning together, reinforcement learning is a control policy and self-supervision is a planning policy, lead to the resiliency and competency. So overall, both on the lower level control policies and in the goal selection, we saw that to get robots to have zero shots into real transfer, domain randomization and training environment design, addressing it, all the parts of the sim to real gap due to the robot environment and modeling errors is important. Second thing, we saw that combining evolutionary algorithms with reinforcement learning algorithms leads to better reinforcement learning agents with less engineering. And the evolutionary algorithms automate reinforcement learning agents designed by learning the fixed properties of the system. And finally, self-supervision and reinforcement learning lead to the planning that improves with the experience that is within agents' abilities. So put together in this way, the planner will not propose the goals that are not feasible for the control policy that the robot actually has. And this is very important for the transfer. And finally, we saw that evolution, reinforcement learning, and self-supervision work together to produce the system that works in practice. What's nice about these things is the better algorithms along each one of these axes actually improves the performance of the entire system. So I presented several techniques here that kind of lead us towards robot navigation in real world at scale. There's many more things that we can be talking about and to look in the future, going towards more complex tasks, different robots, curriculum learning, and so on. but the future is there. And with that, I wanted to thank my collaborators without whom this would not be possible. And I want to thank you. Thank you.
Hi everyone, my name is Anka Dragan, and I wanted to talk to you today about our latest thinking in how to get robots and also AI systems more broadly to assist people, to help us out. So what do I mean by assist people? What is assistance? Well, let me share a few examples with you of recent tasks that we've been working on so that you get an idea of what I mean. So one of the tasks is assistance with navigation. Here, imagine you're visually impaired and you are trying to navigate in a house. And you can't directly perceive the scene in front of you. Looking kind of at the scene from a top-down view, you're trying to go somewhere, let's say here, but you don't know exactly where you are. Here, you could be there, and you don't know exactly how to get to where you're going. And so you need a little bit of assistance, of guidance. So the question is, how can a guide, an AI-powered assistant, sort of give you hints and help you get where you want to go? Another example is for users with severe motor impairments who are, say, trying to type a sentence in their email. So you can see a sentence at the top there. And what we did is we set up an eye gaze-based interface that presents a set of words to the users like so, and it waits for the user to look at the desired word, and then takes a picture of the users through their webcam. And given this webcam image, the interface then tries to predict which word the user wants to type. So it assists in the sense of helping the user actually type out what they want. And we're also looking at this same setup, but in collaboration with UCSF, the Department of Neurology there. They have a patient with quadriplegia. They implanted an ECOG array into his motor cortex. And so for him, instead of gaze, we're using the brain signals, what we're recording from the ECOG array. And we want to map that to the word that he wants to type. And the final example is one where you're trying to operate a robot with complex dynamics. Our stand-in for that here is the Lunar Lander from the Lunar Lander Atari game. And it's really hard to pilot this craft, even though it's in simulation. So these are users without any motor impairments trying hard to land this in between the flags and not crash. And they're doing a pretty poor job, as you can see. I also do a really bad job when I play this game. So these are examples of assistance. And in all of these tasks, users have a policy mapping their state that they're in to sort of the input that they provide to an interface. And then a decoder can take that input and translate it to actions that the system can execute, right? Be it which word you're typing or the controls for the lunar lander. So their input would be kind of keyboard input, and then these would get translated by the decoder to controls for the lander. And a typical way to do assistance here is to look at the user's actions, which are going to be really noisy and suboptimal. And instead of just playing them out, executing them on the robot, the assistant would actually try to infer what the user's intent is, what their goal is. For instance, where are they trying to land? Or where in the house are they trying to go? What sentence are they trying to type? So that's their high-level goal. And then the assistant, based on this goal or on a distribution, would take actions on the user's behalf to better achieve that goal. And this presents some challenges. So we've gotten pretty far with this kind of methodology for assistance. I've worked on this. A lot of other people have worked on this, but we're kind of getting stuck on some things. So one challenge is that same suboptimality in the user actions that requires you to have assistance to begin with, that suboptimality also makes it really hard to figure out what the user's goal is. Like in the lunar lander, they overshoot the goal to the left or to the right, and that leads to wrong inference. You can see here a distribution over goals for these two examples. And by overshooting sort of to the right, that makes the assistant infer the goals on the right as opposed to the true goal, which is here in green. And then the assistant assists with the wrong goal, which is bad. Now, even if we inferred the correct goal, we're then kind of doing the task for the user. So we're taking away the person's autonomy by just completing the task for them and overriding their input. And that's not a very empowering experience. So here in this example, at some point, the assistant just takes over, not here, about here, they just take over and just land. And sure, that gets the task done, but it deprives the user of their autonomy. And so we've been wondering, could we do assistance differently? Could we, instead of correcting the user's actions to make them optimal for their goal, could we somehow just let the person do their thing because they know what they want and enable them to take the better actions, the close to optimal actions by themselves? Could we assist them such that the actions that they're actually commanding end up being the right actions to take? And I think that would be kind of the holy grail. You're not intervening and overriding at the end. So you instead of just correcting their actions at the end, you're somehow injecting assistance in some way so that these actions that come out from what the user is commanding are just the right ones to begin with. And so to figure out how to begin thinking about this challenge, we had to ask ourselves, well, why are users taking actions that are suboptimal? Why do they need assistance in the first place? Why are these actions that are coming out so noisy and bad? And there's many answers to this, but one answer that we've been investigating is that part of what explains why the actions are suboptimal is that this picture of the person sees the state and that's what they use to decide on what to do is wrong. Much like robots, people don't get to see the state, they get to see observations, right? It gets sensory input. And they're acting not based on the state, but based on their belief about the state of the world, their estimate of the state. And that estimate could be wrong. If that estimate is wrong, that leads them to make wrong decisions. So it leads to suboptimal actions when you look at the correct state that they're in. Now, why on earth would their belief be wrong? Well, plenty of reasons. Here's some examples. It might be wrong because of information overload. So people might not be able to pay attention to many different sensors at the same time, which means that they're not going to have the proper estimate. Even see lens distortions that are causing users to overestimate distances to objects. And in general, we know that our perception system is messed up and wrong in some ways because otherwise optical illusions wouldn't be a thing, right? So all humans misestimate the state here, and that's because of these biases and shortcuts that are in our perception system that are really helpful in some ways and really damaging in others. So if we want them to take better, closer to optimal actions, if we want them to command better actions, then our idea is that instead of correcting their actions, we should see if we can correct their belief, as that in turn enables them to make better decisions and therefore to take better actions. Now, we can't just incept a belief into the user's head, but what we can alter in a lot of tasks, in a lot of cases, is the observations that they receive. So the key idea in this work was that the full observations are not necessarily the most informative about the state of the world, especially when they're processed incorrectly by the user due to the systematic biases in their perception. So our thought was, let's look for other observations, sort of kind of lie to the user about what they're seeing. Other observations, instead of OT, some OT tilde, that when the person processes that through their sort of biased processing perception system, they end up nonetheless with a better belief, with a more correct belief. So the way we operationalize this is by using an automated assistant to process the full observation on behalf of the user. This assistant performs state estimation unencumbered by systematic biases or perception difficulties that the user has. And then the assistant provides the user with a modified observation, this OT tilde, that when processed by the user suboptimally, incorrectly, it leads to them having a more accurate belief than they would if they just saw the raw unfiltered observations, OT. And so the way we come up with OT tilde formally is we try to minimize the KL divergence between the assistant's beliefs and the user's beliefs. After the assistant processes the true observations, right, you end up with a belief. It synthesizes a modified observation that it thinks will make the user believe in the same state as the assistant. So that will induce a similar belief in the user when the user processes it with their model BH hat here, that the assistant has when the assistant processes the correct observation OT with the correct model B. Now, why is the assistant belief the target here? Why is that the holy grail? Well, because robots don't suffer from information overload. They can apply Bayes' rule correctly. And so, of course, they don't know exactly the state, but they have the correct belief about the state given all the observations that they received. And so we're trying to minimize the KL divergence between what the user ends up with and what the robot ends up with. The challenge, what's hard about this, is that we don't have access to the user's internal estimation process. We don't have access to this BH hat. So what we propose is to learn it from demonstrations of users' actions. So we look at user actions and then we try to figure out, we try to kind of back derive what a BH hat is that fits that. And so we model the likelihood of the user taking a particular action AT, given a history of observations and actions so far, by marginalizing out the state, right? So you see this integral over S, and what that does is it helps us break down this likelihood of the user action into two components. First, there's a near optimal policy for the completed task, so AT given ST. And then there's a parametric representation of the user's sort of belief estimation process. So that BH hat, which we can parameterize however we want, for instance, with a neural network. And what's nice is that we can compute the near optimal policy. We can observe these actions on the left-hand side. And so we can use this equation to back derive what the belief model for the user is that's consistent with the data that we're seeing. The way we train this is by optimizing the user's estimation model so that those data parameters in the belief model to maximize the likelihood of the user actions that we observe, the actions that the user end up taking. So that's what we do. And we applied this to assisting people navigate indoors. So again, they can't directly perceive the scene in front of them. They're somewhere over here. They're trying to reach a position over there. If they think they're in one corner, but they're actually in a different corner, that's where they're taking suboptimal actions. So let's try to fix that. So we have an agent guide that can see the user's egocentric scene and figure out what objects are around for them. And the guidance that this guide, we have some options here of how the guide can intervene. The assistant that they provide is to tell the user about what is around them. You could also have vests that are haptic and so on. But we went with tell the person what's around them. And a default guide would just tell you about the stuff that's around, sort of in an unfiltered way. That'd be a bit overloading in terms of information and not necessarily very informative. But nonetheless, you'd update your understanding of where you are based on that to the best of your abilities, and you try to navigate. Now, in contrast, our guide selects objects to tell you that are going to be informative to you. And this tends to result in more accurate user beliefs, and as a result, in the user taking less time to reach their goal. This is what we see in our experiments. We also looked at a different task, this lunar lander task, and we made it a bit more complicated, where we made it difficult to see where the lander is, and we added this horizontal tilt bar as an indicator to help user perceive the angle of the lander. And what our assistant learns here to do is pretty cool. It learns to exaggerate this tilt of the lander to kind of compensate for what seems to be an apparent inability that we have to correctly estimate the tilt ourselves. So on the right, you see what is actually happening. And the left is what you would see by default. And then in the middle is what and I'll play this again. In the middle, you see what the assistants decide to show you. And it's wrong. It's not the correct tilt. Essentially, by the agent lying to you about how tilted the lander is, you're able to keep the lander more level. And we see this in a user study. And so basically what seems to be happening is that if you have a slight tilt, it's not noticeable and people don't end up correcting for it and then they crash. However, if you see this exaggerated tilt, you have an easy way to detect it. And it turns out you don't overcorrect. You correct just right so that you end up keeping the thing level. And that angle is different for every different user. So there's some customization. It seems like each of us can benefit from a different level of exaggeration, and the assistant picks up on that. Okay, so in a nutshell, we've been getting creative with how to enable users to take good actions on their own, which I think is a pretty empowering way to assist, right? Instead of just doing stuff for them, just get them the information that they need in order to make the correct decisions by themselves. And in the remainder of our time together, what I wanted to share is 2 quick alternative ways through which we can do this, to which we can improve these actions that people are taking besides correcting their beliefs. So if we want their actions to be good, to be close to optimal, another avenue besides correcting beliefs, and this is perhaps a much more obvious avenue, is to just improve this decoder that maps between their interface, their input, like a keyboard or gaze, to the actions that apply to the sort of the system. And how does this decoder work and how could we make it better? Well, let's remember this typing task, for instance. The overall goal here is a sentence at the top. The actions are the words. These are the decoded actions, but the input is gaze. So how do you train a decoder from gaze or brain signals to the commanded word? How do you do that in the first place? And so what is there to improve on? Well, it turns out there's something to improve, because the standard way in training these decoders, sort of having this calibration stage of the interface through supervised learning. So it requires, we see it here happening, a new user to provide this paired data of inputs and actions, and then you do supervised learning to train that. And this can be time consuming and disruptive. And actually, what is even worse is it drifts over time. Our patient at UCSF, for instance, we see the readings at the beginning of the session. They're very different from the readings that we get for the same sort of task at the end of the session. So you see drift happen, and you see this interface, the decoder, degrading in performance, even over the course of a day or even a few hours. And so there's drift, which means that these interfaces have a lot to be improved on. And here's what happens when you use them. So you start typing, and the decoder inevitably messes something up. And when that happens, you usually have some sort of backspace or undo action. You have to, otherwise you won't be able to fix anything. So this could be, for instance, sort of their sip and puff interface. And our simple observation here is that there's a lot of information in that backspace that we should be using. So instead of learning a decoder once and keeping it fixed, we should notice that whenever the user does backspace or undoes something, they're leaking information. They're telling us information about what the decoder should or really shouldn't be doing. And we can learn from that. And so that's what we did. Our method for learning from these backspaces is pretty simple. We present a set of words to the user. We take a picture of the user's eyes through their webcam, then feed this input to our selection policy. We sample an action from this policy. The user sees this action, compares it to their desired action, and then they decide whether or not to backspace. And this decision to backspace kind of naturally provides our system with feedback that it can use to derive a reward signal. And then train a policy through reinforcement. So in particular, we train a reward model, we train a reward signal to be kind of this binary classifier that predicts the likelihood of this backspace to happen. And what this lets us do is it lets us actually use the default interface and the default decoder and improve upon it. So the way we use this trained reward model is as an update, a likelihood update on the default interface. So we take the default interface, we update it with the reward model, and then that's, lo and behold, our interface. And what's cool is that it doesn't make any assumptions about the type of user input. So in addition to conducting experiments with users who provided gaze input, we also tried this with our patient at UCSF who used their ECOG brain-computer interface to provide input to the system. And I have to say that this was by far the most exciting part of this project, even though we had to really simplify things for this to work with the patient. So we just had 4 words, as you can see here in the top left. Nevertheless, it was so cool to see a person thinking stuff and then being able to type. And we saw that just sticking with the default calibrated decoder, so shown here in the gray bar, ends up with significantly lower accuracy when compared to this way of learning online. So it seems to actually be working for them. And interestingly, we saw that the default interface, maybe because of this drift issue that I was talking about, it ends up never predicting the topmost button as an action, so the topmost word. So there's a 0% recall rate for that action. And in contrast, we saw that with online learning, when you do this reinforcement learning thing on top, you achieve 70% recall on the topmost action. And that's cool, and it's important because it suggests that the online learning can overcome these challenges in the default interface over time as you're getting these corrections. I'm not going to get into details on that, but we see with gaze input, here we actually ran a user study with 12 participants, and we found that learning a reward model substantially improved performance here as well compared to the non-adaptive interface. And maybe what was more interesting is that the default interface performed particularly poorly for the users where the online training helped the most. So sort of that makes sense. So what we see is that by learning the decoder online and sort of back to beginning of the talk by correcting the user's beliefs, these are both ways through which we can really empower users to take the right actions for themselves. And they can be good alternatives to sort of having the system try to figure out their long-term goal and override their actions. And now to wrap up, I just want to give you one final idea for how to achieve this type of assistance. And we got the inspiration again from Lunar Lander. We got a lot of mileage out of this Lunar Lander game. So if you look at what's happening here, the lander becomes so unstable that it's really hard for the user to do anything. No matter what their goal is, no matter what they want to land or what they want to do with the aircraft, maybe just they want to hover it or something like that, they can't do that because they so easily go to these states of instability from which they can't do anything. And we thought that's the problem. We thought that maybe we don't really need to actually infer their goal to help them. What we need to do is get the system to be more controllable so that they can help themselves. So we've thought about this as increasing the user's controllability over their environment. That is the ability to affect actions, to affect the environment through the actions that they're taking. And mathematically, we formalize this notion via this information theoretic concept of empowerment, the mutual information between the user's actions and the resulting states. So low empowerment situations are those in which you're kind of stuck and you can't do much. They're bad. High empowerment states are where you have a lot of controllability over the environment. You can get to many places. You can do many things. And the way we then get an assistant to help increase empowerment is by just giving it as part of the objective. That's your job, is to make sure that the person stays as much as possible in states of high empowerment. This is the example result, or one example result. Even though the assistant here cannot observe the flags and so has no idea about the goal, it nonetheless enables people to land by making sure that, basically by stabilizing the craft. And that's kind of a natural consequence of optimizing for empowerment. You get a craft that's much more stable, therefore easier to control, and you can just go ahead and land it yourself. And so I think that this alternative, right, to typical assistance, this different paradigm is I think really worthwhile thinking about. So instead of figuring out what people want and then having a really smart robot kind of do it, it seems possible to find ways to empower people to take good actions by themselves and do the task themselves. And I think that's good because ultimately they're the ones who know what they do. When we try to infer the goal, we get it wrong all the time. And so if we can just enable them to do what they want, I think that's amazing. And it seems like there's a proof of concepts that we can, or else we can improve things significantly, be it by getting assistance in processing information that they're getting, or making systems that adapt over time as the user changes, or by simply just optimizing for users to be empowered to do whatever they want very directly. I think all of those are ways that get at the same notion of get the person to be able to do the task by themselves, that they want by themselves. So with that, I'd like to thank you, and to also thank my collaborators on this work, especially the students who did the work, other faculty and industry collaborators, and definitely a big thank you to the UCSF Ganguly Lab, without whom this would have never been possible. So thanks so much, everybody, and stay safe.
Hi everyone, I'm Akshara Rai from Facebook AI Research, and today I will talk to you about sample-efficient learning for legged robots. When we think about learning for locomotion, there are a lot of impressive works that have come out recently. For example, here is a quadrupedal robot which is navigating this really rough, unknown terrain. Here is a bipedal robot which is taught to walk using reinforcement learning. Here is another bipedal robot which is which is running on rough terrain, including with disturbances such as slipping, and a quadrupedal robot which learns to trot, pace, etc. from simulation, and then transfers this to hardware. All of this is really impressive work, which looks fairly different from each other. But if you look closely, they all have one thing in common here. It's that none of them use any visual perception. So especially on the left here, right? So you see this robot navigating this really challenging terrain, but the LiDAR sensor is actually pointing backwards. It's because the robot's not really using this information from the LiDAR sensor to update its navigation policies at all. And this is a really common paradigm in legged locomotion, that they don't take any visual perception. And as a result, they often also don't have any online adaptation. So the top two works here are learned using a simple model or simulation. And then the policy is kept constant on hardware, even though we know that in legged systems, because of contact differences, the behavior between simulation and hardware can be significantly different. There is purposefully no online adaptation in these works. And that's basically what will be the main crux of my presentation today, is how do we teach legged robots to perceive their environments so that they can take into account what's happening around them in making decisions. And then once they can perceive their environments, how do they use this information to adapt their policies? And I will talk about two different unseen settings here. One is transfer to hardware, bridging the sim-to-real gap, and the other is transferring to new legged robots, which were never seen during training. And I want to stress that all of this would be focused on doing this sample efficiently, because legged robots, unfortunately, are also very fragile, and they will break if you take a lot of samples on them. So we want to limit the number of samples we have to take, but adapt our policies online based on environment input for legged systems. So let's first talk about how do we adapt policies online to unseen settings. And in this case, the unseen setting or disturbances come from the sim-to-real gap. So in this work, we basically learn latent representations that are designed for adaptation on hardware for a particular legged robot. And the idea here is that we are proposing a hierarchical control framework, which is learning a low-level policy and a high-level latent action in simulation, which can together basically represent a lot of different behaviors on different legged robots. And then once we have learned this low-level policy and latent representation and simulation, we move to hardware where we learn a high-level dynamics model, given this latent action space that was learned in simulation. Once both the low-level policy and the high-level dynamics model are learned, we can do model predictive control on hardware to adapt to online disturbances. So how would we learn such a low-level policy and latent representation in simulation? And the main idea here is that our low-level policy pi with parameters theta, along with the high-level latent representation z, should together be able to represent a lot of different walking gaits. So in this case, for all of these videos, we have the same low-level policy parameters theta, but different samples in this learned latent space z, which result in different movements on the robot. So for example, the robot could be turning left, right, going backwards for different parts of this learned latent representation z. To learn such a latent space z, as well as the low-level policy theta, we start by collecting expert demonstrations in simulation. So in simulation, we assume we have perfect knowledge of the dynamics of the robot, and we can use inverse kinematics for collecting experts that can perform a large range of behaviors. Next, we randomly initialize a common shared low-level policy theta, but expert-specific latent variables z. Next, we calculate supervised learning loss with respect to each expert and then sum it together to create the total supervised learning loss over g experts. Now we can minimize this total supervised learning loss to learn one low-level policy parameter theta and g latent variables z, which basically gives us a setup like this, in which multiple experts from simulation are used for learning one common low-level policy and one latent space z, which can together represent at least the g experts which were used during training. But since now this is a continuous space, z is actually a continuous space, it can also represent gaits that were not seen during training. So for example, by randomly sampling z and changing z during this experiment on the right, our robot can go from going backwards using the gallop gait to going forwards using a trotting gait. And by continuously changing z in this continuously learned space, we can exhibit basically gait transitions on our robots. Now, once we have learned this low-level policy parameterization theta and high-level action space z, the next thing we do is learn a dynamics model where z serves as the action. To do this, we basically randomly sample a large number of z's and measure the resultant change in state of the center of mass of the robot. Given this data, we learn a high-level dynamics model which transitions from the old center of mass dynamic state, a commanded high-level action z, to the next center of mass dynamic state, keeping the low-level policy pi theta same as what was learned in simulation. Now, once we have learned this dynamics model f, we can use that for planning over z using model predictive control to achieve a large range of tasks and optimize many different cost functions. So for example, here is Daisy reaching 8 different goals along a circle using our framework in which the low-level policy was learned in simulation, but the dynamics model was learned on hardware using only 2,000 samples. Now, since this is a dynamics model, it can also generalize to other tasks. For example, trajectory tracking. So on the left is DAISY achieving different trajectories on hardware, and on the right is DAISY following a collision-free path to goal. And in both of these cases, the low-level policy is actually the same, which was learned in simulation. But the high-level dynamics model is different between hardware and simulation. And that's how we can adapt the dynamics model to hardware. We also compare our approach against other learning approaches from literature. And what we observe is that our approach, LAT, is able to outperform other learned hierarchical approaches from literature on velocity tracking, goal reaching, and trajectory tracking, applied to two different simulations of DAISY and A1 robots. And the main reason for this is that typically hierarchical approaches from literature are model-free. On the other hand, we are learning a high-level dynamics model, which enables us to generalize to tasks which are very different from what was seen during training. Next, we also compare our approach against inverse kinematics in simulation. Inverse kinematics is a really challenging setting for our approach because inverse kinematics assumes that it has a kinematic model of the robot. On the other hand, our approach does not make any such assumptions about the kinematic knowledge of the system. What we observe surprisingly is that in normal settings, our approach is able to perform comparably to inverse kinematics on both DAISY and A1 simulations, again on velocity tracking, goal reaching, and trajectory tracking. However, because inverse kinematics is making assumptions about the kinematic knowledge of the robot, its performance deteriorates when this kinematic assumption is violated. So for example, in the bottom here, we disable the back two legs of the robot, and inverse kinematics is unable to balance the robot anymore and falls over, while our approach is able to find, still able to find a latent representation Z, which is able to navigate, achieve a lot of these different tasks. And the key insight here was that because we learned our latent representation instead of a hand-designed fixed latent representation for IK, given settings in which the kinematic assumptions are violated, model predictive control is still able to find reasonably good behaviors, while IK suffers significantly more. So in conclusion, this section of my talk was about how do we adapt policies online to unseen settings. And we proposed an approach here in which we learned latent representations or latent action spaces, which could capture different dynamical properties. And by optimizing in this learned latent action space on hardware, we were able to adapt to unseen settings, including when two of the legs of our robot were actually damaged. Next, let's talk about how can we sample efficiently teach legged robots to perceive their environments as well. So using perception in navigation is fairly common. For example, here is a work which trains a navigation policy in simulation for Locobot, and then is able to transfer this on hardware in this particular experiment. But what happens when we take a point nav policy like this, which is trained on a spherical dynamics model, so no dynamics, just a sphere moving in space, to a legged robot like DAISY? So the sphere has no knowledge about the dynamics properties of DAISY. So it doesn't know that DAISY has a limited turning radius, it has torque and friction saturations. As a result, DAISY gets stuck on this corner and is not able to reach the goal. So when we want to learn navigation policies on legged robots, we need to take the dynamics of those robots into account. To do this, we again propose a hierarchical control framework where we learn first a high-level policy that reasons about the robot motion using egocentric input of the environment. So it takes RGBD inputs from the environment and commands desired center of mass velocities at 2 Hertz. This desired center of mass velocity is taken as input from a low-level policy, which operates using inverse kinematics and a footstep generator to create desired joint angles at 100 Hertz for our robots. If we use this kind of a pipeline, which incorporates dynamics of the robots into the learning, we can learn hierarchical navigation policies for legged robots. So for example, here is Daisy, which has been trained using the approach I just described, and it's navigating in this new house it has never seen before, and it's able to reach the desired goal. But what happens when we take such a policy, which was trained on one robot, for example, Daisy in simulation, and transfer it to hardware or another legged robot in the same simulation? So here is Daisy, which was trained in this Gibson simulation. It's able to reach this goal. And now we apply the same policy on AlienGo for the same initial and final conditions. And what we see is that AlienGo tends to drift towards the left, and then it exceeds maximum amount of steps and does not reach the goal. So even in the same simulation, for different legged robots, there are significantly different dynamical properties, which will cause a policy learned on one robot to not transfer to another. And we can expect the same behavior on hardware. So how could we learn navigation policies across multiple legged robots? And for this, we propose that we should learn shared navigation policies across multiple robots. And for this, first, we basically propose an off-policy training approach in which we collect navigation data from multiple legged robots, A1, AlienGo, and Daisy during training. Next, the data collected from all 3 robots is collected into a replay buffer, which then calculates a joint loss used for updating the shared navigation policy. However, each robot's individual replay buffer is also used for updating a robot-specific latent embedding. So while the joint loss across A1, AlienGo, and Daisy is used for updating the shared navigation policy, the robot-specific embedding of Z-A1, Z-AG, and Z-Daisy are updated using individual robot replay buffers. This basically leads to a training approach in which the navigation policy is shared across robots, but at the same time, we also learn robot-specific embeddings. And this has basically several advantages. One, it increases sample efficiency because now you're using off-policy training from data across multiple robots. So we are getting 3 times as much data for the same number of steps per robot, as well as robustness to dynamical differences. So now since A1, AlienGo, and Daisy, all 3 have different dynamical differences, and all of this data is together used for training our shared navigation policy. Our shared navigation policy is automatically robust to these dynamical differences. Now you may ask, what does such a learned robot-specific embedding capture? So what we observe is that once we have learned this robot embedding, and we keep the shared navigation policy fixed, and sample different values in this embedding, we observe different behaviors in our center of mass space. So for example, on the left is Daisy, 4-legged Daisy with Z is equal to 1. In the middle is 4-legged Daisy with Z negative 0.5, and on the right is Z negative 0.7. And these three different values of the latent embedding result in very different center of mass behaviors across DAISY. In the left two cases, it's not able to avoid obstacles, but on the rightmost case, it's actually able to avoid obstacles and reach its desired goal. Which brings us to basically what we want to do in test settings. So given a new robot, what we can do is search for or optimize for the learned embedding Z, which results in good performance on these unseen robots. So to test this approach, we consider two sets of experiments on cart poles, in which we have 3 training cart poles and 2 held out test cart pole models, as well as legged robots, in which again we have 3 trained legged robots, training legged robots, A1, ALINGO, and DAISY, and 2 test held out legged robots, LicaGo and 4-legged DAISY. For cart pole, we create these different environments by changing the mass, pole length, and pole offset of these different cart poles. So I would like to draw your attention towards CP4, which is the hardest to control cart pole in our experiments, test cart pole, because it's out of distribution from CP1, CP2, CP3. So essentially, CP5 is testing generalization of our approach for in-distribution systems, while CP4 is testing generalization out of distribution. What we observe is that for training on CP3, Learn Z, which is our approach, performs the best, learns the fastest and achieves best performance against a few baselines from literature, as well as against ablations of our own approach. So we compare against Meta-RL, Z, which takes dynamics parameters as input, as well as no Z, so learning one shared policy across all cart poles, and a fixed Z. So Z is initialized to a random value and then kept fixed. Next, on test systems, what we observe is that on CP4, there is a significant improvement when using our approach, Learn Z, versus other approaches from literature, showing that such a learned robot embedding is actually able to generalize to out-of-distribution cart poles much better than using other approaches from literature, such as Informed Z, which is a baseline which takes the dynamics parameters explicitly as input when learning the latent embedding. Next, once we confirm that our approach works well for cart poles, we ran experiments on legged robots. And in this case, we created 3 trained robots in simulation, A1, ALINGO, and DAISY, and then tested our learned policy with new optimized embeddings on 2 previously unseen simulation robots, LicaGo and 4-legged DAISY, as well as on A1 hardware. So here is our A1 trained robot. So the robot is trained, but the environment it's put in is a new environment. So it has never seen this environment before. It's able to navigate this environment and reach its desired goal. Similarly, ALINGO, using our shared policy now, can fairly directly reach this desired goal in a new test house. It can turn around and avoid obstacles to reach its goal. Here is DAISY, which is very different dynamics from A1 and ALINGO. Again, trained using our shared policy, is able to reach this desired goal in an unknown house. And here is LicaGo, which was a test robot. So we optimized an embedding for this robot in another house, and then tested the robot in a new house, and it's still able to navigate to new goals in this unseen environment. Same for 4-legged DAISY, which is the out-of-distribution robot, which has significantly different dynamics from all of our training robots, and still manages to navigate to a new goal in this test house. Next, we can also transfer the same approach to hardware. So in this case, we do not optimize our embeddings on hardware, but take our shared navigation high-level policy, train in simulation, and apply this to the A1 robot on hardware. And what we see is that despite a lot of sim-to-real differences in the depth camera as well as the low-level policy performance, our high-level policy is learned robustly and is able to generalize to new goals in this completely unknown home that the robot had never seen in simulation. This is also consistent for like a large range of initial and final positions, and the robot is successfully able to avoid obstacles to reach different goal positions in this new house. I wanted to say that, here I wanted to say quickly that this was one of the first works that showed that we could train navigation policies in simulation using visual depth input here and transfer them to legged robots on hardware. So I started this talk by talking about how do we sample efficiently teach legged robots to perceive their environments. And I showed some results on one approach, which learns hierarchical navigation policies in simulation and then transfers them to new robots as well as hardware. To transfer them to these unseen settings, we adapt our policies online by learning latent representations that essentially capture different dynamical properties. And as a result, in unseen settings, for example, even when 2 legs of the robot are damaged, we can optimize in this learned latent space to find actions, basically policy representations, which can still achieve a particular task well. Thank you. Here are 2 papers that I primarily talked about in this talk. And some blooper videos of our robots falling over and running into obstacles when they were supposed to avoid them. Thank you.
Hello, my name is Konstantinos Bouzmalis. I'm a research scientist at DeepMind. And today I will talk to you about our recent work on cross-embodiment visual imitation, which we have worked on together with Yuxian Zhu, who was the lead on this project and also the creator of most of the content that you will see on these slides, and also Yusuf Aitar. Let me start with some motivation first. Why are we interested in third-person imitation at all? And I'll start by saying that this is a natural skill for humans. Humans learn new skills by imitation in third person all the time, and we do so from a very, very early stage, as demonstrated also with this cute video of this aspiring Rocky on the right here. And we as humans are able to observe behavior by others, process that visual information, and map it to our own embodiment in order to perform similar actions that arrive at the same results with what we are observing. Instead, in robotics, imitating just by perception other robots or humans performing complex tasks is still a very, very hard problem. It would be nice to have, though, and robotic learning usually requires carefully designed rewards, and we know that this kind of reward shaping and engineering does not scale to the kind of real-world complexity that we're interested in. So we do want to crack the problem of third-person imitation in robotics, as this could enable learning more complex tasks and learning them at a significantly decreased cost. It could make robots more useful by utilizing the abundance of visual data that exists out there. Let's make this more concrete. What we want to do is equip our robots with the ability of third-person imitation, specifically cross-embodiment third-person imitation. As an example, what I'm showing here is somebody in the lab using their hand to stack a red object on top of a blue object. And what we want our robot to be able to do is to understand what's going on in this video and replicate SAT's trajectories as precisely as possible using only vision. And I should mention that in this work, we are always imitating trajectories using this environment on the right in simulation. And our embodiment is a parallel gripper. It's a robotic gripper attached to a Sawyer arm. In order to be able to do that, there are a few challenges that we need to address. First, the challenges that have to do with imitating from pixels. We don't have access to action. It's almost impossible, for example, to define, let alone obtain actions for human demonstrators. There is no task reward, as we, in this scenario, we don't have a particular downstream task in mind. And finally, we either don't have proprioceptive information, or the proprioceptive information that we do have is different to the embodiment of our imitating agent. There's also more challenges that come from from working with different embodiments, and on top of the human hand that I have already showed, which is one of the environments that we are experimenting with in this work. We also have a human operating a pickup stick and manipulating objects that way. We have a 3-finger Jaco arm, and we have a real-world equivalent of our simulation environment. So it's a robotic gripper attached to a Sawyer robot in the real world. What we want is our agents to be able to imitate demonstrations collected with any of these embodiments and actually be agnostic to what embodiment was used and where these demonstrations are coming from. There are some related work in this space, and works that have to do with imitation learning that handles gaps between demonstrations and the environment the imitator is acting on is done primarily on hand-engineered feature spaces. And when we talk about imitation from pixels, there's usually no domain gap, or the domain gap is particularly limited. For the few approaches that do manage to do imitation learning in pixel space from a larger domain gap, as you can see, for example, here, what happens is that these are model-based approaches. So there's a vision model that extracts, let's say here, a human pose, or here a body pose, and then they imitate these trajectories in simulation. But this turns the problem from pixel space imitation to feature space imitation. And our project tried to do specific imitation from both pixel space and also with very large domain gaps, both in terms of embodiment, but also the reality gap as well. So our problem is imitation of third-person demonstration with different embodiments that are unseen during training, and demonstrations that are unseen during training, solely from pixel observations and with large visual domain gaps potentially. We start from a demonstrator providing a sequence, a behavior, and from that behavior, we slowly track frames that are embedded in a manipulator-independent representation space. And the way this happens is the next goal observation is sampled from the demonstration, and an imitating agent is trying to reach that goal. So essentially, this is a tracking problem, is tracking the trajectory from a different embodiment and potentially from a different domain. Our solution to this problem is doing imitation via reinforcement learning. So we learn to follow a given trajectory in our simulated environment. And we do that with an off-policy reinforcement learning algorithm. In our work, we used maximum a posteriori policy optimization, or MPO, where our MPO agent was conditioned on the current observation of the imitating agent and the next goal that is sampled from the demonstration. And what our agent would then output would be the action to take that would get the agent closer to that goal. And in order to train this agent, we use the tracking reward, which is defined as the negative exponential distance between the observations and the goals in a learned embedding space. And this means that the current observation and the goal should be close enough in this embedding space to give a reward of 1. Otherwise, a reward of 0 is given for that frame. So we call this embedding space the manipulator independent representation space, or MIR for short. And the most important part of visual imitation by trajectory tracking is to have a high-level feature space that can match demonstrator and agent observations. For this, we reckon there are 3 desired characteristics for such an observation space. First, it's cross-domain alignment. Observations that are semantically similar in two domains should map to the same representation. Temporal smoothness, temporally neighboring frames, regardless of their domain, should map to the same representation. And finally, being actionable, which means that the representations that we learn need to be suitable for reinforcement learning. And I will now go through how we dealt with each of these characteristics, or desired characteristics, in a bit more detail. For cross-domain alignment, what we did is we leveraged simulation and domain randomization by augmenting simulation in 3 different ways and providing aligned trajectories that way. So we start from our domain randomized environments, which are obtained by starting from a canonical environment and randomly changing object textures and colors, light intensity, ambient colors, and camera poses, which were also slightly perturbed. And then we are also able to get a variation of our environment by not rendering our manipulator effectively. So we have this effect of objects kind of moving by themselves. So we see the effect of the arm, but not the arm. We have a version. We also have a version of the environment where we are also doing domain randomization, but only for the manipulator. And we obtained paired trajectories, aligned trajectories, by combining domain randomized with arm invisible trajectories, and domain randomized with arm randomized trajectories, and that creates a data set of trajectories that we then use for our representation learning. And I should note that this data set was collected in simulation with stacking agents that were pre-trained to stack one object on top of the other, using the feature space that is available in simulation. So with this collected data, we are now able to learn the manipulator independent representation space that can align these paired domains. And one key property of this representation space that we want to have, as I mentioned earlier, is temporal smoothness. And in order to do that, we build upon time contrastive networks known as TCN, which is usually applied under kind of like a multi-view scenario. What TCN does is that it enforces higher similarity between temporally aligned observation pairs compared to kind of any other pairs selected within a single view sequence. However, TCN penalizes misaligned pairs equally. So, for example, these two misaligned pairs are penalized equally when in practice this pair is temporally closer observations should be more acceptable than this pair. And this is the change that we have made to TCN to obtain a more temporally smooth representation. So this multi-view setup now becomes a multi-domain setup in our case, and the negative pairs are now weighted by a temporally smooth distribution, so that temporally nearby observations are penalized less than temporally further observations. Finally, we wanted to make our representations also more RL friendly, more suitable for reinforcement learning training, since that is what we used for our trajectory tracking. So in order to do that, we added an additional auxiliary loss for training goal condition policies in a cross-domain manner. What that means is that given a pair of aligned trajectories, we first select a frame from one domain as our current observation and a future frame from the other domain, and we train our representations in a supervised manner to regress the action that takes the current frame to the next frame. So by doing that, we are able to encode actions while learning the representation, and this is an effective representation as the observation and goal embeddings share the same space. To recap, and give you a full picture of the framework for obtaining our manipulator independent representations, we learn a high-level feature space that can match demonstrator and imitating agent observations. And this space has three main characteristics: cross-domain alignment, temporal smoothness, and reinforcement learning suitability. We are able to obtain this by using different forms of randomization, creating paired trajectories, training our MIR encoder with these trajectories, and a linear combination of temporally smoothness loss, TSCN, and a cross-domain goal condition policy loss for making the representations amenable to RL training. Okay, so time for some results now. I'm gonna immediately show how we're able to track a demonstration by a human hand. So here on the top right, I'm showing the sampled goals from a trajectory that was demonstrated by somebody in the lab, and we have two cameras for our observation. So it's a front left and a front right camera. And similarly for our imitating agent observations, we show how we are able to reach goals, and then new goals are fetched, and then our agent proceeds to reach those goals as well. And here it's the same agent solving the same trajectory, but with from a moving camera point of view. Before I show more qualitative results, I want to briefly talk about how we evaluated our method quantitatively. And because the tracking reward is something that is not very trivial to interpret, we chose a single type of behavior to imitate. In particular, we chose stacking for a number of reasons. First of all, stacking provides comparable complexity in the different environments that we have. It's a quite challenging task that involves multi-object interaction and rich contact dynamics, especially with the geometric objects that we have chosen. And most importantly, it allows us to have a shape reward that can tracking progress along the ways that is specific to stacking. So our stacking reward in simulation can serve as an evaluation metric that tells us when an imitation has reached an object, has lifted an object, and has stacked an object on top of another one. And that way we can quantitatively understand, summarize rather, an imitation attempt without having to look at the video of imitation. And that's pretty important for the kind of evaluations that we have done. For our evaluations, we used 5 demonstration domains. And so we used the invisible arm that I've talked about earlier, the 3-finger Jaco hand. We used the real equivalent of our imitating agent. And then we used 2 settings where somebody in the lab used either the hand or pickup stick to manipulate the objects. And we used 10 demonstrations per domain, and our evaluations included 100 trials per episode, as there is some stochasticity in our environment. So that totaled to 5,000 evaluations for each of the methods that we compared in the paper, and on which I will talk about in the next slide. For our comparisons with other methods, we used baselines from prior work that does feature tracking with small domain gap, and the baselines that we used were temporal distance classification, or TDC, simple goal condition policies, time contrastive networks, TCN, and cross-model distance classification, or CMC. And finally, we have our method, MIR, which stands for manipulator independent representations. Here I'm showing lifting success and stacking success. Lifting success, since all the demonstrations are successful stacking trajectory, lifting success amounts to roughly being able to imitate half a trajectory, and stacking success amounts to being able to imitate the entire trajectory. So what we see here is that all methods seem to be able to achieve some reasonable performance in imitating the lifting portion of the trajectories. However, our method was able to do quite a lot better. And when it comes to actually imitating the entire trajectory, so reaching the full kind of stacking performance, then we see that most of the other representations were not able to be used by the RL agent to imitate those trajectories. However, that is with the exception of the CMC baseline and our method, which performed almost twice or more than twice as well as the CMC baseline. We also evaluated how important these different components to our loss were, and we start from the TCN baseline and progressively add these components. So if you recall, for temporal smoothness, we tweaked TCN to make TCNs more temporally smooth, and that gave us a boost in performance both for lifting and stacking. And then finally, by making these representations, encouraging these representations to be more actionable, we were able to get our final performance. And time for some more videos. So here I am showing demonstrations by a Jaco hand at the top, and our imitating agent is tracking that demonstration on the bottom here. Here I'm showing the equivalent real-world setup. So there's a demonstration in the real world, and again, our imitating agent is tracking it at the bottom here. And finally, I'm showing also how we're able to track a demonstration by somebody in the lab using a pickup stick to manipulate these objects. We also looked into trajectories that were not, or behaviors that were not included in the training trajectories, and the trajectories used for training the representations. And in this case, we have stacking followed by unstacking. And this is a demonstration by a Jaco hand, and we're able to imitate that with our imitating agent and our robotic gripper. And similarly, we're also able to do that when the hand is not rendered. And for some failure cases, there were cases like this where, although we did track the trajectory, the gripper was not released. So that doesn't count as a success, that counts as a failure. And there were other cases where our demonstrations had some heavy occlusion on one of the cameras, and our agent was not able to deal with that. So as a conclusion, what I've talked about today is our work on making third-person imitation with reinforcement learning work for cross-embodiment scenarios from pixel space and with large domain gaps. And we discussed what was important for creating representations, manipulator-independent representations that help for a cross-embodiment third-person imitation. And those were cross-domain alignment, temporal smoothness, and reinforcement learning suitability. And if you enjoyed this and you would like to learn more, please visit our website where we have also a link to our paper, or reach out to Yuxian, Yusuf, or myself for any questions you may have. Thank you very much.
All right. Well, thank you, everyone, for joining us today. Next up, we have Sanja Fidler of NVIDIA, who will be talking to us today about neural simulation.
Thanks, Anthony. And thanks for inviting me to this exciting workshop. Let me just try to share my screen here. All right. All right, you guys see this, right? Yeah, I'll just start. So today I'll talk about neural simulation, particularly some aspects that are perhaps the most relevant for this embodied workshop. All right, so at NVIDIA, the vision for the future is 3D, right? So the vision is that anything that is built will be visualized, anything that moves will someday be autonomous, and then anything autonomous will be simulated, right? Which means there is really need to power large-scale simulation that is both physically accurate and can handle really complex virtual worlds. So towards this, NVIDIA has been building this real-time visualization collaboration simulation platform called NVIDIA Omniverse that has been released. So I really invite all of you to check it out. And it essentially connects all these different 3D modeling tools that are already available. You know, Blender, Maya, Unreal Engine, anything can be plugged into Omniverse, and the scenes that you're editing in this original 3D software can be visualized and simulated inside Omniverse. Another really cool aspect of Omniverse is that it allows you to very easily plug in new tech, be it a new rendering algorithm, algorithm, some faster physics, or any AI algorithm that you may develop. And the command is just like a Python interface that you can plug in, and very quickly you can have a demo on this great visualization platform. In fact, a lot of the work that's coming out of my NVIDIA lab is actually demoed in this way in Omniverse. So you can imagine that this kind of visualization platform can power all sorts of downstream applications, from architecture, entertainment, like film. But one very important domain, which I'm going to talk a little bit about today, is driving simulation, and generally simulation for robotics. Right, we know that for safety critical applications such as robotics or driving in particular, you need to have simulation. You need to test your vehicle against all sorts of different challenging scenarios before you can have some hope of validating that this is actually gonna work in the real world. Right, and simulation is great. It gives you all the control that you want in terms of the kind of maps you want to drive in, how many vehicles you're going to put on the road, about their speeds, dynamics, weather, and so on. So this DriveSim, the latest update, was revealed a month ago, I think, by Jensen and GTC, and I think it's really just kind of a work of technology and art. So everything is rendered real time, photorealistic, so ray traced. Physics is all computed real time, all the lights, dynamic lights, everything is real time. So for the ego algorithm that's running on this little car over here, or driving in simulation or driving in the real world should be the same, or at least in terms of the sensor data coming in, it should be the same speed. And NVIDIA has been really kind of honing in on simulating perception as well, right? Because you want to simulate the entire stack, both perception and then planning, so end-to-end simulation. Awesome. So Omniverse is being the main effort is being run by my manager, actually. So we are very motivated to create research that is going to kind of power some of this content creation for Omniverse, or driving simulation as being one of the domains. So we've been working on all sorts of different things, from synthesizing worlds, synthesizing layouts of objects that you can place in these worlds, scalable synthesis of assets or reconstruction of assets from all sorts of different modalities, AR, VR applications, and then some sort of a more artistic content creation helper tools like stylization. And of course, there is a static component of content creation, so how the scenes look like, but there is also the dynamic component, which means that we need to be able to simulate behaviors, traffic models, simulate pedestrians and other dynamic participants of the scenes, and also animate, for example, humans in realistic ways. A lot of the research that we're doing in 3D deep learning has, some utility functions that you can abstract, and we have been releasing all that through this Kowlin SDK, which also has a plugin into Omniverse where you can visualize your research results. So please check it out. All right. So today, let's talk about it. I'm gonna talk about two different projects that I felt are maybe perhaps the most relevant for this workshop on embodied AI. And the first topic I wanted to mention is on traffic simulation, right? Which means that, yes, I have this wonderful simulator that looks, super photorealistic, but one of the really hard challenges to solve is simulating how the vehicles, and not just vehicles, pedestrians or anything that moves, basically, how they actually move. And this, we've been working for this for some time now, and it turns out a very, very challenging problem, right? So what do you need to solve? These traffic models need to be realistic. So they shouldn't be like a robot. They should be like, humans, should behave like humans. They need to be reactive. So if my ego vehicle is making an action, then everyone should be reacting in realistic ways to this action. It needs to be controllable, because I want to specify the exact scenario I want to test in my vehicle in, which means that I want to place certain behaviors on other vehicles, and I'm expecting them to actually behave that way. And of course, it needs to be diverse, right? I don't want each other vehicle be perfect in some definition of perfect. It needs to be human-like, which means aggressive, cautious, distracted, all that needs to be captured by these traffic models. And of course, it needs to be rich enough. So it needs to cover edge cases, right? So if I want to simulate scissor overtaking, cutting into a lane, I should be able to do that. Okay, so my talk today is not really going to answer all this. I think this is a really tough problem, and I'm really inviting the audience to work on this. But hopefully, it's gonna unveil some questions at least. So how have people been kind of approaching this problem, right? So maybe the most common one has been used in games, which is some sort of behavior tree, some game logic that governs how all the behaviors of the vehicles are created, which means that it's very scripted. It's perhaps less human-like, right? So someone has really kind of had to create how all these vehicles are going to behave in different situations, which means that it's hard to resimulate certain scenarios, right? If I encounter some intervention, I want to resimulate it, I now need to go and manually kind of script all these different behaviors, right? In self-driving, people have been mainly tackling this from an imitation learning perspective, where I have recorded tons of real data, and I want to kind of mimic those trajectories that cars or other participants make, right? So this has some advantages, for sure, because this is going to be more human-like, but it also has some problems. So here was kind of us trying to do this a year ago for the CVPR paper. This is just like purely imitation learning policies that are rolling out on new scenes maps, and that they have also been trained on new scenes. So if you kind of look long enough, you're going to see that longer rollouts always kind of lead into problems. There's either collisions, there's some sort of illegal maneuvers that these vehicles tend to take. And at least for new scenes, because not all the state has been annotated, so you don't know the state of traffic signs and so on, that kind of causality hasn't been learned by these imitation learn policies. So it's a good step, but it's definitely not something amazing we can just directly use in a driving simulator. And of course, the question is, what do I do, right? So yes, I can post-process, I can maybe avoid some of those collisions, I can maybe make some sort of imitation learning with RL, but then as soon as I have RL, how do I encode reward functions? How do I encode traffic rules that all these vehicles need to follow? There's just so many of them, right? And it just becomes a very daunting problem. So in this project, we kind of try to take a little bit of a different perspective on kind of driving. And we're gonna investigate social driving. So we're gonna formulate driving as an optimization problem in a multi-agent RL framework. And in particular, we're gonna try to design, the most simple reward functions or objectives that these agents should be optimizing as a whole. In particular, we're going to train these agents to travel from A to B, so from start to end, as quickly as possible without colliding. Okay, so you can think of this as the basic function that probably every driver is optimizing for. And if you think of this old era where cars just started out, very few vehicles were on the road, maybe this was actually the objective everyone was optimizing. And then as there were more and more vehicles, more and more roads and so on, and then traffic rules kind of emerged as a way to prevent accidents. So we wanna basically analyze the emergence of those rules. So what happens if I have this very simple objective function, but I add many different agents, which is basically how the roads look like today. And what if I purposely add noise to perception? All right, so arguably human eyes are not perfect, particularly not at night in different weather. So, how does that affect the learned behaviors of this just very simple objective function? And we're gonna try to analyze, the behaviors that emerge in this environment. All right, so this is just a very simple setup. So moral multi-agent reinforcement learning. So how we're formulating this is there's a single policy that's going to be shared by all agents, here denoted by pi. The observation is going to be kind of like a LiDAR, a mini LiDAR, where there's like a equiangular beams coming out of this agent. We're limiting the distance that the agent sees by 50 meters, and we're going to be adding some noise along this race, kind of mimicking noise in perception. Right, so each agent is going to see just like some local environment from where it is. Then the reward for the agent, like we discussed before, is going to be very simple, where you have this expectation over the entire trajectory. So this is agent I. So it's a discounted reward where A here is the action that I'm taking in time step T, and S is the state that I'm in. Okay, and I want to basically define this reward this way, the usual way. And at each time step T, kind of going back to that, the data that we talked about before, I'm defining the reward as, reaching the destination at time step T, minus, I'm giving like the same kind of penalty, colliding for the first time with an obstacle at time step T, and then distance to the goal. So I want to get there as fast as possible, but somehow normalize distance to the goal. And we added this kind of regularization loss here with ACE, kind of saying that this drive has to be smooth, so the actions have to be similar. And the multi-agent reward here is just a sum across all agents, right? So we're kind of optimizing this joint utilitarian reward. And we want to find the policy, the shared policy that maximizes this objective. And we're going to use the PPO algorithm for this. So there is no real technical novelty here in terms of how we're kind of approaching this problem. What really kind of we want to investigate here is if we define driving this way, what kind of behavior emerges. So let's look at what actually happens. So here we had a very simple environment, which is basically just a four-way intersection. And the agents start on one side and their goal destination is on the other side of the road. And we're going to have different number of agents starting from different road sleeves. And here we're just kind of analyzing the emergent behaviors that happen after all the training. So the colors here are going to represent fraction of agents seeing the green signal. So we're going to place, like a traffic light on each intersection side over here, where there is no meaning of red light. Is just a token that the agent sees, which is like on or off the token. And basically, we're going to try to analyze whether this agent, as a result of this optimization, start to pay attention to that traffic light, just because that helps them optimize their very simple objective. Okay, so basically, reading this legend, the most green I am, the most I'm paying attention to the traffic light. So let's try to read this plot here. So here in the top left, we have only a single agent. And obviously, a single agent doesn't need to pay attention to the traffic light. So there's basically like, random chance of it paying attention to the traffic light. But here, as I'm increasing the number of agents, they're trying to pay attention more and more to the traffic light. So here in the middle center, so here in the intersection, if this is very green, that means that all these agents actually only crossed over if there was a green light. So they started paying attention to the green light. So basically, the more agent I have, the more they pay attention to the traffic sign. And kind of a similar situation happens here. So here I have 4 agents when I'm adding LiDAR noise. From no LiDAR noise, you have these plots are basically matching. They're still paying attention to traffic lights. The more blind I'm making them, so 100% LiDAR noise basically means they're random, they're blind. The more they're just paying attention to traffic lights, which is kind of great, right? Because basically a rule of using a traffic light is emerging as a result of this optimization problem. Here is just showing some rollouts of these learned behaviors. And again, here I have these 4 agents with 0 LiDAR noise. And if you observe this long enough, you see that sometimes they don't pay attention to traffic lights. And the more agents there are, the more they're actually going to obey and stop at the traffic light. Cool. And we have even taken that policy that was trained on like this very simple environments and rolling out on this a little bit more complicated new scenes patch. And it turns out that it kind of works. So it was also started paying attention to traffic lights here without ever us specifying the reward function associated with it. Cool. All right, so the next one, of course, is going to be following lanes, right? We know that rows have lanes. So the question is, does this also emerge in this very simple environment? So if you look at here with 4 agents, I don't think there was any LiDAR noise over here. You can see that they kind of have this, not lane-like behavior, right? So it starts somewhere here, but then it crosses over and goes on the other side, just because there is no other agent on the other side that would kind of obscure their path. Here on the right, as I'm increasing the number of agents, I think here we have over 8 agents. If you look at this carefully, you can actually see that they're starting to really pay attention to lanes. So here is maybe a better visualization. So this is just aggregating many, many different rollouts and looking at their trajectories. So you can really see that, without specifying any reward for lanes, they learn how to follow lanes, just because that optimizes the joint reward, which I thought was kind of cool. Here is another fun experiment. This is the emergence of fast lanes. So here we're making some agents have a higher possible max velocity, and some agents are going to be slower. So here darker purple, I guess, denotes cars that can be faster. And you can see that, again, lanes emerge. So they all start on a lane. Lanes, again, emerge. And the faster cars tend to go here in the bottom. And they cluster together, and the slower are in the top. And again, they cluster together, which is kind of similar to how highways are built, right? There's always like a fast lane. This is perhaps less visible over here, but we try to scale this to a little bit more complicated environment. So this is taking patches from new scenes, which is a real driving data set, and giving some traffic lights, and again, optimizing the same reward function. And what happens is that these agents start paying attention to the safety distance, right? Because as you're increasing the number of agents, if they don't pay attention to safety distance to the car just in front of them, they're going to start colliding. And another kind of aspect that we notice is there's a slight notion of right of way. So if I'm the first one to enter the intersection, you're also likely to exit it first, which was really kind of cool to see. So this plot might not be the best to visualize this, but there is somehow a plot that maybe shows this a little bit more. So here on the x-axis, I have distance to the car in front of me. On the y-axis, there's like a speed matching that distance, right? So if I'm going at a particular distance, what should be kind of my speed match distance to not collide with the car in front of me? So safe stopping so that I match that velocity of the car just in front of me. So basically, this means that here, this diagonal over here, and this green triangle. So if the point is in this green triangle, I have a safe distance. Okay. So on the right side is this RL train agents. On the left side is the real agents. So these are humans, and we did the analysis on just new scenes trajectories. So what kind of you can see over here is that even humans don't always have perfect safety distance. So they're kind of assuming that the car in front of them is not gonna just quickly brake. In the RL environment, the agent also pay attention to safety distance, but maybe less so. There's more violations over here. I'm not exactly sure why. Probably we should just add a lot more agents. Or maybe optimization needs to be done somehow better. But this was kind of cool. So this was just our first step on this direction of just how far can you go by training these RL agents with just very simple objectives without needing to engineer all those reward functions. So the next step is really kind of scaling this up to a lot more agents, a lot more complicated environments, and just see where we land. And there are certain rules that I can see how it's going to be hard to emerge, like speed limits, and maybe we need some rewards for that. But I think this is actually a pretty promising direction over here. All this project that you see here is released. So the environments, the code, everything is released. So I'm really inviting you to work on this and play with this environment, particularly if you're an expert on RL. Cool. So I'm going to switch gear a little bit here. So this was really about, how do I model those traffic in like a graphics environment. Here we're going to try to train a neural simulator. We're going to train everything from scratch from pixels directly, right? In driving, I'm collecting so much data on the road. And once my platform is basically built, it's easy to collect data. I just go out and record. Right. So the question really here is going to be, can I build a model of the environment directly from pixels, right? Kind of sidestep all that development of the game engines. All right. So we're calling this neural simulation. And our first take on this was this game GAN, where the idea was that can we, like in game engines, you basically have an action that the user can make, and then there's the game engine that's going to paint the frame as a reaction to that action, right? And our question was, can we completely replace that game engine or with a neural net? So a neural network basically mimicking what's happening inside that game engine. Okay, so we're imagining this game GAN over here receiving an action from the user. So there's still going to be a player in the loop that's going to play the game, but the neural network is going to be painting the frames. And we're going to learn how to paint these frames by basically looking at trajectory samples from real games. Okay, so you're going to say, why do I even need to do that? I mean, there is already a game engine, right? And this is the first toy task that we should at least be testing against. I think where this is really going to be powerful is where you don't have access to the game engine, the real world, right? If you guys have watched the Matrix, maybe there's an existence of a Matrix, and we're hoping that this game GAN is going to recover that Matrix. All right, so the first design for this model was very simple. It was basically this LSTM that would receive an action at each time step, some random noise, and the previous generated image. It would process, produce a latent state, then throw this into some synthesis network that would produce the next frame. And we also had this like nice memory module, which you can think of as some sort of a map of the environment that the neural network is able to build as it's exploring the environment. So, kind of building a mental model of the maze or the map, basically reading and writing in this additional memory, spatial memory structure. All right, how we were training this, I mean, there is not a big rocket science. So, there's a single frame discriminator trying to make sure this image is looking realistic. Temporal discriminator is looking at a bunch of frames, making sure that the trajectory of this frame is realistic. And in order to actually pay attention to the action, we have this action condition discriminator, which takes 2 consecutive frames and tries to infer back the action, meaning that I have to actually be generating images in a way to respect this action. Okay, so here is one result in this like Ego Pac-Man environment. And all this that we're seeing here, so there is a sync with the author, the main author, and this is playing this game, but the frames here is painted by game GAN. Okay, so this was pretty cool. And I wanted to show that this is not an easy task. It seems so easy. Okay, fine, there is this Pac-Man painted. We started with stuff that looked like much worse. So here is some results from the early development of this game GAN. And so here is on the left. And one thing to notice is it's extremely hard to generate a ghost. Everything looked a little bit more blurry and it was hard to produce the ghost. So, we were really chasing ghosts for quite some time in this project. So we kind of narrowed down the scope at the time, make a much smaller environment and debug here. So here was like some intermediate result. So here the ghosts are appearing. It's much easier to paint them. I can always see them. But it was so hard for this Pac-Man to learn the rules of the game. Like it would not die. Did not learn a concept that if it catches this red ghost, it would die. Nothing really happened. So making Pac-Man die was the next next part of the development process. But we did quite well. So we actually released this model for the exact 40th anniversary of Pac-Man, and people kind of really love that. So here is this promo video, and it's also showing like the latest results of Gingan. I'll just play this. So here you can see, you could have seen that, it kind of learned how to paint the ghost color, change the ghost color, eat Pac-Man, and then it would disappear. And the food was disappearing as the Pac-Man was traveling around. Oops. So this is a fun video that I saw someone post 2 days ago. And we basically released the source code, and someone just trained this game gun on the Grand Theft Auto. Okay, and I'm just gonna play their video here because I thought it's quite hilarious.
Welcome everyone, Theft Auto. What you see here is me playing inside of a neural network's environment. This neural network was trained by watching a bot play Grand Theft Auto 5 on this particular stretch of highway, learning how to generate new frames from previous frames and player input. So every pixel you see here is generated from a neural network while I play. While generating the visuals or just improving them is interesting too, and there has been some interesting work lately with neural networks improving the visuals with Grand Theft Auto 5 in particular in attempts to make it look more photorealistic. This is something much more than that. The neural network in this case is the entire game. It's handling what happens when you press a key.
This goes for like 17 minutes. I'm not gonna play. In 2 days, it got 140,000 views and a lot of positive comments. So I was super excited. And of course, I was also a little bit, feeling tiny because this quality is actually not as good as one would hope for. But here is a good thing for us. We have been actually thinking about this use case ever since we published Gingan. And really we wanted to scale that particular project to more complicated environment. Grand Theft Auto is one example, but basically for driving. And here we're basically trying to train this new model called DriveGAN on the Carla simulator. And even more complicated Carla simulators here with many different objects also present in the scene. And again, the user is controlling the wheel here, the speed, and this is being synthesized. Not perfect, but it seems like it's doing a good job. So let me tell you a little bit about what we've done here. So the model is similar to as before. So there's still going to be some dynamic engine that takes in an image and an action, but we're going to try to scale this entire pipeline to this more advanced generator. In particular, we want to take advantage of StyleGAN as maybe the state-of-the-art image generator. Okay, so instead of here our custom-based network that we had before, we maybe want to plug this like a StyleGAN-like architecture over here. And we felt that train this entire pipeline would be a little bit hard on just a lot of videos. So we're pre-training this part here with just like a simple, like a VAE GAN approach. So we're going to have an image that's going to train this encoder over here. It's going to produce 2 different codes. One is going to be a content code, so information about the environment, and one is going to be a theme code that controls weather and maybe night, day, and so on. And like VAE style here, so it's producing some distribution. And then we're taking that latent code and we're decoding here with StyleGAN-like architecture into an image. So this is like VAE GAN, so it has the GAN-like, so discriminator objective from StyleGAN, but then it also borrows the loss functions from VAEs. Okay, and so we're basically pre-training this, which means that we have pre-trained this green part and the red part over here. And when we're going to video, the real challenge is basically training this dynamics engine, but we're basically training the dynamics in the latent space, which we felt would maybe be easier. Okay, so, and there's a little bit of like key design choices here that I'm gonna explain next. So here is just us kind of trying to train this VAE StyleGAN on a single image. So here is what I'm showing on the right is the original image. And here is this VIE that's producing the latent code, and then we're decoding it back to the image. So, I'm showing here what's the best reconstruction we can get by training this particular model over here. And this is using just this plain Stallion architecture, which means that this content code here is just 1D. And it's kind of good, but at the same time, if you look at the details, it's not good. Like here, for example, for this car, Stallion has pasted a completely different car here. And some of these other cars are all gone in the reconstruction. The buildings are kind of weird and so on. So what the first real modification to Stallion we've done is make this content code here spatial. So instead of just making it 1D, here is going to be a spatial content code. And that improves things a lot. It doesn't perfectly solve them, but it improves things a lot. So you can see now these other vehicles starting to appear, and there's maybe more consistency in the reconstruction. And this is pretty great because now what I can also do is have an image and an encoder that produces this latent code, which maybe we're going to use this later for other tasks that I'm going to talk about. So here is just the same result, but for real driving scenes. So here are the input images, here are these reconstructions, and it's not perfect, but it's kind of trying to do a good job at least understanding where the objects should be and what the semantic of the image is. Here is one more example. Here I'm showing, what different parts of this game can control. So here on the x-axis, we are randomizing the theme vector. So you can see that, at least here in the last row, we're basically controlling the weather or night and day by basically sampling a different theme vector. And modifying the latent code is basically allowing you to click on some spatial block and plug and replace a different latent code in that block only, which allows you to either delete something or maybe place another asset in a particular location. So let me just play this video over here that maybe is a nice visualization of this. And let me know where I need to stop. I think I should probably finish my talk anytime. So here you can control different themes and you can paint different objects. So here I'm just maybe, and then we can stop here if the timer is run out, and just a longer rollout out of this drive game.
Well, I want to thank you then for your presentation. I think that there's going to be a queue. I have many questions I might want to ask, but I think we're going to wait for the formal Q&A so that we'll have the chance for everyone to talk together. So thank you, Sonia. Next, we have Chelsea Finn, who will be speaking to us about embodied AI and robotics.
Great, thank you. Hi, everyone. I'm Chelsea. I'm an assistant professor at Stanford, and I'll be talking about broad data for broad robot generalization. And Sonia's talk is actually a great, there's a great transition because a lot of what I'll be talking about does have to do with generative models of predicting the future, but more focused on robotic manipulation than for driving. So to start off, I've spent a lot of my prior work working on reinforcement learning for robotics, and we could get a robot to learn pretty impressive skills like using the spatula to lift an object. Also a number of other labs have kind of applied these same sorts of techniques to get robots to hit hockey pucks into goals, open a door, throw an object to hit a target, and so forth. And you might look at these and think that we've kind of solved the problem of learning these kinds of skills on real robots. However, we have a bit of a problem here, which is that the robot isn't learning generally how to use spatulas and how to open doors and so forth. It's learning how to use, for example, this spatula with this object, with this background in this environment. And if you wanted the robot to be able to handle a different spatula, for example, or a different environment, it wouldn't be able to generalize to those scenarios because its entire world is this one environment in which it learned the skill. And so analogously, if you were to think about what this would be like for a human, it would be like on day one, giving the infant a spatula and saying, your job is to figure out how to lift this object with this spatula. And so from this perspective, it seems like we probably need to rethink our approach if we want robots to be able to generally understand their world and perform in a wide variety of environments. Now, one way of looking at this problem would be from this kind of machine learning standpoint, where we're essentially training on a lab environment and hoping that we'll be able to get generalization to the real world. And so from this perspective, one natural solution to this problem would be to, instead of training on a lab environment, trying to broaden the distribution in which we are training robots on. Essentially, if we want robots to generalize broadly, we should train them with equally broad data. And this is a recipe that's been super successful repeatedly in machine learning, from computer vision to natural language processing. And it's also reflective of the fact that people accumulate and learn from broad experiences. And so this suggests that perhaps we should figure out how we can train robots, not just on one lab environment, but with much broader data. And so the corollary to this statement is that we need to figure out how we can develop algorithms that can learn from such scalable data sources. And so, for example, if we're developing online reinforcement learning algorithms that need to learn from online experience and collect data for every single new experiment that they do, that may not be as scalable as if, for example, they could leverage an offline data set of their previous experience. Okay, so with this motivation in mind, one natural question that we could ask is, can we use broad computer vision data sets? For example, can we use off-the-shelf object detection systems? It turns out if you take an off-the-shelf object detection system and apply it to a robot like this, you get images that look like this. And these are exactly the kinds of images that, that off-the-shelf models tend to work actually quite poorly on. We've actually tried to run them on these kinds of images, and they generally don't work very well. There's too much domain shift between the kinds of images that people take on the internet and these images. And also many of the objects that you see here might be out of set compared to the objects in kind of a closed set detection system. Another option is, well, we have ImageNet, we have good features, can we fine tune features from ImageNet? And we've also tried this for robotics and found that compared to learning from scratch, we often see pretty minimal gains from pre-training on ImageNet. I don't know exactly what this is, but kind of my main hypothesis for why this is that in embodied, whenever you're learning with kind of an embodied agent with a robot, you need both a good representation of perception as well as a representation of action. And if you only have a representation of perception, maybe that isn't good enough. Maybe fine tuning from that isn't good enough for solving, for being able to quickly learn a new task. Okay, so what I'd like to talk about today with this motivation is first, how we can acquire broad and diverse data sets for robots so that we could allow robots to generalize much more broadly. And second, how can algorithms then try to learn from those offline scalable data sources? So we'll be talking about data and algorithms. So first, let's talk about the data side of things. And on the algorithm side, we'll be looking at both robot data and human data. Okay, so the first thing that we could consider doing when collecting data with a robot is to collect data with random actions. And if you kind of lightly script a policy that's somewhat randomized, you get data that looks like this. And you can actually collect a ton of data this way. You can run robots overnight and get kind of millions of frames. And the data actually is surprisingly rich. And we actually use this data collection technique to really scale and accumulate a broad data set, actually not just within a single lab, but across multiple different institutions. And so we did this across, we were calling this the RoboNet data set, potentially somewhat shamelessly. And we collected this data across 7 different robot platforms. It contains 15 million video frames, 113 camera viewpoints, and it was collected across 4 different institutions. So it actually has a lot of diversity, not just in the robot platform, but in the background scenarios, the objects, and so forth. And it's also something that's open for contributions. It's something that we want to be able to grow in the future. So this is, I think, kind of one way that we could consider scaling data collection. However, random actions don't lead to as sophisticated of behaviors that we might want a robot to be able to do. And so kind of what I'd like to talk about in this first part of the talk is if we can collect such broad data sets, but containing more sophisticated interactions. So one approach for doing this would be to provide demonstrations by essentially having a human guide the robot through certain motions, and you can get, as you see here, interactions that look a lot more sophisticated, a lot more interesting. For example, picking up a tool and using that tool to push objects. So this leads to more useful data probably than random data, but you can't get a lot of it because you require a human to be there for the entire data collection process. It's a very manual process. And so this isn't something that is going to scale quite as readily as autonomous data collection. Now, another potential data source would be videos of humans. For example, here's the Epic Kitchens data set, which has like tons of really rich and interesting interactions of humans performing different behaviors. And so this is lots of really interesting data, but it's of course pretty hard for a robot to use this because you don't have the actions. There's some domain shift between what a human's arm looks like and a robot arm, and maybe the degrees of freedom of humans and robots are different. I'll talk a bit more later in this talk about how we can leverage this data. I do think it's a promising data source, but it's not something that robots can necessarily use directly. Okay, so how can we like scalably collect really useful robot data? And this isn't just a matter of an engineering challenge. I think this is actually also a research challenge. And we started looking into this in a research project that I'll talk about now. So the first thing that we tried was novelty seeking methods. There's essentially a lot of literature in reinforcement learning on trying to develop methods that can explore their environment and seek out novel situations. And in particular, we positioned this robot in front of this IKEA desk. And our ultimate goal was to get the robot to interact with this drawer. We wanted it to learn how to open the drawer and close the drawer. But ultimately, we would want it to do lots of different things in this environment. And so we took a very recent exploration method that has worked very well in simulation environments and kind of video game type environments as well. And what we found is the kind of interaction that the robot is performing is not actually successfully seeking out all the kinds of things that you might want the robot to do. And in particular, even just like moving its arm in different ways led to the kind of novelty that this algorithm was seeking. And as a result, it never actually, or it very rarely actually reached for this drawer handle right here. So unfortunately, this isn't yet a viable approach, although I hope that we can eventually develop novelty seeking methods that can explore that. And so at this point, we asked the question of whether a person could help the robot and help show the robot what are interesting things to do such that it could explore in a more targeted way. And critically, unlike demonstration data collection, where the human has to be in the loop for the entirety of data collection, we want to have a scenario where a user can help at the very beginning and then have the robot explore and collect data autonomously for the rest of data collection. And so we want to be able to have a user help the robot without being in the loop of data collection. So the way that we approach this problem is we first had the person show examples of interesting states. So for example, if we wanted to have the robot explore this drawer environment, we would show it examples of reaching towards the drawer and opening the drawer and so forth. And this kind of collection of interesting states would just take a person around a few minutes to do. And then we would learn a classifier that can classify between these interesting states and the data that the robot is exploring. So it's just a binary classifier that classifies between these two kinds of states. And then have the policy try to explore specifically to try to find images that are classified as interesting. And that's kind of the gist of the approach. We give it interesting states, and then we try to have it find things that look more like the interesting states and less like its autonomous exploration data. And what we find is that if we give the robot just less than 3 minutes of human guidance of providing it examples of opening this drawer, and then run the robot autonomously, we then get data that looks more like this, where it is able to actually kind of target its exploration towards this drawer, for example, and kind of sort of play with the drawer in different ways, and interact with it in a much more targeted way. And we ran this kind of we were able to run this autonomous exploration overnight. And I think that in just around like 32 to 48 hours of autonomous collection without a human in the loop at all, it was able to collect data that looked like this. And so if you actually also compare the amount of episodes that it actually touches the drawer handle and moves the drawer handle, it's substantially more than this disagreement-based novelty seeking method. And then we also had experiments in the paper in simulation that showed a number of different scenarios, including interacting with objects, interacting with a variety of objects in the scene, and so forth. Okay, so the takeaway here is that a small amount of guidance can really go a long way towards this sort of data collection, especially when this guidance comes at the beginning of training before the robot autonomously collects data. And then the last thing that I'll mention here is in a follow-up paper, kind of along the lines of reusing and leveraging offline data, we actually took this data set that was collected in this previous paper, didn't modify it at all, didn't collect any additional data, and just directly reused the data set to learn how to train a policy to close the drawer. And in particular, we labeled some images as opening versus closing, trained a classifier which could serve as the reward signal, and then ran offline RL with this reward signal to train the robot to close the drawer. And this is all from image observations. And so the resulting policy that we get looks like this, where the robot learns a fairly robust policy for closing the drawer. This is showing this is a real-time video, so it's not sped up, and it's showing a 76% success rate. So this is an example of exactly what we'd like to be able to do of just having some offline data set and learning from it without having a lot of expensive online data collection. Okay, so that's on the data side. I talked about how a small amount of guidance can really go a long way. And the next step is to really try to scale up this form of data collection and collect much broader data that is both broad as well as somewhat targeted towards the kinds of interactions that we might want the robot to do rather than simply random interactions. Okay, so next I'd like to talk about the algorithm side of things. Once we have a broad and diverse data set, such as the RoboNet data set or such as broad human data, can we leverage that data and learn from those offline data sources in a way that's very useful? So first, let's talk about the robot data side of things. This was before, we haven't, I guess, yet developed a really large data set of like demonstrations or more sophisticated interactions. So we're going to be working with the RoboNet data set that has pretty diverse data in terms of robot data of many different kinds of interactions. And so we wanted to ask, what is the bottleneck for handling these kinds of data sets, and can we train models that can handle this data? And we're going to be taking an approach kind of somewhat similar to what Sonia was talking about, where we're going to try to train a video prediction model conditioned on the robot's actions to generate frames from this data set. And if we're able to train such a model, then we can actually then use that model to get behaviors that optimize some objective. And so here are examples of ground truth robot videos from the robot's perspective. And we then trained this really state-of-the-art video prediction model from Ruben Villegas from NeurIPS 2019 on this data set. And unfortunately, the predictions here don't look very good. The predictions, I mean, in some cases it looks sort of reasonable, but in general, like even the robot arm predictions aren't matching what the robot is supposed to be doing. And sometimes the robot arm predictions are extremely blurry, or it's kind of imagining other arms entering the scene. And moreover, this isn't just the predictions on the validation set. These predictions are representative of what the predictions look like on the training set. And so it's not that it isn't able to capture and generalize to these kinds of videos, it's that it can't even fit the training set in the first place. That's underfitting, which is actually somewhat rare in deep learning, general in deep learning, because typically we're used to having these huge overparameterized models that fit the data well. And this was actually a pretty large scale model. It actually filled up a single GPU, a single 24 gig GPU. And so we wanted to ask the question of how we could try to scale these dynamics models and train larger models without kind of running into these practical challenges and so forth. And one practical bottleneck that comes up is the GPU memory. Even with a small batch size, that previous model was 24 gigs. And so if we wanted to scale the model even more, we would have to do things like model parallelism and so forth, and that would actually involve a lot of complexity and also just significantly slow down training. And these models already take multiple days to train. And so when we were thinking about this problem, there's actually this old trend of training neural networks in a greedy fashion, where you train neural networks layer by layer, where you first train kind of a one-layer autoencoder, and then you train the second layer of that autoencoder to reconstruct the corresponding activations and so on and so forth. And the kind of insights of this kind of model is, first, this kind of model reduces memory costs significantly because you don't need to fit the entire model of end-to-end training, both the forward pass and the backward pass, in your GPU. And I guess the second thing that I'll mention here is, beyond memory, it also these were actually used to alleviate optimization issues. And it turns out that optimization issues also present a challenge for video prediction models because they have a tendency to kind of fit into this local optimum of just predicting the frame that you gave it. Okay, so this is work done by Bohan, and we were thinking about whether we can apply this idea of greedy training to video prediction models. And so kind of at a high level, what the model does is it first trains a one-layer video prediction model, essentially. And then it freezes this layer right here, and then trains another layer on top of it, and so on and so forth. And there's kind of a lot of details in this model, but I'll highlight a few of the high-level bits. So of course, we're training each of these modules, each of these encoders and decoders sequentially and freezing the higher layers of the network. And second, we're actually, instead of optimizing these to match the activations, we're still optimizing them with respect to reconstructing the future frames. And you might ask, well, okay, then maybe this doesn't actually reduce memory, but it does actually reduce memory because you no longer need any sort of backward pass into this part of the network right here. And that actually leads to pretty substantial memory gains and allows us to train much larger models in the same amount of memory. And then one last thing that I'll mention here is that the one thing that we found important in this architecture is to have the encoder compress the spatial dimensions throughout the depth. And the reason why this is important is that when you train these variational autoencoders, there is a prior on your variational distribution that each of the dimensions are independent. And if you have a lot of spatial dimensions and then you flatten that, you're going to have a lot of correlations between neighboring pixels, and that's going to break this assumption that that every dimension is independent. So this is the mean field approximation in variational autoencoders. Okay, so we asked a number of questions about this model, how they compare to state-of-the-art, do they lead to better downstream planning on robots, and how does this compare to end-to-end training and overfitting? And so we evaluated this model first just in terms of standard video prediction metrics, including FBD score, which looks at visual quality, and LPIPS that looks at perceptual similarity to the ground truth, as well as just a human preference. And what we find is, compared to Ruben Villegas's model, the one that I showed that was like kind of large scale models from 2019, we see a pretty significant boost in prediction quality in terms of all three of these metrics. So we see a 20 to 50% improvement across the board. Now, of course, at least I don't care that much about the video prediction metrics. I care a lot more about what this enables for robots. And so we took this model, we pre-trained it on the RoboNet dataset, and then we fine-tuned it on a small amount of data from this environment, which is actually unseen in the RoboNet dataset because we had to move the robot to a different lab location between working on RoboNet and working on this project. And we tested the model on two different kinds of tasks. One is to pick up the sponge and kind of sweep an object into the dustpan. And the second task is to sweep an object off of the plate. And so what we found is, for both of these tasks, using these larger scale models, the greedy hierarchical variational autoencoders, we're able to get a much, much higher success rate than using the model that is really struggling to fit the data, to fit RoboNet, namely. And I guess it's also worth mentioning that we also tried not pre-training on RoboNet and only training on the data that we had in this new lab environment, and that also wasn't able to perform well. Okay, and then the last thing that we looked at is how this compares to end-to-end training and whether these models are overfitting. And surprisingly, we actually found that, at least for this model architecture, end-to-end training didn't perform well at all. And it seems like the greedy training actually leads to an easier optimization problem. And then the second thing that we found is that this model still appears to be underfitting on RoboNet, because we see that the training and test loss is still roughly the same, and we don't actually see any evidence of overfitting, at least on the RoboNet dataset. For other datasets that are smaller, we do see overfitting. Okay, so essentially more research is needed to try to still combat this underfitting problem. Okay, so this is an approach for learning from really broad robot datasets and can combat this challenge of underfitting. Now, what about human data? Human data is something where we might be able to get a large number of very sophisticated interactions, potentially just from the internet. And so it's a potentially really exciting data source to use for robots. And it's the goal here that we wanted to be able to handle is actually focusing less on controlling the robot and just looking at the problem of learning a metric of task success or reward function, which is also kind of critical importance to robots, because if we don't have a reward signal or a task success metric, then we can't train the robot in the first place, and the robot won't understand whether it's being successful. And we want this metric to be able to generalize across tasks, environments, and viewpoints, unlike something that might be just trained in a single environment, which wouldn't generalize in this way. Of course, there's actually a lot of work on learning from videos of humans. I'm showing some of these works here. However, kind of the vast majority of these works typically use very narrow human data sets with a lot of close similarities with the robot data. And as a result, if you have this sort of narrow human data, you won't be able to promote the kind of generalization that I've been focusing on this talk. And so really, at least for me, one of the big benefits of using human data is this ability to leverage very broad human data in order to promote generalization. So we looked at these kind of in the wild human videos, and in particular, we looked at the something something data set, which is illustrated here. And we wanted to take these human videos and combine it with a small amount of robot data, basically the narrow robot data that we would typically get in a lab environment, and try to combine these data sources and get something that generalizes much better by nature of using these videos compared to only using the narrow robot data. And so we take these videos, the human videos as well as some narrow demonstration data, and we train for a video conditioned reward function that, conditioned on a video of a human, can acquire a reward function that lets the robot know whether it's succeeding at a task. This is during training. And then at test time, we can, in a new environment and a new task, we can use a human video, for example, of pushing this tissue box to the left, to get a video conditioned reward function for that task. And then actually execute the task and learn the task in the real world, potentially in a new environment with a new viewpoint and new lighting conditions. Okay, so this is kind of the problem setup that we're looking at. So how do we actually kind of accomplish this sort of problem? The key idea behind this work is really, really simple. We just train a model that takes as input 2 videos and outputs whether those videos are doing the same task. So for example, if we give it these 2 videos where both the robot and the human are closing a drawer, we give this a label of 1 because they're completing the same task. For these 2 tasks of moving something away versus closing something, we give this a label of 0 and train it to predict the label of 0. And likewise, for these 2 videos, we train it to output a label of 1. So it's just trying to discriminate whether or not 2 videos are performing the same task or not. And it's trained across all of the human data and the narrow robot data that we have available, which is either in simulation or in real. Okay, so we refer to this as domain agnostic video discriminator, or DVD. And we ran experiments both in simulation and in the real world. So I'll start with our simulation experiments. And in particular, we wanted to be able to test generalization to new environments where our initial environment looks like this. We want to be able to test generalization of the reward function to an environment with new colors, with a new camera viewpoint, as well as with the new arrangement of objects. And we considered 3 different tasks in this environment: closing the drawer, pushing a cup to the coffee machine, and turning the faucet to the right. So this first question is, do these human videos allow us to generalize to new environments? And so in particular, what we looked at here is we looked at the baseline methods are the ones that don't use the human data at all. They just use the robot data, which is kind of the standard approach in robot learning. And these, the success rate for each of these approaches is shown in green. And if we actually use this approach to use both the robot data and the human data, these success rates are shown in these pink colors. And we see a large boost in success rate, around actually a 20% boost in success rate on average between using only the robot data and using the human data. And the reason why we see this boost is because we are evaluating for generalization to these new environments, and we just can't generalize to these new environments if we only train on narrow robot data from one environment. And then qualitatively, what this looks like is we give it a human video that looks like this. We then use this to acquire our reward function directly, and then we run planning with a video prediction model to solve the task. And so we can solve this in the training environment, but we can also solve it in environments with new colors, with new colors and a new viewpoint, as well as new colors, new viewpoint, and new arrangement. Another example shown here is pushing this faucet to the right. We again kind of run the same process to get the reward function. And we also see that this reward function can generalize not only to the training environment, but also to these new environments where the robot can figure out how to push the faucet to the right, even under quite different environments. And then beyond environment generalization, we can also look at generalization to new tasks. And so in this case, we actually held out these tasks from the human data set and the robot data set. And so these are tasks that it had never seen before. And we see that comparing using only robot data to using human data, we see, again, a 20% improvement in task success. And then lastly, we also tested this on a real robot. And so, for example, this is actually both a new environment and new tasks. And so the robot can figure out how to close the door with the video of a human. And likewise, we give it a video of a human of pushing this tissue box to the left, and the robot can figure out how to solve the task. Okay, so to wrap up, I first talked about collecting data and how a small amount of guidance can really go a long way towards autonomously collecting diverse and interesting behavior and data, and also about how generally when we broaden the data, we can achieve broader generalization, and that videos of humans are a promising data source for robotics. And all of these, I think, are steps towards actually getting robots to generalize to a wide range of environments, but we, of course, have a long way to go. I think there's also kind of a number of exciting future and open questions. I think we've barely scratched the surface of data scalability. And more broadly, we can think about not just generalizing with broader data, but also trying to generalize beyond the data distribution. I'd like to thank my students, and I look forward to the Q&A.
All right, thank you, Chelsea. We really appreciate what is a fascinating talk. Just as one note before, and also I want to thank all of our speakers. Before we go into the Q&A, I'd like to just have a little errata for my initial intro presentation right at the beginning of the live stream. If anyone was awake to see that, SoundSpaces challenge will be airing in the interaction challenge results at 4 with the challenge team in the Q&A at 5 p.m. We had done that load balancing to try to make sure there was a good balance between the two groups, and I did not include that change in my slides. So apologies for anyone that was confused by that. But the CVPR and EAI website schedules are correct, and mine talk was not correct. Without further ado, I will hand it over to the Q&A session, and we have a lot of great speakers to hopefully answer questions. And we are, I think we have someone who's supposed to join and actually be asking the questions. But until they do, I can certainly take on that role. First off, we had a set of questions from the Slack, and I believe someone is going to be looking those questions up and handing them to me or to Eric if he joins. And so, did I hear someone?
Yeah, I'm here.
Okay, great. And I'll hand it over to Eric.
Yeah, I was just waiting on Peter to figure out video before we get going. Yep, oh, and there's Drew also. Okay, everybody, welcome to our panel discussion. We have a whole bunch of great people here to answer what seems to be a whole bunch of interesting questions. I'll start off with letting people introduce themselves. So just give your name, institution, and a kind of one-sentence takeaway from your talk. And Drew, that doesn't apply to you, but you can figure out something. So go ahead and start with Chelsea, since you just finished up.
Hi everyone, I'm Chelsea, I'm at Stanford, and I just talked about how we can broaden robot data to get robots to generalize much better.
Konstantinos?
Hi everyone, thanks for the invitation. I'm Konstantinos Bousmalis, I'm a research scientist at DeepMind, and I talked about cross-embodiment imitation.
Alexandra?
Hi everyone, I'm Alexandra Faust. I'm a research scientist at Google Brain, and I talked about how to train autonomous robot navigation scalably.
Sonia?
Hi, I'm Sanya. I'm associate professor at the University of Toronto and also lead a research lab at NVIDIA in Toronto. And I talked about different approaches to simulation.
Akshara?
Hi, everyone. I'm Akshara. I'm a research scientist at Facebook AI Research, and I talked about how to teach legged robots to perceive their environments and adapt to what they see.
Anka?
Hi, I'm Anka Dragan from UC Berkeley, and I talked about getting robots and AI agents to assist people, and in particular, how we might do that differently than just inferring the person's intent and then helping them do that and essentially doing that for them, and instead sort of empowerment-based formulations of assistance.
Hoyun? I think that's how I say your name. Please correct me.
Yeah, this is Hyo. I usually go by Hyo, and I'm at Stanford, and my talk was on how human, especially children, learn from others, help others learn. And I was basically running my imagination wild in terms of how we can get machines to do something similar.
Peter? Peter, we can't hear you at the moment. Oh, still nothing.
You are unmuted, but probably Zoom is not using the correct microphone.
Sometimes it has Zoom audio device or something weird.
All right, I've tried switching mics again. Does that work okay?
That's good.
Okay, sorry, folks.
No problem.
So, Peter Anderson from Google. So my talk was about building massive data sets for language-guided navigation agents.
Andrew?
Hi, folks. I'm Dhruv Batra. I'm a faculty member at Georgia Tech and a research scientist at Facebook AI Research. And my role here is that I was shepherding the conference organizers. I'm not an organizer or a panelist. I'm mostly just making sure this thing runs.
Appreciated. Okay. So we'll get going with some questions here. So one question is kind of on the contention of hierarchical RL. This is directed somewhat at Akshara, but I think everybody can have some input here. Which is, so in hierarchical RL, often the low-level controller, the low-level agent is frozen before you train some top-level controller on it. And while this makes sense, it's somewhat dissatisfying. So what do people think is the bottleneck of being able to get to possibly training these together in the loop? Or Or if we can get past that, does it just become a kind of single end-to-end system that doesn't necessarily have hierarchy in it without this freezing? Akshay, I'll let you start.
Yeah. So Maria, I can start with, basically some experience that we have with this. So agreed completely, this is very unsatisfying overall. And we're basically constraining our search space on hardware often to whatever we have learned in simulation for our low-level policies. And as you can imagine, if your low-level policies are not learned properly, there's not much that you can do on your high level, which will result in good behavior, basically, if your low-level policies are not trained properly. So yeah, definitely, I think freezing your low-level policy is a very unsatisfying way of doing this. I think that what we need to do here is probably a more iterative approach in that we are kind of using offline data and online data to update our low-level policies as we are getting more data, rather than do an end-to-end planning, learning approach, basically, which will be much more sample efficient and does not necessarily generalize. So I think modularity still has a lot of benefits, especially with regards to generalization and cross-embodied learning and data sharing. And we should still exploit that, but instead of freezing our low-level policies, we could probably do a more iterative approach of updating the low-level policies based on information we are getting as we are, unrolling things on hardware.
I completely agree for what it's worth. I think one reason we're not doing this is because it's more of the engineering challenge than anything else. And we should be doing more of that. On the other hand, the modularity does help. If we have a full end-to-end system, then we're risking into being able to solve one complex use case very well without being able to reuse the policies. So I think the ideal scenario would be having multi-headed, multitask, higher level policies that are running on top of the single lower level policy and training at the same time.
Yeah, I tend to agree with that. Just speaking, having worked with Sandra on this is it's challenging getting them to learn at the same time, but having something multi-headed where the core is learning the same thing is a good approach.
So kind of in a similar vein to this, there are a lot of different sources of potential supervision in embodied AI. This comes down to reward in different shaping, actions, and demonstrations, be that from oracles or humans, and potentially self-supervised sources. What should we be focusing on this? Is there one of those that's more particular than the other, or are these things kind of all together that have their own importances and we probably need to bring them all into one to be able to get to where we want to go?
I can maybe start taking a pass at that. I think in our experiences so far, especially when it comes to just information about the reward function. So I'm going to assume that RL works. And if you have a reward function, everything works out great. And the rest of you are going to figure out how to make that work. And then I'm going to say that for the reward function itself, we don't know what it is, right? And so traditionally we use demonstrations, but demonstrations are very limiting, not just because people are suboptimal and so on, but also because demonstrations, if you think about it, they only compare the optimal or approximately optimal thing to do with everything else, but they don't provide you much information about how different suboptimal things compare, right? And so when you don't have that information, well, you don't need it to just imitate the policy, to imitate the demonstration. But if you want a reward function that has a hope at sort of transferring to other environments, now you're in trouble. And so we have definitely seen that there's pros and cons in terms of their informativeness, but also the completeness, essentially, of different forms of feedback. And surprisingly, we found that there's a lot of kind of hidden sources of feedback that we weren't thinking about yet. My favorite example is this idea that that my student Rohin Shah came up with, which is that you can take a look at the environment, and that itself provides information about what the reward function should be, because people have been acting in that environment. You haven't observed those actions, so you haven't gone demonstrations, right? But they've been already shaping their environment to sort of be to their liking, and that informs you about stuff that you probably shouldn't do. If someone put a bunch of effort into creating something, you should probably not just knock it down. And so there's kind of hidden information. I like to talk about leaked information from people. People leak information the way they react and the way they set up their world and so on and so forth. And it really feels like we should be reading into all of that as well. So I think the answer sort of is that one type is probably not optimal if you combine the sample complexity and the need to actually disambiguate the reward function. And I could imagine that you can sort of generalize that to learning about the task in general beyond the reward.
Social norms that you're referring to. That in these applications, it's not just enough to complete a task, but how the task is completed is very important and is contextual.
Yeah, and I think that even just to kind of add on to what Sandra said, I think in RL, we tend to kind of kid to ourselves that the task is easy to specify, but maybe there's, pesky users that have preferences. But in my experience, I don't know how to set up a reward function for an actual autonomous car that needs to face any environment, and that reward function has to incentivize the correct behavior everywhere. Like, that's a joke. I cannot write that down. There's no way that I could possibly do this. And I can take any time, even something like grasping, right? It's just, if you really want to do the real complex task, then I think we kind of have to stop kidding ourselves that we can actually write down the specification of the task is fine, but then maybe there's nuances in, users, preferences, etc. Forget about users, just us as designers, we specify stuff and we get it wrong all the time. And so I think we kind of have to think beyond, to think about these notions of learning reward functions, even for just a vanilla task that have nothing to do with people.
On that note, I think that task specification is, like, in general, a very underrated problem. I think that there's so much work on reinforcement learning and optimization of behavior. And in comparison to that, like, the amount of work and people studying task specification is so much smaller. And I do think that part of the challenge is we don't even know what the right problem formulation is. And, like, we don't have a clean problem statement. And I think that's good. I think that we need more research on different problem settings, like the problem settings that Anka was mentioning, of, like, inferring these sorts of rewards or inferring preferences from the state of the world, for example. And I think that we shouldn't just pick one. I don't think there is one best one. I think that there's pros and cons of each. And as a community, we should be open to a variety of different formulations that people are exploring, because we haven't really figured out the best formulation of the problem, and figuring out the problem is part of the research.
Just jumping off of what everyone was saying, just from the perspective of somebody who studies humans and especially children, I think it's absolutely right that the task specification is a problem that is kind of a giant in the room that we are not really talking about. But if you just look at what children are doing, there's no such thing as, like, starting and ending. It's all something that we have defined for ourselves. I'm going to say I'm starting now. I'm going to say that I'm ending now. So this is something that agents can set for their own, instead of something that's been imposed by an external world. Of course, there's schools and homeworks and assignments that kind of impose these for learning, which is something that we're trying to impose on robots, for instance. But I think it's important to think about that. And also just thinking about reward function specification. Humans are incredibly good at balancing across different kinds of goals and knowing what to do in a given moment. And in the talk, I was briefly mentioning this example of a baby that's failing to do something, but then depending on why the baby thinks he or she's failing, they either seek for help. There's no way I'm going to be able to do this, so I'm going to ask for help right now, and that's what I should be doing. Or, I think this is broken, so I'm going to go look towards something that's seemingly working. So trying to figure out what to do in a given moment and trying to generate the specific reward functions for the specific goal that I'm trying to achieve seems to be something that I would love to see
more progress on. And I think for this, it would be great to see more cognitive scientists and people who study humans talking to more people who are developing AI.
Just to add, I think one elephant in the room is that we have a fundamental gap in the abstraction level between POM MDPs and MDPs that are used for sequential decision making, whether you use RL or whatever technique for learning we might be using. But then the practical problems we're trying to solve do not fit the POM MDP mold. We're talking multitask, we're talking multi-environment, right? There is no abstraction for environment in MDP. There is the rewards are a lot complex. Task specification does not exist in POM MDP and so on. So focusing on kind of figuring out what is the right abstraction to do these applied problems and then do a translation of the world in POM MDP is really where this, we call it seem to real gap, and it's practitioners approach without kind of having a lot of fundamental principles developed yet.
I'll say one very quick last thing, because this is probably my favorite topic, which is that if you're in the audience and you're sort of new to this area of learning from human feedback, we try to write up a tutorial that might hopefully be useful to you. It's called Reward Rational Implicit Choice. It's kind of like a survey of, here's how you can think of all these different feedback types, and here's kind of a unified framework in which you can kind of see them as doing all the same thing, so you can start being able to combine them and do active learning among them and so on. So if you're interested in kind of learning more about this space, Reward Rational Implicit Choice is the tutorial that we wrote up to try to help with that.
So Peter and Sonia, one common theme from both of your talks is imagining the environment. How far do you think this can be pushed, and what do you think the limitation of this is?
Sorry, can you say again? What was the question?
One common theme between you and Peter's talks is imagining the environment. How far do you think that can be pushed, and what do you think kind of the core technical limitation is of imagining the environment and training agents within that?
You mean like generative models of the world?
Yeah, generative models of the world, or like it doesn't necessarily have to be at the level of pixels or something like that. It can be in some latent space, etc.
Yeah, I kind of believe in that approach because in my head I can imagine a lot of things. So that I am building an environment of the world. However, there's also limitations, right? Because right now we can only imagine things we have seen, so because it's all data driven, right? So if we haven't seen certain accidents occur, like if we're talking about autonomous driving or illegal maneuvers, we can never imagine that, right? So there probably is also need for human engineering, game engines that can kind of counter that and imagine things that we know can happen, but maybe we haven't physically encountered. So that would, I guess, be my answer to kind of counter both approaches, right? So human engineering, how the model should look like, and learning from data.
So I'm, I guess, continue to be amazed by the trend towards training vision and language models on web data, and this trend just keeps going and going, and the performance of these image text models is just surprisingly good. And so to me, this motivates a kind of desire to want to do something similar in embodied AI, but of course we can't just get on the web and find trajectories and, instructions or, whatever type of training data we're looking for. So to me, that's the motivation for this sort of generative approach. And my opinion is that the sweet spot is where you're taking some sort of web data as initialization to a generative model, but then you're using the generative model to sort of fill in the gaps to maybe, resample some video from YouTube in the action space of the agent that you want to train and that type of thing. One limitation of this is putting expensive generative models in your training loop is going to be pretty expensive, and looking at all the work that folks have done on things like Habitat to kind of speed up the frame rates and the benefits that has provided, I think, clearly shows that that's important. Just recently, I was excited by the decision transformer and trajectory transformer sorts of models, because I guess one advantage of those types of approaches is that it's effectively imitation learning, and you can kind of pre-generate all your trajectories without doing it in the training loop. So yeah, I guess that's a potential limitation, but there may be ways to get around that.
I can also comment on this because I also have done a lot of work on generative models, including some of what I included in my talk. Like I mentioned in the talk, I think that underfitting is one challenge, and also like Peter mentioned, I think that these models are expensive, and so using them in the loop can be challenging. If you can get a good latent space model, then that actually is a huge win in terms of speed, because then you can potentially just put everything in the latent space and then have this much faster latent space model. And we've seen some benefits there, including in the first part of the work that I talked about with collecting the data. One, I think, underrated benefit of these models is that they're actually very interpretable. You can look at the predictions and see what the model is thinking, quote unquote. And in the real world, this is super, super valuable, because actually running the robot in the real world is super expensive. And so you don't actually have to do that to understand roughly its performance. This is, I mean, if you're working in simulation, this is less important because you can just run your policy in simulation and get an evaluation directly. But in the real world, getting that sort of evaluation of your policy is really difficult. And so being able to look at the predictions and what the model kind of knows and so forth is really useful, because if it doesn't know how the object is going to be pushed when you move your arm, then it's certainly not going to be able to figure out how to interact with that object with planning and policy optimization.
And maybe just that. So one thing that is really nice about these generative models of the world is they're differentiable, right? So suddenly you have a differentiable representation of the world, right? So for example, in any of these robotics applications that maybe some intervention happens or something like that, it's really key that you go and reproduce that scenario in simulation so you can test again or maybe even train again. And if you have this kind of differentiable simulation where you can recover some of the parameters, you can resimulate very easily. I think it's like a huge win.
To add to that, we've also had a lot of pleasant experiences with leveraging the fact that these are differentiable, just to be able to actually directly optimize over environments to put the robot in, to then have a human look at and say, oh, no, do not do that. And so you can actually do active learning over this stuff. And it really kind of cuts down the sample complexities and the unwanted accidents at deployment time, in my experience.
Konstantinos, do you have a perspective on this of how it might tie into, as an interpretability thing, probing the agent's knowledge and beliefs about the environment?
I think that's I think interpretability is a big issue here, and I think I don't know exactly how people deal with interpretability when they generate latent samples, but I think there are obvious advantages to using latent samples, and if interpretability for latent samples is improved, I think that would be another path here potentially.
So your argument here would be potentially to generate in kind of like observation space that way, because that gives you interpretability quite easily.
Well, so generating in observation space has the obvious advantage is that you can actually look at the data before you use that for training, but it also comes with big sizes, right? So being able to have concise codes, latent codes that represent that data, and being able to reason about your scene in that latent representation is preferable if you had some way to actually make that interpretable as well. I'm not sure if there's a lot of work on actually producing latent codes that are also interpretable. I don't know if others in this panel are aware of such works, but I think that would be an interesting path.
Yeah, I'll just add to that. I'm actually quite excited about how interpretable these generative models are. So particularly the ones that we were using, so generating the images, so the pixels themselves. So the thesis is that if you're able to generate like an entire image that looks realistic, then that generative model, the feature representations inside, know a lot of things, know about, lighting, geometry, semantics. And, then we have all seen these latent codes being interpolated, and everything in between also looks great. So there's some correspondences that these generative models actually find across maybe many different examples. So it turns out that now if you just add like very tiny MLPs on top of those latent codes and just label that output like the image, you need like super little training data, super little annotations, and it kind of just propagates that information across the latent space, which is, I think, like a huge win, because suddenly you can go like 100x less label data by just basically leveraging these generative models.
I wanted to add one point to the interpretability part of the latent model. So something that we have looked into is kind of for robotics applications. As Chansi said, it's actually really hard to unroll a policy that you learned in simulation on hardware because the system has to be more safe than as you would be in simulation. But something we've looked into is kind of learning latent representations at a higher level and then unrolling them in simulation to get an estimate of what kind of behaviors do we expect on hardware on the real robot. So for example, if some parts of your space in this reduced order space are just producing random motions of your arms and legs, you probably don't want to search in the space on hardware. But on the other hand, if you're actually getting reasonable behaviors in simulation in some part of your space, then you can use this for also informing this the search that you will do on hardware. So some part of interpretability in these latent actions could also probably be added by building simulators for whatever environment you're interested in, I imagine.
I have a two-part question for you. So do infants learn to evaluate their teachers? And if so, is there evidence that they act on this information to kind of re-rate their teachers and use that to aid in them learn? And then to the rest of the group, if this is the case or if this isn't the case, is this something that we should try and do in ML systems of evaluating teachers and then trying to re-rate the teachings based on that?
Yeah, so I can speak to the first part first. So some of the studies I talked about today, especially on the how they interpret signals from humans and how they make use of it, some of these come from infants and some of these come from older children. The studies I talked about in terms of explicitly evaluating or labeling a teacher as unhelpful or less helpful, not as good, these are coming more from children who are older than 3, 4, at least years of age. And some of the studies that we won't find success until 5 or 6 years of age, which says something quite a lot about what is involved in these kinds of tasks. You have to know something and remember that in order to be able to evaluate whether a person provided helpful information, because otherwise you're just learning from them. There's no way for you to evaluate if you don't know the truth about the world. And second, I think there's a lot of perhaps something like a default assumption that children have when you're seeing something coming from adults, especially in a pedagogical context. This person is trying to tell you that I know something, I want to tell you something. It's really hard for children to override that default assumption unless they have a lot of evidence. So being able to evaluate somebody who calls a shoe a horse, that comes earlier compared to saying that, oh, if you didn't show me all 4, you showed me all just 1. That seems to be emerging a little later. So a lot of these are not coming from infants, but there's also a lot of work showing that even very young infants are sensitive to people who are acting irrationally in terms of their inefficiency. So they're paying attention to what others are doing, and they're constantly assessing whether that person seems to be acting in the world in a way that is consistent with what they think about what humans or human agents should do. So I think what this says is that human agents do seem to be having some very initial set of assumptions or some kind of generative model. We talked about the generative models of the world, but there's certainly generative models of how people act, think, and plan. And they seem to be growing over time in a way that makes their predictions richer and the way in which they respond to other people's actions much richer. So that's one thing I could say, and I'll leave it to the other panel speakers for addressing the second part of that question.
So for the second part of that question, I think there are already RL methods like AWR or CRR, advanced weighted regression or critic regularized regression, that evaluate the information that comes from, say, a teacher policy or multiple teachers' policies, and adjust how much the specific supervision affects training. I have not seen something that does that at the teacher level, but maybe that's not necessary if you can actually evaluate the specific supervision that you're getting for a specific state. Let's say.
I think there's maybe two problems here. There's one thing that you can do when, going back to our previous discussion, you know the reward function, then it's pretty easy to say, oh, in hindsight, this sucked versus this was very good, because you can actually evaluate teacher policies using the reward function you have. But if you're doing, teaching, learning from humans to speed stuff up in RL, then I think we're in good shape with that. If you're doing learning from humans because you don't know what you should be doing in the first place, so you don't know what the reward function is, then it becomes a little harder because you don't know whether something was good or bad. One idea there that could be helpful is to jointly infer the reward and the teacher's rationality level. So typically when we learn from people, the way we connect the rewards, right, what they want to teach us with the actions or the feedback we're observing from them is through some kind of rationality, approximate rationality, biased rationality, whatever kind of model like that. And then you kind of have this kind of cool opportunity to not just infer the reward function, but to jointly infer distribution over the reward function and the teacher rationality. Now, this is a joint distribution, so we'll have ambiguity, right? You can come up with explanations that are like, either the task is this and the person is really rational, or they're crazy for this other task. And both of those explanations are super valid. So it doesn't just completely solve the problem, but you at least kind of can, you can then use that joint distribution to sort of plan an expectation or to sort of hedge your bets, do some sort of a worst case risk averse optimization, stuff like
that. Just one small point, completely agree with what Anka and Konstantinos said, right? And I think when we have human demonstrations, maybe in a way, we don't even need to think about if they are good or bad, because they might be good for some settings while being bad for other settings. And it makes sense to kind of get maybe like an offline policy kind of a setting with human demonstrations in which you're just getting skills out of it. And then depending on whatever task you have in the future, you choose out of those skills, which ones would be most suitable for the new task that we have at hand.
Just to close the loop on that, I was watching Chelsea's talk, and there was this example of humans providing interesting examples, and then the robot performs a lot better, and then it opens and closes the drawer. And then I was imagining, like, what if in addition to that, there was a human? I know there's like hours and hours of data there, so it's hard for humans to observe the entire thing. But what if humans can label certain discrete sort of segments of that as, hey, that's called opening the drawer. Hey, that's called closing the drawer. And in order for agents that are behaving in real world environments and then hopefully assisting at some point with real world tasks, excuse me, it'll be really important and interesting for those machines to be able to learn from human feedback. Hey, that was good. Or, hey, that wasn't as good. And in real world environments, it would be nice if they could distinguish between people who are actually providing useful feedback versus kids that's just kind of, running around with the robots and not really providing feedback, but kind of things that they can ignore. So being able to jointly infer specific individuals in terms of their informativity or usefulness for their feedback would be a really nice feature eventually to imagine. So just wanted to add that.
Yeah, I agree with that. I guess one thing that I'll add to that too is we actually have some work that we submitted to Coral very recently and will be out soon on giving that sort of feedback actually in the form of natural language, where you collect data and then just have, we use crowdsourcing because we have a lot of data, just to kind of say, okay, what did the robot do in that case? What did it look like and so forth? And I do think that natural language may provide a useful interface for providing supervision to robots and conveying information, because it's a very flexible thing. Like, we can describe a lot of things, it turns out, with language, and also it's a very easy medium for humans to provide feedback compared to things like demonstrations and so forth. And beyond the work that we have coming out, there's also, of course, like a lot of literature on language and RL more generally as well.
And if we look at the very first part of this question of what do children do, just in case people don't know, there are these awesome studies done in the 80s by Andrew Meltzoff, which basically show that if you have, at some point, I don't remember the number of months, maybe 14 months old, if you do a task in an irrational way that the infant can't really explain as you had a reason for doing it that way, they'll actually imitate the kind of the intent and do it in the rational way. The example is with pressing a button, and you're not pressing with your hands, you're pressing it with your head. And in one condition, you have a reason to press it with your head. Your hands are tied behind you in a blanket or something like that. And then the infant actually just figures out, oh, you want to press the button, and then they press the button with their hands. And I think that's a super cool thing that we develop at, probably not 6 months of age, but 14 months of age, or we already have that ability to say, you've done it in a weird way, but I'm going to do it the better way.
So just to add on to what Anka was saying, Andy Meltzoff did a lot of studies from the 80s, including facial expression imitation. The blanket study is from Gergely Chibra and Gergely, a team in Hungary. And what exactly as you say, what they have shown in that study is that goal inference really matters in terms of when they imitate, what they imitate, and depending on what they think the person's goal is, they will either do the exact way of imitating the person's behavior, or try to just go ahead and achieve the goal if they think they don't have to do it because that person's actions were constrained. So this is like a combination of action perception and understanding that that person's action space is constrained, but mine is not, and therefore I don't need to imitate that person, but I'm just going to emulate that goal instead of just copying the behavior. But there are cases where that's important, and even then they're not blindly copying. They are achieving the goal in the same manner as the humans did, or as the adults did, because they believe that that's how the toy works. So even though their action space is not constrained at all, they will still use their head to activate that light. So thanks for bringing that up, Anka.
Kind of a question to everybody. How important do you think big data is for embodied AI, and how feasible do you think it is? Peter's talk in particular kind of posited that it would certainly make things easier, but does that distract us from moving towards human level sample efficiency?
So I think that this question really depends on what you mean by big. I think that 2 hours of data personally is I just don't think that's enough. Humans, well, I'm not an expert on humans, but humans clearly seem to need more than 2 hours of data. And so I think that we need to be in settings where it is much more than that. Personally, if we want robots to generalize in ways that are meaningful and actually could have the potential to go into the real world, I think that data efficiency is important, but I think that in particular, online data efficiency is really important. The amount of new data that it has to collect. And in order to get to big data, I think that we need to be using large offline data sets and then potentially a small amount of online data for the particular scenario.
Yeah, that's a fair point to throw out there also of, are humans actually data efficient?
I was just about to say that human sample efficiency is actually, we should take into account that there is such a paradigm of what what Chelsea just described, right? So there is a lot of data, a lot of experience that comes from years of living in this world, and this would be kind of the offline setting, the sim setting that we would want our models to be able to utilize, so that the online, the expensive data efficiency is low.
So I'm obviously in the pro big data camp here, I guess. It was a feature of my talk. I do think there's a bit of a tendency for us to, maybe put more of our focus as a community on building models as opposed to worrying about the data that they're trained on. We sort of get a benchmark academic data set and we run with it as hard as we can, and maybe don't consider just making that larger. And that doesn't necessarily mean spending money, but I think if some of the cleverness we put into the modeling was instead focused towards cleverness in terms of how we generate synthetic data from resources that are available, perhaps, then we might find there's some inroads we can make there.
The other thing that I'll add is I think that you need to be thinking about data efficiency with respect to the complexity and breadth of the problem. If you need I think that big data is a good thing. I think that especially large offline data sets, but if you're using a huge offline data set to get a cheetah to run forward in a fixed environment, that's not what I'm talking about. Because I think that that's just we need big but broad data sets and to try to learn kind of things that generalize very broadly from such data sources. And so it's a matter of what things look like. I hope Sandra's okay.
Sandra, are you okay?
Hope the crisis is manageable. Just to add on to what Konstantinos and what Chelsea was saying, I also want to add that human sampling is efficient, not only because they did have a lot of data from their whole lives, but also perhaps we should think about how their knowledge is structured and how they're getting used at every single moment of the day when they're trying to decide what to do and how to interpret this person's action. Or I'm looking at a scene, what am I looking at? And once you have an understanding of once you have that kind of structured theory, knowledge of how the world works and how people work, then a lot of things that you observe in terms of people's actions and what you see in the world makes so much better sense. And you're able to focus on the right way or right dimensions of the images or scenes that you're seeing. You can generate more informative alternative hypotheses in terms of what you are trying to learn from. So I think I also want to draw attention to that aspect of how humans store and use the observed data, in addition to just the fact that they do have a lot of data or have had a lot of data.
Eric, can I press on that question for a little bit more clarification?
Yeah.
To follow up on that direction, I think we have good ideas or good sources for how to scale web scale data, images, videos, text captured by people, uploaded online, made available for offline tasks. I think we have good ideas there and good sources there. I think we have okay ideas on how to get simulation data. It's not infinite, but diversity is limited, but we have some good ideas there. I don't think I know good ideas to scale hardware experiments other than robot farms, which get limited. And I have particularly a hard time thinking about how to scale human-robot interaction type experiments, where it's not the same as connecting Mechanical Turk to a chatbot. So those two, do people have better ideas? How do we scale that to the extent we believe in the scaling hypothesis that if we can get 100x more data of that kind, things will work better?
I can start. I'm sure, this is a great question and everybody's going to have different experience. The one thing I think that we can do is that we establish the differences in kind of statistical matter between simulation experiments and on-robot experiments. And if we can establish that, okay, maybe our simulation experiments across the set of environments and whatnot are within 3 to 5% or so on, so we have margin of error, then we can kind of start more evaluating in simulation with the idea that yes, this transfers. I think also as a community, robotics community in particular, we need more of the physical test beds. So supercomputing back in the day community had these large data centers where researchers can go and submit their jobs in simulation that actually propelled. Robotics does not have anything like that. There is not a large scale physical test bed that we can do and submit jobs in simulations. Once they pass this test, then you submit them on a physical robot in a test bed and so on. And that's a serious conversation to have across the community. But
So I would argue that I think that maybe there's a chance that we don't actually need a large physical test bed of robots. I think that collectively across all of the institutions that have robots, we actually have a pretty large number of robots overall. And the problem is that the paradigm in robot learning is to literally throw away your data after every single paper and every single experiment. And I think that if we can figure out how to stop throwing away that data and figure out how to reuse it across experiments, across papers, and essentially do kind of reinforcement learning across papers, maybe we can get towards the data that we have. I also think the good news is that robots can collect their data without humans in principle. So if we can figure out how to allow them to have greater autonomy, then we might be in better shape.
Chelsea, just to clarify, my point of view comes from navigation, where it's very hard to replicate same conditions. In manipulation tasks, you can have more similar physical settings that can be compared in different institutions and so on. With navigation experiments or environments are just so large that, I don't know, maybe there is a value.
One of the things that we've been trying to do with the navigation group that Sandra and I were part of in Google is to actually build out the ability to do these experiments. And it's painful. It takes a good bit of time to build the infrastructure to make that necessary. And it's always, seems better to get the next paper out. But it's also a finite problem. And after having spent some time doing this, we had the pleasure of running a recent experiment where I literally was able to roll things out like almost immediately in the same pipeline that all the other experiments were running, and we can collate the data against each other. So it's a painful step to go through as a research community, because it's more like the development than the research. But if you can make the investment, it's worthwhile. The one caveat is when you start to try to bring in humans and human appearance into it, getting large numbers of people whom we have the right to use their faces, without deblurring and so on, that's another engineering challenge, because ideally you would love to deploy many, many robots and then just see how they interact with people and use those tracks. But there are legal, things to consider. And when you start trying to use that in experimental data in association with an academic institution, there's experiment review boards. I think these problems are solvable, and we should. And I don't think we should be daunted by the fact that there may be a few hurdles to overcome.
I think I will give a more controversial opinion here, and then hopefully everybody doesn't jump on me. But I actually think that we should reason about what space we want to get this big data in, because in robotics we do have a lot of knowledge about the system that we are operating on. So we have the dynamics model of our robots, we have physical simulations, and yes, simulations are not perfect. There's a lot of things to work on there, but I think it's worth thinking about if we want to collect big scale of data of the robot without moving, interacting with one object in a static place, versus do we actually want to collect data on the larger scale of a robot operating in a house, but maybe not every time-second interaction that the robot is having with the environment, because we could probably use a lot of prior knowledge in building controllers, which can, basically building controllers which can do the low-level things while we are dealing with high-level data collection for robotics. I don't know if that makes sense.
I'd like to pick up the human side of this that Drew mentioned. I don't think anyone touched on that. I think broadly there's at least two ways, potentially. From time to time, people talk about creating sort of massive interactive environments with people in the loop that are sufficiently gamified to be interesting, that people want to be involved. And I guess there's that direction. I'm not sure if anyone's made very serious attempts at that yet, possibly because our models aren't good enough at tasks to be interesting. I think there's various other risks involved with that as well, including the fact that everyone just hates it and nobody sort of joins or participates. The other broad direction is probably trying to leverage text and image data and the sort of web resources, but using a combination of generative models or even template-based models to sort of rewrite that data into a format that more closely associates with the sort of task that you're trying to learn, I guess. So I mean, there's a two that I've given some thought to.
There's a third one, which is to rely on human-human interaction data, which also has its limitations, and kind of part of the nuance there is not, there's the obvious, which is, well, a human will not act necessarily around a robot the way they act around another human. Okay, cool. But there's also sort of something more nuanced, and I think more coming from the statistical perspective, which is that I can collect a bunch of human-human data, and then if my robot needs to decide on what to do, it's going to have to somehow query that model and condition it on these kind of counterfactual, hypothetical things that the robot is considering doing, and know what the human would do in response, right? So in order for the robot to do planning, RL, et cetera, with these sort of models, you will, by definition, push them out of distribution, because it's not the case that the only thing you'll query them on is the human-like thing that the human that they interacted with was doing, if that makes sense. So it's just the trouble with human-human interaction is actually not very different from physical interaction. It's basically that you have to have collected data where you have explored the space. And human-human interaction data doesn't explore the space enough because it's just based on reactions to other human policies.
How important do you think the embodiment of the robot is in human-robot interaction data collection? For example, we could collect good amount of data with, like, I don't want to say photo, but I will say photo, but like a face, basically a video conferencing system, or maybe a vector, like a tiny robot that's moving around on the surface. It's easier to collect data with such a simple embodiment versus having a full humanoid robot operating in the space. And do you think that to the panel in general, is there value in such data on simplistic robots?
I'd say likely not more value than just observing humans, period. Because if what you're looking for is the way people will respond, adapt, react to, move around your robot, they will do, the task is so different, right? They do very different, the Cosmo or the vector just sits on a table, right? And so and if you want to think about, well, how will pedestrians walk around my autonomous car, the interaction that they have with the Cosmo in their house doesn't really, or if you want to say you're Sandra and you want the robot that navigates in people's homes, again, the interaction, the data that you collect from just it's basically, I think it's essentially as which is valuable, but it's as good as kind of putting a camera in people's homes and being able to track them. And then you know how they act in isolation and how they act around each other. And that goes back to my previous point of them in isolation and then around each other is not quite enough from a distribution of data perspective compared to what you typically need for when you put a robot there.
Yeah, I'll just add that perhaps they just thinking from the human perspective, the realism of the robots, like actual embodiment, might actually matter less than we typically think. It'll affect the way that people interact with the robots because they understand that this has different ways of like physical affordances on the world. So it might not shake to, try to shake hands with the robot if it's clearly not having an arm, but that, the way we think about C3PO versus R2D2 doesn't really depend on, how they look, but how they think or make decisions and interact in terms of their actions and verbal behaviors with the humans. So I think that's one thing to consider in terms of thinking about how important the realistic physical embodiment is. But cues are important because if it has eyes, people will assume that it can see. And if it has hands, people will assume that it can actually physically manipulate objects and so on and so forth. So those assumptions that people have about what the robot is capable of doing, I think those kinds of features will really affect the way that people initially expect what robots can do.
Going a step further and kind of echoing these 2 points, humans will behave differently around robots, and that's robots' reality. We should be able to learn these discrepancies from the observations, the baseline that Anka had mentioned, and then observing how that differs and changes in these very specific environments, and then using that knowledge and baking it into training, and that way possibly bridging the gap. Basically teaching robots to know what to expect. I don't know, just a thought.
All right, we're almost at the time here, so I'm going to go around and have everybody give a kind of final takeaway of what they want the audience to leave with, both from this discussion and kind of from the workshop in general. And so we'll go in the opposite order, starting with Peter this time. If Peter, do you want to start?
Sure. Well, I guess probably the takeaway is the same as my talk. We should think about how do we get 100 times or 1,000 times more training data, and think about synthesizing and generating aspects of the data in order to do that.
Akshay?
I think the takeaway is that we're very far away from bringing embodied agents into the real world, right? And there are many unsolved questions for me. Maybe collecting a large amount of data, as Peter said, is one way going forward. But yeah, I would also say that we should think about what the space should be that we're collecting data in and how we're using it. So I think at some point, someone mentioned how do we reuse old data that we have seen before and continually keep using it in the future and things like that.
Anka?
I'd say for me, it's that we should not think of the human role as being just a speed up learning for embodied robots, but really in my mind, they're kind of hold the definition of the task that the robot should be doing. And I think that that's very clear when you talk about assisting people with what they want, but I think we're underestimating how true that is for almost every robotics task we set out to solve.
I agree with everything, including the fact that I think humans are more important than everyone knows that humans are important, but perhaps even more so, not just in terms of thinking about how to collect large amounts of data, but thinking through how humans are able to make a smarter use of that data, and also how they're defining tasks around embodied AI and providing useful demonstrations, not just to be copied, but to be, again, used in a smarter way. So I'm hoping that sort of thinking from the human perspective and trying to embody some of those features into robots, and also thinking about the human user side, I think more of that thinking has even bigger influence on the field after this panel.
Sonia?
Yeah, so I think simulation is really key and super important for embodied agents. And my personal personal belief is that data-driven simulation is really the way to scale these efforts.
Sandra?
There is a lot that we need to do. First of all, it's a great discussion. The takeaways is that, yes, humans are central and humans have two major roles in the embodied systems. One is to provide the data and be the trainers, and the other one is to be a teammate and actually part of completion the task and so on. So on the first end, where people are providing expert demonstrations and so on, generative models and automation have really big promise there and bridging this into real gap. And then I think we need a lot more work on the HCI and robot-computer, robot-human interaction.
Konstantinos?
So the takeaway for me is the data is limited and very expensive in the real world, and we need to do more work, more research around data reuse from prior tasks, from other robots or environments, including simulations, and also data reuse from third-person imitation. And I think that's something that the vision communities could help with. Bridging the perceptual reality gap, utilizing demonstrations from other embodiments, and especially humans, and maybe learning actionable and general representations. I think the vision community would be really instrumental in helping with this.
Yeah, so the takeaway that I'd love to convey is that we should try to figure out how to stop throwing away data and actually figure out how to reuse data a lot. And I think that, unfortunately, I think that doing this will probably require a fairly big paradigm shift where we're no longer using data from our one particular problem and trying to solve that one environment and so forth, and moving towards a scenario where we might need to be using messy data from other tasks, from other environments and so forth, maybe collected with a slightly different robot, a different action space. And so I think it's going to be hard, but I think it's a shift in the way that we think about these problems that is super important for generalization and maybe even inevitable.
All right, well, these are some great takeaways. Thank you very much for joining the panel discussion. Thank you very much for your talks. It's been great hosting this. Yeah. And so now we'll kick things back to the rest of the
Thank you.
See you guys.
Thank you.
Thanks, everyone.
Folks.
Thank you, everyone.
Everyone.
Great, so we'll be breaking for lunch from noon to 1 p.m. And at 1 p.m. we will have a poster session. See our website for the link to that. And then at 2 p.m. the live stream will continue on from a brief pause, and we will talk, go into our challenges. So thank you, and I hope to see you all soon.
Hello, my name is Alexander Maximets and I'm a research engineer in Facebook AI Research, working on Habitat and one of challenge organizers. My talk is divided in several parts. First, we will briefly talk about Habitat, then about task for the challenge, concluding with winner announcement and submission analysis. Habitat is a simulation platform for research in embodied AI. Our goal is advance science and engineering for the field. This habitat enables training of virtual robots and egocentric assistants in highly photorealistic and efficient 3D simulator before transferring learned skills to reality. This year, Habitat Challenge is part of Embodied AI workshop at CVPR 2021. That includes 9 of the other challenges as well. The results of Habitat Challenge 2020 indicate that the benchmarks we proposed previous year were far from being solved or stagnated. So we continued point nav without localization sensors and object semantic navigation tracks. Point nav task where agent has to navigate to locations specified with coordinates without localization sensor is much harder than point nav with GPS and compass and has significant amount of the realistic noise. We believe that solutions of the task specified this way will unblock usage of point nav as subtask for other tasks where no GPS and compass is provided, like visual language navigation or embodied question answering, as well as help better sim-to-real transferability. Let's look on sensors available to the agent. First, goal specification is relative to episode start position and doesn't update during navigation. Then, visual RGBD sensors observations that are noisy, and building map leveraging the depths is harder. While we have 4 discrete actions, the action doesn't guarantee deterministic position orientation transformation. We use Lockabot actuation noise model here. Thus, the task specification remained unchanged to previous year. This year, for the agent's camera tilt angle, we changed it, and the agent can observe the area in front of it as the camera now is tilted. Switching to semantic navigation task. The goal of task is to navigate to the object specified by category, like find a fireplace. In terms of observation, the goal is specified by goal category and is static during episode. GPS and compass is provided to model robot's odometry and is relative to episode start position. There can be more than one object from goal category. Navigation to any of them considered successful, but closest one is required for optimal performance. And regarding performance, we use success-weighted path by path length called SPL metric to evaluate the agent's navigation. This year, there are some statistics for this year, and this year number of participants teams increased significantly compared to previous one. And the number of teams submitted to Object Nav Challenge phase doubled. It's time to announce the winners of Point Nav Challenge. And Point Nav Challenge first place is Inspire AI Robotics team with a 0.74 SPL. Congratulations to the team. Inspire AI Robotics team includes Xiaolong Hu, Shupen Wei, Tenchu Zheng, Chenjun Wang, and use deep reinforcement learning for end-to-end localization and navigation by learning visual odometry together with policy. And the second place is Ukulab team with a 0.72 SPL. Congratulations to the team. Ukolab team was led by Ruslan Parsey from Ukrainian Catholic University Lviv and used robust visual odometry for realistic point goal navigation approach. Winning teams will present their approaches in separate 5-minute talks. If we check SPL with confidence intervals, there is no interval overlap between teams, as well as statistical significant tests show that all submissions are significantly different from each other. Here is a leaderboard sorted by SPL. Here is a leaderboard sorted by soft SPL. We encourage all participants to fill details about their approaches and add links to detailed descriptions. To analyze the impact of last mile, we show potential SPL chart with two larger success zones. And as we see, the winner team's performance won't improve much. We see breakthrough happening with a major 3 times performance improvement in 2021 for point now version 2. There is a 0.2 absolute gap between success and SPL for best performing entries. Based on our experiments, that can be caused by actuation noise. And we noticed that even with agent with ground truth GPS and sensor, it reaches only 0.76 SPL, while success is 0.99. So the problem of replacement localization sensors for this task is close to being solved. That's amazing news. Let's switch to ObjectNet task and announce results of the challenge there. So the first place is Red Rabbit team with the SPL 0.13. Congratulations to the team. Red Rabbit team was led by Joel Yi and used auxiliary task and exploration enable ObjectNav approach. And the second place is Habitat on Web team. Congratulations to the team with SPL 0.06. So Habitat on Web team was led by Ram Rahia and used learning exploration for ObjectNav using human demonstrations. Winning teams will present their approaches in separate 5-minute talks. Here is a leaderboard sorted by SPL and soft SPL. As you can see, winning entry reached 30% of success on the test challenge split. That's amazing. We compare success to SPL here, and we can think about success as upper limit of SPL. If all successful episodes would have ground truth navigation, as we see, the agent path was at least twice longer compared to shortest path on average. So that was exploration stage takes. Based on human performance on 12,000 episodes from train split provided by Habitat on Web team, we can expect human performance will be around 0.4 SPL and 0.87 success. So ObjectNav has a room till we can reach human performance. While progress was made, ObjectNav task is far away from being solved. From organizer side, I want to thank all our participants. That's exciting to see what progress was made for both benchmarks. We want to thank partners from Embodied AI challenges and Embodied AI workshop to supporting us in this journey, and Eval.ai for hosting our challenges, as well as Facebook for providing evaluation infrastructure. We are grateful everyone who had fun with us, and we are going to keep test standard leaderboard active to be source of truth for state-of-the-art performance for the tasks. Thank you.
Hi everyone, I would love to present iGibson Challenge 2021, co-organized with the second Embodied AI workshop at CVPR 2021. The challenge is hosted by the Stanford Vision and Learning Lab and Robotics at Google. My name is Chengshu Li, and I'm one of the co-organizers of the challenge. In recent years, Embodied AI research have produced impressive results in vision-based indoor autonomous navigation. However, these solutions are usually studied and deployed in static environments such as warehouses and have limited applicability to the dynamic scenarios that are inherent to human environments such as homes and offices. In these spaces, we find a large variety of objects with which the robot can interact, such as furniture, shoes, toys, laundry that are lying on the floor. We also find humans ourselves living in these environments, walking around and performing everyday activities. How to train embodied agents that cope with dynamic environments still remains a challenging research question. Therefore, this year, we want our challenge to focus on navigation in dynamic environments. On the left-hand side, you can see an example of the robot interacting with dynamic objects, such as furniture, shoes, hats, toys that can be pushed around by the robot based on physics simulation. On the right-hand side, you can see an example of the robot interacting with dynamic agents. In this case, these are simulated pedestrians with predefined trajectories. This year's challenge has two different tracks for two tasks. The first track is called interactive navigation. The agent is required to reach a navigation goal specified by a coordinate given RGBD images. The agent is allowed or even encouraged to collide and interact with the environment in order to push obstacles away to clear the path. Note that all objects in our scenes are assigned realistic physical weight and they are fully interactable. Along with the furniture objects that are originally in the scenes, we also add additional objects such as shoes and toys to simulate real-world clutter. The second track is social navigation. The agent is required to navigate among pedestrians in the environment. The pedestrians in the scene move towards randomly sampled locations, and their movement is simulated using a social force model called ORCA that is referenced below. ORCA was integrated into our simulator iGibson. The robot agent needs to avoid collision with the pedestrians, otherwise the episode would terminate. It should also maintain a comfortable distance to them in order to respect their personal space. For the environment setup, we use a simulated local bot. The observation includes the goal, the current velocities, and RGBD images. The action space is a twist command. The reward function is up to the participant's design, and the episode will terminate if the robot exceeds 500 time steps or it collides with any of the pedestrian. We provide 8 fully interactive scenes as the training set, 2 scenes as the dev set, and 5 scenes as the test set. For evaluation metrics, for interactive navigation, we use interactive navigation score, INS, as our evaluation metrics. INS is an average of SPL and effort efficiency. SPL stands for success weighted by shortest path, by path length, sorry. Effort efficiency captures both excess of displaced math, kinematic effort, and applied force, dynamic effort, for interaction with objects. We argue that the agent needs to strike a healthy balance between taking a shorter path to the goal and causing less disturbance to the environment. For social navigation, we will use the social navigation score, which is an average of STL and PSC. STL is short for success weighted by time length, similar to how SPL is computed. The shortest time is measured by the time spent by an ORCA-controlled robot agent to achieve the same goal. In the context of social navigation, we argue that STL is more applicable than SPL because a robot agent can achieve perfect SPL by just waiting out all the pedestrians before it makes a move, which sort of defeats the purpose of the task and also can take a really long time. The other component is at PSC, personal space compliance. This is computed as the percentage of time steps that a robot agent comply with the pedestrian's personal space. In our definition, the personal space distance threshold is 1.5 meter. We argue that the agent needs to strike a healthy balance between taking a shorter time to reach the goal and incurring less personal space violation to the pedestrians. Next, we're very excited to announce our winners for this year's challenge for interactive navigation. The top 3 winners are Naoki Yakuyama, Weiyuan Li, and Yan Xinlong. For social navigation, the top 3 winners are Feng Gao, Chong Liu, and Weiyuan Li. We would love to give a round of applause to our winners. Next, we will show some video highlights for each of the track. On the left-hand side, we show the winning team of interactive navigation track, Georgia Tech. The policy performs quite nicely despite a large number of clutter objects that are scattered around the floor. The robot learns to push these light objects away in order to clear the path while avoiding pushing other heavy objects such as chairs and tables. On the right, we show the winning team of social navigation track, NIC-SEFC. The policy also performs quite well around a decent number of pedestrians that are also moving rapidly in the same space. There are a few cases where the robot almost hits the pedestrian, but the policy was able to react in time to swerve the robot away. Across different submission teams, people mostly use model-free reinforcement learning algorithms. Some teams use SAC with continuous action space, whereas others use PPO with discrete action space. Quite a few teams have very interesting algorithmic design to improve or robustify their methods. For example, LPAAS team use extensive image augmentation on the RGB space while regularizing the Q function to have similar prediction. The LPACSI team use explicit pedestrian detection and localization module with YOLO v3 and a force model that learns to balance pedestrian avoidance and goal seeking. Moving on to more analysis of quantitative results, we're glad to see that there's fierce competition among participants during the final test phase. The main metrics shown on these plots of the leading team are only 2-3% apart from each other. Some teams are better off in terms of SP or STL, while others perform better in effort efficiency or personal space compliance. And we observe that the teams that strike the best balance between different metrics emerge as the top winners. Finally, we will take a look at the qualitative results for each track. In the following visualization, the robot will be represented as the blue circle, the goal as the green circle, and the clutter objects, and later on the pedestrians as the red circle. First, we will show 2 successful episodes in the interactive navigation track. In both episodes, the agent is able to push away one or more clutter objects, and that is blocking the way, and finally achieve success. Then we show 2 failure cases due to timeout. In both episodes, the agent is a bit overwhelmed by the number of clutter objects that is blocking the way. It ends up either wandering off into the wrong room or getting stuck when trying to push multiple objects simultaneously. And in both cases, they fail to retract and correct its past mistakes. Next, we move on to social navigation. First, we will show 2 successful episodes. Just note that the pedestrians are represented with the red circles. In the first episode, the agent almost hits the pedestrian, but it is able to turn left on time to achieve success. In the second episode, the agent is a little bit more conservative, moving in very low speed when multiple pedestrians are around, and even back up when necessary. However, once the path is clear, it goes straight to the goal without hesitation. The next 2 failure cases are due to pedestrian collision. In the first episode, the agent tries to sneak between one pedestrian and the wall, but unfortunately ends up colliding with that pedestrian. In the second episode, the agent actually hits the pedestrian when it is backing up from the wall. This becomes a debatable question whether it's the robot's fault, actually, because its RGBD camera cannot see anything that is in the back. The next 2 failure cases are due to timeout. In the first episode, the agent didn't know what to do around these many pedestrians in the hallway and decided to take the wrong turn into the wrong room. In the second episode, the agent was forced onto the wall by a pedestrian because it is trying to avoid that pedestrian. However, it got stuck there and wasn't able to take a right turn from there. Right, after the analysis of the results, here are some of the key takeaways that we think might shed some light on future research in robot learning for mobility in dynamic environments. First of all, navigation in dynamic environments is still far from being solved. Dynamic objects are very challenging because the agent needs to balance between obstacle avoidance and goal seeking. Our participants' policy tend to be more on the conservative spectrum and didn't attempt to interact with the clutter objects as much as they should to achieve higher success rate. Dynamic agents are also super challenging because theoretically speaking, the robot really need to understand humans' intent and predict their behavior. Most of our participants' policies, on the other hand, use more of a reactive and model-free approach by training with negative reward when the robot gets too close to the pedestrians. We're interested in learning how these methods will compare against more of the model-based approach that has prediction, planning, control in the loop. Secondly, we believe that simulating pedestrians is super challenging. Although we make a significant first step to incorporate photorealistic humans into the iGibson 3D environment, there's still a lot that needs to be done. For example, currently our pedestrians are just walking around in the scenes. It will be very interesting to model realistic human behavior in their homes, such as talking in a circle, sitting on the couch, or interacting with home appliances. It will also be interesting to simulate realistic human motion with their limbs moving around, for instance. And we have already seen many exciting research along this line in the computer graphics community. Finally, designing metrics for interactive and social navigation is tough, mainly because in these dynamic environments, it is typically a multi-objective optimization problem. The robot should try to achieve the goal with the shortest path or the minimal time, but also it shouldn't destroy the house or harm the humans. We made our first attempt in designing these metrics in the challenge, but we are still constantly thinking about what would be the best metrics for these dynamic scenarios. Finally, I would love to thank all my colleagues, the co-organizer of this challenge. I also want to say thank you for all the participants again for the time and effort they have put into this challenge. We look forward to seeing you all next year. Thank you for your attention.
Hi, I am Shivansh, and in this video, I am going to talk about the multi-on challenge. Multi-on challenge is based on the task of multi-object navigation or multi-on. In multi-on, the agent navigates to an ordered sequence of objects inserted inside a photorealistic 3D environment. The objects are sampled randomly from a set of 8 cylinders with identical shapes but different colors. In the episode shown here, the agent is tasked to first go to the green goal and then to the red goal. Multi-on is a natural extension and generalization of the single goal object navigation task. Since we insert the objects in the environment, multi-on freely allows to control the complexity and length of the task. In each episode, the agent is initialized with a random starting position and orientation in an unseen environment and provided a sequence of goal objects to navigate to. The agent must navigate to each object in the sequence in the given order and indicate the discovery by calling found action. The agent has access to a noiseless RGB sensor and a noiseless depth sensor. It also has access to a noiseless GPS and a noiseless compass. We use the Matterport 3D scenes for our challenge. These scenes are rendered using the Habitat simulator, which supports efficient simulation of a large number of 3D datasets, including Matterport. The embodied agent is a cylinder of radius 0.1 meter and height 1.5 meter. At each environment step, it can take one of 4 actions: move forward by 0.25 meter, turn left by 30 degrees, turn right by 30 degrees, or call found. Calling the found action incorrectly terminates the episode. We base the multi-on challenge on 3-on tasks where the agent has to navigate to 3 target objects in each episode. We have 50,000 episodes per scene in the train split. For evaluating the challenge entries, we use 3 dataset splits: minival, test standard, and test challenge. The minival split has 25 episodes which were publicly released prior to the start of the challenge. This phase is meant to be used for sanity checking the results for remote evaluation against the local evaluations. The test standard split has 1,000 episodes which were not publicly released. The results of this phase are used to prepare the public leaderboard. The test challenge split has 500 episodes and these were not released publicly as well. This split is used to determine the winners of the multi-on challenge. We have 61 scenes in the train split, 11 scenes in the minival split, and 18 scenes in the test standard and the test challenge split. Test standard and test challenge splits share the same scene. Here we plot the distribution of episodic geodesic distance on the test standard split. It can be seen that multi-on episodes have long trajectories. For evaluation, we use success and SPL as metrics. Both of these are widely used for evaluating embodied navigation agents. Success simply measures the proportion of episodes successfully completed, while SPL also measures the efficiency of navigation in successful episodes. We also use the progress and PPL metrics, which are the multi-on analogs of success and SPL. The multi-on challenge winners are based on the PPL metric. All these metrics range from 0 to 100 and higher is better. Here we discuss our baseline agents. First is the NoMap agent, which processes RGBD observations, object goal information, and previous action, and passes it through actor and critic heads to obtain action and value function. Second is the Proj neural agent, which builds and uses a semantic spatial map in addition to the NoMap agent architecture. Both of these are trained using the PPO algorithm. Here, we briefly discuss the challenge infrastructure. Multi-on challenge is hosted on EvalAI, an open source platform for evaluating and comparing machine learning and artificial intelligence algorithms. Participants implement their model in Docker images and submit it to EvalAI. The Docker images are then evaluated on our evaluation servers and the results are sent back to Evalia. 6 teams participated in various phases of multi-on challenge. Out of those, 3 teams submitted to the challenge phase, which is used to determine the winners of the challenge. We received a total of 126 submissions to all phases. Now it's time to declare the challenge winners. The first place goes to Team Leon, Mapping and Spatial Reasoning. They achieved PPL equal to 44%. Team Leon is led by Perry Massa from INSA Leon. Their method uses auxiliary tasks to learn mapping and spatial reasoning. They build on top of the cross-neural map baseline from multi-on work. Their method performs 3 auxiliary tasks in addition to action and value prediction. These help the agent build a more useful representation of the environment and as a result perform much better than cross-neural map baseline. The second place goes to Team Scholam with PPL equal to 38%. This team is led by Chuno Kim and uses simultaneous goal localization and mapping to build an effective map representation of the environment. Their method builds an occupancy grid map by back-projecting the 3D coordinates using the input from the depth sensor. It also builds a separate goal map to store the location of goals seen during navigation. Conditioned on whether the goal was already seen, the agent either goes towards the goal using the goal map or continues exploration using the occupancy map. Here is the test challenge leaderboard. First place is held by Team Leon, second place by Team Scholam, and third place by Team Wimp. Pertinently, the order in the leaderboard remains unchanged no matter what metric is used. Here we look at PPL and SPL on test standard phase. There is a significant performance gap between the first and the second participant and also between the challenge entries and the baselines. When we make qualitative comparison between the no-map agent and the mapping and spatial reasoning agent, we observe that the latter is much better at efficiently exploring the environment. The no-map agent inefficiently explores and eventually fails to find its goal object. Mapping and spatial reasoning agent, on the other hand, explores efficiently, looking from room to room until it finds its goal. In the episode shown here, the no-map agent, even though it has seen the second goal, does not come back to it. The mapping and spatial reasoning agent, on the other hand, returns to the second goal, having seen it earlier and remembered its location. This demonstrates the advantage of having a useful long-term memory representation. Here are some of the takeaways. All the challenge entries use some form of map memory and they perform much better than baselines. This suggests that maps can be a promising direction to explore in the near future. Efficient exploration, better perception, and backtracking is what distinguishes a good agent from a bad agent. We nudge the community to think in these directions to advance research in embodied AI. Lastly, there is a lot of scope for improvement as even the winning entries achieve PPL of 44% and SPL of 35%. We would like to thank the Embodied AI workshop organizers and other challenge organizers for coordinating on challenge timelines and specifications. We would also like to thank Evalia team, especially Rishabh, for hosting the challenge and for helping us resolve various issues in the way. Lastly, we would like to thank the Habitat team, especially Eric and Alexander, for making this challenge possible. We would like to thank all the challenge participants for taking the time to participate. We were very impressed by the performance of participants and want to congratulate the winners for setting new benchmarks on the multi-on task. We hope that insights gained from this challenge will help further advance the research in embodied AI. Thank you.
Hello, my name is Jacob Krantz and I am a PhD student at Oregon State University. I will be introducing the Room Across Room Habitat Challenge, hosted at this year's Embodied AI workshop. I will present the task, results, and share what we learned about this difficult language-guided navigation task. In the R-Cross-R Habitat Challenge, An agent is placed in a previously unseen, simulated environment with the goal of accomplishing a vision and language navigation task. The agent is given a natural language instruction, such as, take a left and go down the hallway, turn into the bedroom on the left, and stop at the foot of the bed. This instruction describes a path through the environment, which necessitates grounding language in the visual scene and reasoning jointly about vision and language. The agent then must follow this path, given a discrete action space of left, forward, right, and stop actions. We also allow the agent to manipulate the camera with look up and look down actions. Contributing to the difficulty of this task is that the agent must operate from ecocentric vision alone. At every time step, the agent receives a forward-facing RGB and depth frame. Active perception is required for the agent to gain information about the environment. We instantiate the agent in a 3D scene reconstruction from the Matterport 3D dataset. These reconstructions provide unconstrained agent navigation that reflect the continuous nature of navigating in the real world. Such realistic difficulties include colliding with objects, getting stuck in tight areas, and visual occlusion. We run these simulations with the Habitat Simulator, which also powers 3 other challenges at the Embodied AI workshop. The dataset for our challenge is the Room Across Room dataset, or R-Cross-R for short. R-Cross-R is a recently released vision and language navigation dataset with instruction path pairs spanning 60 scenes in the Matterport dataset. R-Cross-R has many characteristics that make it compelling for both the training and evaluation of instruction following agents. It contains 16,500 navigation paths, supporting 126,000 instructions over 3 different languages. The dataset also contains time-aligned pose traces that detail when and where the annotator was looking while giving the instruction. In comparing R-Cross-R to an existing popular VLN dataset, the Room-to-Room dataset, we see that R-Cross-R has an order of magnitude more paths, is multilingual instead of monolingual, and removes the shortest path prior of room-to-room. The shortest path prior is the understanding that every path in room-to-room travels the shortest distance between start and goal locations, like in this example. However, room across room samples more challenging paths, as shown here. As you can see in the last diagram, R-Cross-R was created within navigation graph environments. This means that agents navigate by teleporting between adjacent nodes. To make the R-Cross-R dataset compatible with continuous 3D environments, we follow the conversion process for vision and language navigation in continuous environments. This includes porting all nodes in the navigation graph to positions in the reconstructed navigation mesh, pruning episodes with nodes that cannot transfer, and pruning episodes that an Oracle agent cannot successfully navigate. This yields the converted R-Cross-R habitat dataset, complete with its own test challenge split, accessible only through the leaderboard. The R-Cross-R habitat dataset is now the largest VLN dataset for continuous environments, with nearly 90,000 instructions. For the simulated embodiment of this agent, we synchronized with the Habitat Object Nav Challenge and modeled the agent after a zero-turn radius localbot robot with an Intel RealSense camera. Some of the relevant configurations are shown here, such as the agent's height and radius, the camera's horizontal field of view, and collision sliding. When sliding is enabled, actions resulting in collision make the agent slide along the wall or object for some distance. Disabling this video game-like simulation feature makes collision avoidance more important. To evaluate agents in the R-Cross-R Habitat Challenge, we choose the primary metric to be Normalized Dynamic Time Warping, or NDTW. This metric computes the path alignment between an agent's path, labeled Q, and an Oracle ground truth path, labeled R. An ideal agent would maximize the expected NDTW across all episodes with a score of 1.0, indicating perfect path alignment. We use NDTW as the primary metric because R-Cross-R does not have a shortest path prior. We care more about an agent's ability to follow a path than its ability to reach the specific endpoint of a path. We include a suite of secondary metrics, both success-based, including SR, SPL, and SDTW, and descriptive, such as path length. To establish baseline performance on the R-Cross-R habitat task, we train a pre-existing cross-modal attention model based on the reinforced cross-modal matching model in VLN. We feed this model pre-computed BERT instruction embeddings provided in R/R. The model itself uses single modality encoders, tracks visual history with a GRU, uses the visual hidden state to attend to instruction features, uses the attended instruction features to then attend to spatial attention, and finally passes through a second GRU to predict an action. We use teacher forcing to train this model, which learns to clone the behavior of the oracle. We train our model on monolingual episodes, which leads to having one model per language. For evaluation, we merge the predictions into a single submission. We submitted this model to the leaderboard back in March. It earned an NDTW near 31 and a success rate near 14. The official submission window closed at the end of May. We had several teams participate in the challenge and work hard at developing new models. However, the baseline model proved hard to beat. As such, the leaderboard received one official submission. The team named Player 1 submitted their model Zorro, which was multilingual by training and evaluating on all languages jointly. Zorro involved separate RGB and depth language attentions. It was trained with a progress monitor loss and a scaled stop action loss. Here we look into the performance of the baseline model on the unseen validation split. We find that performance across languages is similar, with a range of less than 2 NDTW. We also run an evaluation with sliding turned on. While sliding increases performance, the magnitude is not substantial. As a community, we have a long way to go on this task. Looking forward, we can work on generalizing ideas in VLN to continuous environments and mitigating the computational cost of current methods. I would like to thank everyone who participated in the challenge, my fellow challenge organizers, and all the organizers at the Embodied AI workshop. While the official challenge is over, the leaderboard remains open. I encourage you to bring clever new ideas, check out the starter code, and compete on the leaderboard for the top spot in this difficult task. Thank you.
Hi, in this presentation I will discuss the two 2021 Embodied AI challenges held by the prior team at AI2. These two challenges include object navigation within the RoboThor environment and visual room rearrangement in iThor. RoboThor is a platform designed for research in simulation-to-real transfer. With this target, our team designed RoboThor so that there is a distinct correspondence between real-world rooms and scenes in simulation. RoboThor includes a large variety of different indoor scenes with varying layouts and objects. Our simulated robotic agent is modeled after the popular and relatively inexpensive Locobot. While the pandemic has stymied our initial plans of allowing external researchers to test their simulation-trained agents in our real scenes, we hope to resume this direction shortly. Our iThor environment was built prioritizing complex interaction while abstracting away some robotics complexities. iThor supports realistic physics, object manipulation, object state changes like opening and closing cabinets, and even multi-agent collaboration. We will first discuss our object navigation challenge within RoboThor. In Object Nav, the agent is randomly initialized within a scene and given a goal object category. In this example, a TV. The agent must then explore the environment until it finds the object of the given category. The agent is considered to have successfully found the object if, when it takes the stop action, which ends the episode, it is both sufficiently close to the object and the object is visible within the agent's camera frame. Our challenge includes 85 unique scenes within RoboThor, with 60 reserved for training, 15 for validation, and 10 for test. These scenes include diverse wall and furniture distributions, over 700 distinct object categories, and 12 goal target categories. These objects are distributed across the RoboThor rooms, and there are many unique object instances for each target object category. As noted previously, the RoboThor agent is based on the real-world Locobot, equipped with RGB and depth sensors. For realism, we simulate actuation noise using data from real-world experiments. We encourage anyone interested in object navigation within RoboThor to try it themselves. Installation is easy. We use sensor and action configurations compatible with other frameworks. We have extensive starter code and pre-trained models built using the LN-ACT framework. And while our 2021 challenge has concluded, we have a persistent leaderboard where you can submit your models at any time in the future. The winner of our 2021 RoboThor challenge is the ICT Action Boost model from Bai, Zhang, Li, Song, and Jiang at the Institute of Computing Technology at the Chinese Academy of Sciences. This submission introduces a lightweight Action Boost model that can be quickly fine-tuned upon existing baselines. In their experiments, the ICT team identified several challenges, including training RL models with limited computational resources, using object detectors within simulation, and sharp performance degradation when using models trained offline in the online setting at test time. Next, we move to our iThor rearrangement challenge. In our visual room rearrangement task, there are two distinct stages, a walkthrough stage and an unshuffle stage. During the walkthrough stage, the agent roams around the scene and views objects in their goal locations. During the unshuffle stage, we start by temporarily removing the agent. We then change the state of between 1 and 5 objects. For instance, a cabinet may close and the bread may change in position and rotation. The agent is then placed back at its same starting position. Its goal is now to interact with the environment such that it undoes the changes just made. Note that the top-down image shown here is purely for visualization purposes. In practice, agents see only first-person, egocentric RGB images. For this challenge, we generate a dataset containing 10,000 rearrangements across 120 unique rooms with over 1,200 object instances that may change openness and over 1,800 object instances that may change in position and rotation. We have two challenge variants. In our two-phase challenge variant, the agent must first complete the walkthrough stage before going on to do the unshuffle stage. In contrast, in the easier one-phase variant, the agent need only complete the unshuffle stage and is then given at every step the paired image that would be seen at its location in the walkthrough stage. Here, the corresponding walkthrough image shows the laptop on top of the table. The agent can then use this information to place the object in the correct position. As with the RoboThor challenge, it is easy to get started with our rearrangement challenge. Installation is easy. We have extensive starter code and pre-trained models, and you are free to submit to our leaderboard at any time in the future. Finally, our 2021 challenge winners. Unfortunately, no one is able to beat our active NeuralSlam-based baselines. This suggests that our rearrangement task is quite challenging and that our baselines are surprisingly strong. We encourage you to try your hand at beating our models. Thank you very much. Hello, everybody, and welcome to the Navigation Challenge Q&A panel. We have the great opportunity to welcome some great organizers for these different challenges. So first, we're going to begin with just some introductions by them. So why don't we start with Shivansh, representing Multion. You just give a quick review of your background and yeah.
Yeah, hey, I'm Shivansh Patel. I'll be joining UIUC CS PhD this fall. I was the challenge lead for Multion, where we had a task where the agent had to navigate to multiple objects in a row, in a sequence. And this is very closely related to the navigation problems and memory, where the agent has to come back to things it has seen. So, yeah.
Great. Can we next go to Shangshu?
Hi, everyone. My name is Shangshu Eric Lee. I am a PhD student at Stanford Vision and Learning Lab. I am one of the co-organizers for the iGibson Challenge 2021. This year, we tackle interactive navigation and social navigation in which the environments that the agent is in is dynamic.
Great. Next is Matt.
Hello, I'm Matt. I work at the Allen Institute for AI on the prior team, and I'm also at UW. So I'm representing AI2 Thor and the RoboThor Object Nav Challenge.
Fantastic. Alexander?
Hello, my name is Alexander Maximitz. I'm a research engineer in Facebook research, working on Habitat and Embodied AI research in FAIR. And yeah, today I'm going to represent Habitat team and the Object Nav and Point Nav version 2 tasks that we proposed. Thanks.
Awesome. And then last but not least, Jacob.
Hi, everybody. I'm Jacob. I'm a PhD student at Oregon State University, and today I'm representing the R-Cross-R Habitat Challenge, which is a vision and language navigation task. And we want to give our agents natural language instructions, and they can follow those paths.
Cool. So we're going to start with a wonderfully controversial, perhaps, or aggressive question. So it's sort of two different questions that came in through the Slack. So first, navigation seems like a relatively easy problem. Why isn't it solved? And then also, it seems from the DDPPO paper that navigation has been solved already with greater than 90% SPL and greater than 95% success. Why do we care about navigation? And so I'll open the floor to everybody.
I think models tend to be able to pretty much solve tasks or navigation tasks in environments they've seen and trained on. Generalizing to different unseen rooms and different unseen houses is still quite difficult. And I think a lot of this work is being done right now just to try and get that to work better. But I think that's one of the key challenges still.
And a lot of the past success in navigation seems to be on this clean and static environments in which the robot isn't really interact within the environment. And it has, in the previous Habitat Challenge, it's assumed that localization is perfect, but this year obviously changed. I think there are certain assumptions that we are making when we said that we have achieved over 95% success rate there. And finally, we don't forget there's still the sim-to-real gap. So when you deploy the policy training simulation, there are some gaps in dynamics on the floor or the carpet, and there's a bunch of stuff that are not modeled very well in simulation.
To add to that, DDPPO is trained on the task of point nav, which is a simpler task as compared to what we want to see in real world, something closer to object nav or instruction following.
Okay, cool. I'm going to jump onto that, what Changshu had mentioned, sort of, we don't model a lot of things correctly, potentially, right? We have the sim to real gap. And so I guess one of the questions that sort of comes out of that is, how important, or what are the steps we really need to take to narrow the sim to real gap? Is the lack of high fidelity visual observations the issue? Do we need better physics simulations? Do we need to actually explicitly model the difference between hardwood floors and carpets, or is there some other approach we could take? And I guess, I'll start with you, Eric, if you brought it up. So I'm gonna push.
Sure, of course. I think I think we do not need to simulate the exact dynamics because that's extremely hard. And also, even if we can do that, it's going to make the simulation extremely slow, which is very unfriendly for RL. Therefore, I kind of agree with what Drew said on the Slack that some of the more control side of things can be tuned on the lower level controller level, essentially. When you're conducting real world experiments, you can do some tuning from a limited sets of real world experience rather than hoping you could really do domain randomization perfectly in simulation. So there are definitely a lot of work in domain adaptation and SysID, for not just real robots, right, but also for those kind of lag robots, which is even harder for Sim2Real. So I still think there's a bit of adaptation you need to do eventually, no matter how accurate the simulation was.
So I know within the, so talking about adaptation within the RoboThor environment, there was some push to be able to actually, do some training and testing and whatnot on actual rooms, right, that are very similar. And I think Habitat did some similar work. So you could talk a little bit more about that. I know a lot of these plans were stymied because of COVID, but is the sort of next goal that we actually, test our models on actual environments that have been trained in real ones?
I think for navigation tests, at least, it's surprisingly not as bad as you'd expect from sim to real, at least if you match like the environments and do these type of things and even have domain randomizations. But for interaction, I think it's still wildly difficult to even simulate that type of stuff and especially match that in reality, which is even in line with like interactive navigation and stuff like this. It's hard to do that and match what you have in simulation with reality there.
Yeah, I wanted to add that, we have a paper that is comparing a sim to real transfer. And as Matt said, it's not as bad as you would expect, as well as for this year, we had point now version 2 challenge, especially for answering this question. What will happen if we'll have more realistic noise on actuation and on sensors, RGBD sensors and so on. And I'm really surprised that with 2 years, we get close to where we can replace odometry with visual odometry. And that can bring you to the space where you don't care much about slippery of the floor as soon as you can localize your robot well, right? So you definitely want to train it with a good, even possibly more significant noise what you will have in reality. But if your visual transfer is acceptable, then possibly you can leverage your odometry and localization that you trained in simulation.
Cool. So maybe changing gears a tiny bit. It seems that a lot of the challenge submissions, sort of outside of maybe room to room, don't use much imitation learning. And so I first want to ask, in room to room, why is imitation learning important? And then sort of open it up to everybody else. Why don't you use imitation learning? What's going on here?
Yeah, it's an interesting observation. In the R-Cross-R challenge, we're using imitation learning for one, because the sample efficiency. When doing straight reinforcement learning, these agents need to see a lot of steps of experience before they can learn to ground language and vision together in order to accomplish these tasks. Whereas if we can use straight imitation learning, say behavior cloning, we can use these high quality data samples from our data set. So that is a benefit there.
I guess along those lines, do you think that you'll be able to use pure RL methods for RxR, or is it, imitation is the only way?
Yeah, we definitely want to move towards reinforcement learning because imitation learning can have some hindrances to it. For example, an agent is not able to learn the consequences of their own actions. Even when you're training with dataset aggregation type methods, Dagger, the agent is always being supervised
with what an oracle would do at that exact given time step. Whereas in reinforcement learning, an agent can take a sequence of actions and figure out what the result was from taking that long sequence.
I want to comment on imitation learning as well, because with Object Nav Track this year, we have interesting entry from Habitat on Web team, which is actually train their solution using imitation learning. But the difference is that if you take Object Nav, your agent should go where the particular object of particular class. And usually you don't know it because it's unseen scene. And that means that it should be some exploration. If you just take a sequence that will actually be shortest path to the goal, your agent will overfit to existing trajectories a lot and will not learn to explore. But what Habitat on Web participants did, they actually captured the human performance with exploration phase and then use imitation learning for these sequences. And with a short amount of the sequences, like several thousands, they were able to reach not the best performance, but still reasonable. So I think it can be kind of connected with some other approaches and get better results. But this is interesting observation that it can help.
We've seen similar patterns in the VLN space where imitation learning can be combined with reinforcement learning, and ideally seeking to get the best of both worlds.
Just to add to that, initially I thought it's easy to provide imitation learning data for navigation because you have the ground truth, right? Like you can compute the shortest path. There's an analytical solution. Then I realized, I think it was mentioned, there's a good point that when the agent is initially in the scene, it has less information, right? Like it doesn't know where the goal is. So there is this exploration phase. And I'm wondering, maybe one way to imitate is let a real human to provide demonstration in a virtual environment where the real human also doesn't know where the goal is, need to find the door or find the object, the exit. I think that would be interesting. Although the challenge there is that I think human demonstration is very, very noisy and suboptimal. So how to train a policy based on that is another challenge of itself, I think.
Well, so I think still on that sort of Dagger sort of, I guess, mindset, it seems like a decent number of people sort of initialize with, or a reasonable strategy might be to initialize with Dagger and then sort of gradually move to PPO, right? You'd hope that kind of get the best of both worlds. Have you had any experiences with that, or these sort of warm start approaches for imitation learning and moving to PPO? I guess this is a totally new ground. No one has tried this within the space of navigation. This is going to be our next paper using DDPPO and Dagger together. Cool. So yeah, one question we got in the chat just really recently. So there seems to be a big disconnect between the robotics and navigation communities. Robotics tends to operate within the same environment for a very long time. In our communities, we sort of tackle each test environment brand new every time, right? Will methods developed for this short-term sort of instant case have uses in the sort of long-term environment that I guess multi-on is sort of getting towards? Are we valuing the wrong things? If we have to see the environment new every time, then maybe the advantages of maps aren't really quite as apparent. Any thoughts?
Yeah, I think even if we have, even if the robot operates in the same environment for the first time, it has to, when we keep it into a new environment for the first time, it has to do the task at least once. So always the bottleneck would be the first time the agent does a task in a new environment. So it is not that bad because we are still trying to nudge the bottleneck rather than trying to solve the whole task.
Yeah, I think it's an important question because my feeling is that it's something that is like actually different from how we expect to have intelligent assistants in our house to work. Because like you don't expect them that they should work perfectly in unseen houses. You just initiated them. You are okay with the mapping phase, right? And then if it works better. So it's a little bit less realistic, but I think intent was like that. If you can learn something that can generalize to unseen environments, definitely there is no way that is overfitted to existing environment, and that's only just some subset of features are important that is not kind of generalizing well. So I think we should as a community think about the task where you perform a set of things in the same environment, but again, you don't have luxury to train in an environment that you are going to be deployed usually. So this is not going to happen. It can be a phase of your evaluation that you have like pre-exploration phase or something like that before.
It could be an interesting challenge to try to close the gap and have a SLAM system, for example, learned or traditional, where the challenge is, can you map the environment well enough that you can transform the object nav problem to the point nav problem to known locations? And like that, it seems like a well opposed problem. And I know there's a semantic SLAM in the next session, which maybe they have something to say about that. But it does seem like, what we do now is a useful first step towards that. But if we want to follow the speculation in the question and see that that's actually a problem that the community could tackle.
Yeah, I like this idea. Yeah, and another possible view on this can be, if you have an episode in one scene, can we just evaluate it that you still have a memory across this episode and you expect it to perform on the last episode better than on the first set of is your model improving with operating in the same scene? This can be also interesting behavior and challenge to see how good our models are in that.
Yeah, I definitely agree with what is said above. And just to add to one interesting note, last year we actually did this experiment with the iGibson challenge last year, where this the sim to real part, right? So what we did is we rent a real apartment, and then we take a Matterport scanner, we scan it and put it in iGibson, so people can train in that apartment, and then just to handle the sim to real part, not generalized to new apartment kind of generalization. But that's kind of interesting. So maybe that's something we could do in the future when we buy a new home robot. We first scan our homes, right? Currently we have mobile phones that can do that. We upload it to whoever who produced the robots, and actually, let the robot and overfit to that scene, and then ship it to your home and do a bit of tuning in the real. And maybe that works. Maybe that's a new avenue that we can try. I don't know.
I think there's a slight limitation to that approach. So suppose we're able to completely map somebody's home or environment. We send them their robot and they do home renovations. There's some sort of dynamics that change about their environment. That's where we go back to this gold standard of how well can a robot do in a novel environment. And we can use that to be able to guide progress on when an agent is encountering something novel, something dynamic, new in this environment.
Great, cool. So in the live Q&A that we had before with the speakers, Chelsea Finn noted that we were basically throwing away all of our data after every project, right? And this isn't quite as true maybe for the embodied space, because you're not throwing away the evaluator, and it's at least we're not doing that, or we're not throwing away the simulator, so at least we're not doing that. But at the same time, I think there's a pretty clear parallel in that people will train their model, their brand new great mapping model in one environment, and then claim victory and then move on, right? And so what really seems to be missing is that we don't have any sort of joint training or evaluation across all these different tasks and environment, despite the fact that only speaking for myself, we put a decent amount of effort into making sure that the actions and cameras and everything was relatively the same between all these different environments, right? So, what is missing? Why don't people train and evaluate their models across the spectrum? Why doesn't somebody train their model in Habitat and test it in iGibson?
at least from an implementer's perspective, I don't think there's really a compelling reason or much of an incentive to. This reminds me a lot of like the paper from about a decade ago on unbiased look at dataset bias, where you can easily tell an image is from AI2 Thor, or it's from iThor, or it's from RoboThor, or it's from iGibson or Gibson or Matterport 3D. And these are really easy to do. And then once you try and train on iThor and evaluate on Gibson, this is not going to get great performance. And why report it if it's just going to be bad?
Yeah, I completely agree with that. And I also think that the overhead of trying it on different simulator is a lot harder than, for example, in the computer vision community, try on different data set where you can just download different data set and try the models. I think right here is, I think we should do that. It's just that I felt like people, like there's different, like people need to learn to use different simulator in order to do a good job of cross-platform evaluation. I think something that we can still further work on in the future. I think we should move towards that.
Yeah, recently it was a part of the project when we tried to have the same model like learned in one simulator and evaluated in another. And I think there was a case before as well. So usually there is, distribution changed a lot. So this is a main reason, right? You have a simulator, even like when you hide or like some little parameters, floor height, there was a difference in Gibson and Habitat, even for the same scenes, there was this difference that incorporated like loss in performance in the end of the day. So it's different. I think maybe we should work on some protocol. Like, okay, it's hard to set up the environment if you're training in one environment and another and connect it. Maybe we can collect some like sequence of, as we talked about imitation learning, some data set that will be as simple as a vision, just images and some information that will give an option for you to fine tune your solution and get your model from one simulator be acceptable for another, something like this. And we have definitely like projects that do more of this cross simulation submissions to understand it better. But that will be valuable because, as I mentioned, for example, for object nav in AI2 Thor, we would be happy to participate, but categories are different. We need detector for this new simulator trained. And if this will be answered, like detector is presented, so we can just abstract in terms of categories and maybe some mask where there's object, it will be easier for us to participate. Something like some additional artifacts that will help transferring one sim to another, that will be amazing.
Luca, can I follow up with a question at this point?
Go ahead.
By the way, thank you all for your answers. I was listening to you folks on the live stream, and I thought I'd ask this question. So there's an interesting documentary on Netflix about black holes, and they cover one of the projects called the Event Horizon Telescope Project, which is an international collaboration between multiple teams. I think it's like 20 different countries, and it's over a decade-long project where they actually had to go to. The goal was to create the first photograph of a black hole. In order to do that, you need an Earth-sized telescope. You cannot construct an Earth-sized telescope, so you go cover the hemisphere with multiple telescopes and try to solve the sparse reconstruction problem. The interesting bit to me was watching the coordination between multiple research groups, multiple countries, multiple funding agencies, and ultimately they wrote, you had to establish sites at multiple countries, you had to collect data, you had to work together, and you had to solve all these socio-political problems where you want to make sure everybody's heard, you reach decisions by consensus, you write a common paper, you make sure everybody's on the same page, even though, of course, we're all humans and we have our own interests and various dynamics going on. So my question to you folks is, given the fact that we're just discussing training in one simulation, testing in another simulation, what is the EHT equivalent for embodied AI? You each represent a different team with its own interests and dynamics at play. what's that grand goal where we can leverage the unique skills and strengths of everything that you bring to the table? And we can hear from anyone on the panel.
So for real world deployment, especially in things like RoboThor, I think it's much more necessary to be able to collaborate with other groups who don't have access to such resources. But for simulation, I don't necessarily think it's that difficult to, I guess, build your own simulator or even leverage open source ones and build your own tasks with them, which kind of leads to this having like 15 different standards for how these tasks should be done.
I think there's a question of how we want to align ourselves. One way is we could align ourselves bottom up by saying, okay, we have this set of tasks. Let's each align ourselves, these different simulators, with similar embodiments, similar definitions, so that we can transfer these agents. Or if we take the top-down approach, we can say, what is some task that we want to align a community around, and go that bottom down and say, what are these component tasks, and build from there and align ourselves towards a goal, and then build out our infrastructure together in pursuit of said goal.
Yeah, so I think adding on to what Matt said, there seems to be this, or maybe a need for some sort of standards body, right? Maybe we need to come together and really sort of formalize and figure out precisely what the goals as a community we're chasing after are, and how do we specify these tasks in a very precise way that makes this transfer sort of incredibly easy. So like, everybody needs to have an object detector trained in their environment type of deal. Yeah, I mean, this is of course a hard problem. And I think it's difficult to get past the fact that we are a community and we're very collaborative, but there's some competition going on. We're all sort of competing for the same ideas, and I think we need to potentially get past that. Let's not be afraid when we see another group's paper come on archive. We should be prepared, and we know roughly what they're doing.
I like the idea of imagining a grand challenge for navigation, where I think someone called it the gold standard is dropping an agent into a new environment. When you go into a new home you've never been in before, you don't go, right? You explore safely, you learn to recognize objects, and then later you can say, oh, I need to get to the restroom, you know where it is. But then if that's blocked off while they're doing renovations, you know to change. And we could design the scope of a grand challenge, say like, here's looking at deploying a robot navigation stack on a new class of robot in a new kind of environment. And it would go from being a kidnapped robot, not knowing where it is, to a robot that could return you, a map and navigate to a known object very quickly, and then tell you, oh, by the way, that corridor you just sent me down is blocked off because they're renovating. And that general problem could be of great use, whether or not you're an indoor navigation researcher like me, whether you're focused more on responding to sound, whether you're focused more on being in an industrial environment. There's plenty of room for different researchers to tackle that. And if we could come up with that kind of grand challenge and good metrics, then individual challenge organizers and groups could instantiate within that and tackle the parts of the problem that were relevant. And then, might be like, well, I'm not really going to, I do want my own simulator because I've got this distinctive type of robot for this task that I'm doing, but I can fit within this scope and I'm tackling this part of the problem. That might be one way of trying to get that shared understanding that we're progressing without, eliminating healthy competition or eliminating the distinctiveness of each individual problem.
I guess I think we haven't completely formalized that idea, but I would be interested in opening it up and getting people's perspective on what your sort of internal grand goal is. Where do you want to see, or what is this all leading to, right? What's the point of navigation? It has to have some context. What do we want to have out of this?
Yeah, so I first wanted to answer a comment on Drew's question. So my feeling is that our teams are now finding the specialization, right? So we see some particular teams like Gibson, for example, focusing on obstacles during navigation, more dynamic navigation. That's very interesting, and low-level control that is close to robots. Different teams are focusing like still in discrete action space, but much harder task, long horizon. So we start getting our specialization, not like to go with one field with different simulators and just initiate our own task, but still in simulator is a part that everybody is reinventing. And I'm curious what will convince your team to join and say, this is our simulator, we are going to use everyone. It's like MIT license, everybody can fork and work with it and so on. And we are not going to, but there is no like one person that can just ban your decision or something like this, but still we can kind of focus more on research goals instead of all do the same engineering process. So for this, I think first we can learn, come with lessons we learned. We have different challenges, some similar tasks previous year. What was the difference? Why one approach was popular in this challenge and another was approach popular in this challenge? Is actually the simulator difference was causing this, or like one simulation was harder, another was easier, and then still we can just come up to common understanding? Or we still need to have these different simulators to progress and not to be biased to one particular approach or one particular interpretation of the task. Yeah, coming from our Habitat team, we made our best to make a simulator fast, open source, MIT license, free to use, like not locked to particular vendor, and loading different data sets and scenes. And we are open to collaborate with teams that want to load their scenes in the simulator. We would be happy to see this.
Yeah, I also want.
Sorry, Alexander, can I just press? Luca's question was, what's your ideal task? What would you like to see being solved?
So it's a question for me. Yes, I think in terms of a little bit more complicated task, rearrangement task, like clean your room. This is something that is coming with the rearrangement paper. I think is great next task above navigation. In terms of navigation, that's a great question. I think even like for this rearrangement task, robots should navigate in the apartment safely, understanding where there is semantic context for the people, as well as like dynamic social navigation makes sense a lot. Like, and low level is also important. So I think as a community, we are tackling different pieces of that. And then we should start joining it into one like super hard navigation task, which will be great base for rearrangement task, because that's what you need. You need to place your robot in particular location to perform some interaction with environment, not hurt people, and do it in an effective way, not just with discrete actions which are not optimal in terms of time.
Sorry to interrupt you.
No.
Go ahead.
Oh, no. Sorry, I just want to also try to answer Drew's question and also Luca's question. For Drew's question, I think we definitely need a shared benchmark, like what Alexander said. I think it would be really great that we have an offline evaluation, like episode data set that have hundreds of thousands or millions of episodes that can be used across platforms. And ideally, these episodes are very diverse, in terms of RGB sensors in different scenes. I think we have reasonable number of large indoor scenes, right? I think we can do that. Dynamic, if we had to have dynamic agents and dynamic obstacle, that would be even better. But that's something that kind of people can compete, on a year-long basis, like ImageNet, for example. And I also feel like we need to have, maybe we can put our fund together and then create this real-world setup where we can, like Robo4, right? Like you have this idea of everybody can submit their solutions and some people will test it for them. And I think that would be really, really awesome to have something running so we know where's the gap to the real world. In terms of the golden standard, I think for navigation, again, I think diversity is very important. And then one step up will be rearrangement. I think even beyond rearrangement, there are still a lot of other extended object states that are not covered by simple pick and place, right? I think people still, like there are these variety of complexity in the household activities that are not just restricted to pose. For example, there's temperature, there's this the sliceness of an apple, or the dirtiness of a tower, etc., etc. I think that would be an even further level that we could potentially tackle.
Going back to what was said about like evaluating these on the real world with, say, RoboThor, I think one of the big things we found is that it's really hard to do this autonomously, like without a human in the loop. And then even just scaling this beyond one environment at a time is quite difficult. So you pretty much have to have someone there 24/7 to monitor these agents. And that's not really that great of a solution, at least in my opinion.
I guess, yeah, and especially as we move to a more like social navigation type settings, I guess, Jacob, would you have any ideas of how would we evaluate models in the real world when they have like language? Is this something you've ever thought about?
Yeah, I would say evaluating these such language navigation models in the real world, we can start with these static environments where we've already had a study by Peter Anderson et al. Where they did a sim to real transfer for vision and language navigation. We can create these physical spaces and map them into our simulators and use that as our transfer. And we have ways that we can do that evaluation, and we can specify those paths and compute alignments. I have one point to add about the gold standard idea of creating a task amongst everybody. I think that is a very interesting question, especially for this group, given that we each have organized these different challenges that are all focusing on a different sub area. I would like to add to it that how to specify a goal to an agent is an important question, regardless of the actual task that we try to accomplish. And that sort of human-robot interaction is something we should keep in mind as we push forward as a community. And I think that using natural language to interact between the human and the robot is something we need to continue to push forward on as we specify our tasks.
And I know Room to Room, correct me if I'm wrong, but has some multilingual components, but presumably that's also a huge issue. Could you expand maybe a little bit more upon that? How do we get enough data to be able to actually have these assistants work in India or China or something like this?
Exactly. Yeah, we have a monolingual bias in a lot of our data sets to the English language, or even, for that matter, the top 10 languages in the world. And since our systems rely so heavily on vast amounts of data, it's a very big problem when we want to deploy these agents for speakers of other languages that are not as prominent in the world. And so developing systems that apply to other languages is a start, and developing systems that apply to underrepresented languages is an even bigger challenge there, that we hope that Room Across Room can take a first step towards by saying, hey, this is a monolingual data set, and we are going to evaluate on all three languages here.
I have a question for Jacob. So how big is the monolingual bias? So if you have one language instruction in one language, then you can, and if you have a good language translator, then you can effectively say that you have language instructions for all the languages. So how big is the monolingual difference that is causing all the issues in moving from one language to another?
That's a really good question. Yeah, the quantifiable difference, I would have to point you to the R/R paper, where they go into details of trying to use translations. I would add to that people that speak different languages will convey their ideas differently, and possibly look at different ways of providing an instruction to a robot. And so while you could just directly convert a semantic of some instruction, you may have different characteristics of an instruction by different populations that speak different languages.
And Shivansh, do you have any perspectives on what a grand challenge would in general look like in the navigation setting, or just in general? What are we striving for?
For short term, I would say for navigation, I just want my robot to bring the cup of coffee without bumping into anything strange.
The coffee bias is real. Yeah, I know. Okay, great. So that was a very illuminating discussion. I think I'm gonna, unless anybody else has some more to add on that one, I'm gonna move into a little bit of a different, maybe more practical direction. So I think one thing that we've really realized, and Alexander sort of touched on this before, is that to be able to train these agents, big data in terms of variety is great, but even within sort of the same environment, you really need a lot of frames, right? And so simulation speed is sort of critical. And across these different environments, we've all used our own tricks to be able to speed them up. And so I guess I was wanting to hear sort of what your learnings are from that. What are the best ways to sort of improve simulation speed? And what are the big hangups?
Look at the question for me, kind of.
Yeah, for everybody, but let's start with you. Sure.
Okay. Yeah. So in our team, usually we come up with simulate only what you need. So if you are simulating physics, you should simulate only physics around the robot if that's what's important and it's focus of your training. If you simulating graphics before moving to high fidelity and saying that high fidelity is very close to reality, we should evaluate how important is that. And depends on the task, but at least for point nav, it doesn't look that this high fidelity is as much important. It has this high importance for navigation, for example. But for something else, like when humans are interacting and with robot, maybe it's more important. Yeah, so mostly this sacrificing parts that are not important and focusing only on that shows improving performance of your agents.
Yeah, we've also found this to be useful as well in terms of just rendering what you need in AI2 Thor. We've recently had a few big speed ups just by doing that, and then not returning all the object metadata and stuff like this when you don't need it. I also really like this recent paper from Habitat, the team, and where it shares the memory of the simulators, or of the instances of the simulators at once. So you don't have to store different objects for each time you run the simulator. And this had pretty substantial improvements in terms of 10,000 frames per second or something like this. And I'd really like that in AI2 Thor, although it's quite hard, but I think that's a super promising approach.
Yeah, so I think that's when you're touching on this, it brings up this interesting tension, I think, between optimization versus generality or generalization, right? So I can't speak for this most recent paper, but generally, as you try to optimize your speed, your ability to add new features is sort of diminished, right? So if I have local physics, maybe I need a custom physics simulator, and then I won't get any of the nice rendering and things that come out of Unity. So I guess have anybody found that to be a problem? Have you built something for speed that you then realized wasn't flexible enough for something else you needed?
Definitely, what Matt just mentioned is batch rendering. This is a very powerful technique when you have one simulation that is actually looking as a number of environments towards for your training your model. So it's as we are not humans, we have agents. You can have one simulator that is generating multiple views for a number of your agents, but that it's giving you limitation that you cannot do different actions in random time in any of these environments. It should be synchronized in some way, for example, or at least like async, but then again, you don't have this control one-to-one between your agent and between environment.
One other maybe obvious thing to mention is I think the big benefit you get from AI Tutor is that you have this ability to simulate interactions really well, although you don't have this great speed up that you get from Habitat, which is one of the downsides there that is quite annoying.
And one thing that we, the iGibson team encountered is that as we make our scenes fully interactive, we are dealing with hundreds of objects in the scene, not just one static mesh. And how to exactly scale this up without spending time that linearly grow with the number of objects, which is very challenging. And we've spent a lot of engineering efforts into that. And one thing that really echoed is exactly what Alexander said, that there's this object sleeping idea in physics simulator. So if the moving agent can only affect what is surrounding, then all the other objects should go to sleep. The same idea for rendering, like we can, for example, pre-allocated memory that have all the texture maps, and it's just easier to read them. And that will also give us quite a bit of speed up. But yeah.
One question there, how do you decide what to render? Because if you imagine throwing a ball across a room, maybe it hits this object that you didn't anticipate earlier that it was going to be interacted with.
Right. One thing we did, the trick is actually thanks to the physics simulator. So essentially, if they're forced wake up certain objects, we also know that we need to update their poses in the renderer. So we have this coupling.
Luca, can I add a follow-up?
Yeah, you came off, so I was wondering.
Yeah. So here's a way of thinking about simulators, and this is something that I think I'd presented to the Stanford folks in my talk, and I haven't publicly sort of talked about it elsewhere. But there are two ways of thinking about simulators. One is you could think that simulators are like data sets, that they're just the dynamic version of data sets, in which case there is no such thing as a universal data set. It is dependent on your task. And so depending on what problem you want to solve, maybe there will be multiple simulators and they will forever be around. And it means that your prediction for the future should say that as we have more tasks, we will have more simulators. And that's one possible pathway for the future. And the other way of thinking about simulators is that they are frameworks or libraries, or they're like platforms, and they're like PyTorch or TensorFlow. And when you take that view, it becomes pretty clear that the market is almost winner take all or top 2-3 take all, right? The TensorFlow and the PyTorch and maybe one else will survive, and the Theanos and the cafes of the world will be thanked for their thought leadership and their contribution, but ultimately sort of sunset at some point. And the future there is that. Right now, it's not clear to me. Like right now, simulators are like the Schrodinger's simulator. They exist in both worlds. So maybe, in the spirit of falsifiability, we could get people on the panel to predict what do they think about this and where do they think future lies.
Perhaps a bit controversially, I think this is pretty much a winner-take-all situation, just because when you see someone start to use one simulator, they pretty much never change, and they find out that their tasks can, with enough effort, be transferred into this new simulator. Although that's not always the case with some of these simulators that currently only work for navigation, it probably will be at some point.
Any other thoughts here?
But can I just ask, like, so you're pointing at a universal simulator, right? There will be something that will satisfy everybody's need, but it feels like people want to solve many different kinds of problems. And like, do you think there's a universal data set?
No, but I think you can build on top of a simulator to do any other task that you want. I think you're seeing this with AI Tutor with things like ALFRED, where you have these vision and language tasks, or rearrangement, where these are vastly different tasks, but they're not exactly the same data set.
And how about when we have to do clothing, fluids, like fine-grained things? How about when someone wants to, study just sort of human-robot interaction, or something that's so fundamentally different that they find it's easier to start from somewhere else?
I could see this happening, like if you think of an outdoor simulation or a factory simulation where these aren't even in AI Tutor, you're basically starting from scratch. You may have to do this, but at least for the tasks we're proposing and these sort of shared benchmarks, I don't necessarily see that happening as much.
Okay.
I do a lot of work. Our team has done several different simulators, and I do a lot of work looking at cross-simulator work at Google. And without going into total detail, like we've done everything from very simple, the grid worlds in testing, forget those. The very similar, car or bicycle models, dynamic model simulators, which are great for speed. And then we've had higher level physics simulators that we've used. They really aren't as useful for a lot of training, but when you get to integration tests on a robot and want to understand the implications of deploying software on the robot, they become more important. We have had people who had to do, grasping of soft objects, and they used finite element modeling. And the fourth one, my team has not used as much, is high fidelity visual simulation. So there's at least 4 different perspectives you can come at this, and they're not all compatible at the same time. All right, you can't really do FEM or high fidelity physics at the same time as having a very, very fast car model. And what I personally find is that if you are trying to develop an AI algorithm and you have to change your simulator, you'll just spin your wheels. And so it's really important to try to perfect a technique. But once a technique is perfected, and then I want to extend it to a new simulator or a new context, then it's more feasible. So I think that this model, I like the model of like the framework more than I like the the infinite number of data sets, because I think there's a few classes of high fidelity physics, high fidelity visuals, fast, or it really matches my robot. But you could have one framework that enabled you to do all of those different things and have those things talk to each other and say, well, I'm in here, but now I can easily go there. So I think that there's a role for that. But if I was a researcher starting a problem and I did a build versus buy assessment, which everyone should do, and there was no way to, like, for example, like say implement what I wanted, I could see why someone would start with a new one. I would first, I would look at Gibson and Habitat and AI Thor, and I would look at all of them first, though, because I think that a lot of the times people are just simply aren't aware of what already exists. And it's our job as a community to make people aware that you really can do this for many tasks.
Yeah, just to add to that, I think I'm leaning more towards the data set point of view, at least in the short term, because I do feel like, we look at a lot of comparison between different simulators, and I do see that people are different simulators are specializing and good at different tasks and have different capabilities. Some even have different underlying physics engine, right? Like Flax or Unity or PyBullet. They have different rendering mechanism. They have different assets management, for example. Is it buying from Unity store or is it downloading some OBJ files you bought from TurboSuite, for example? And I do think, at least in the near future, as we kind of this field of embodied AI flourish and so many people are tackling on different fronts, I still feel like we will end up with a very great diversity of tasks in the simulator in the near future, at least.
I know I'm not part of the panel. I just wanted to make a comment. I think it's important to also know that there are people behind these simulators, right? So every team brings in a new diversity or new angle towards doing things. And I like how the last two workshops and efforts by a lot of leaders on this group, I see it from the outside. And I enjoy the fact that there are these papers written at every frequent checkpoints where all of these leaders kind of come together and do a conversation, and they write a tech report or a white paper on rearrangement or evaluation of embodied agents or so on. I do feel we're in that from a robotics perspective, and when I talk to people in the robotics side of things, people still feel that our field is slightly new and still evolving. So if we form like a single thread and work together as one big group, there is possibility that we'll not be able to come up with these cool alternate takes at doing things. And that's probably why groups at different universities work separately and not as like one big oligarchy, or monopoly of sorts. And this oligarchy at this stage, or like this few groups trying to do different things and new things, is pretty interesting but I'm not particularly involved with one group per se, but I see it from the outside and of that people are bringing in new factors and new things which they wouldn't probably be able to work on if all of them were a slow-moving, bulky group, I guess. So I'm just bringing in the practical angle that the people behind these simulators, and it could be a data set or a framework, but I think they're also people. So that angle comes kind of interesting to me from an academic outsider perspective.
Cool. So we have a relatively short amount of time left. So before I ask everybody to just sort of summarize your takeaways, maybe I'll quickly ask one last question. You can sort of put a one-sentence answer to it. So over the last couple of years, it seems we've been sort of going back and forth between sort of adding in a bunch of inductive biases to our models, like mapping and things, and then moving towards end-to-end methods. Like now we can do auxiliary tasks and we don't need mapping. And it sort of like, goes back and forth. Where do you see this going, just quickly, in the next couple of years and eventually?
I could start. So one thing that introducing these inductive biases gives us is a way to overcome some data sparsity. I think that once we can scale up our data sets and train our agents on them, we will require less of these sorts of things. And one thing that is encouraging here is that we see blind agents, and they're doing that with these general architectures. And so if we're able to see some of these things emerge in our general methods, we can make them more impactful as we scale up our data.
Cool. I'm going to take that as the summary for everybody. So I'll go through everybody in sort of the reverse order, and you can just give the sort of high-level takeaway that you'd like the audience to go away with. So in reverse order, Jacob.
Okay. I think it's really cool that we were able to get this panel together from people with different perspectives and trying to accomplish different navigation tasks. And so one takeaway that I would like to supply from our cross-R perspective is that navigation can be more than specifying a point to go to, and interacting with a human via natural language. We can specify these continuous paths through environments. And if we can encode our goals via natural language, we can make our agents more accessible to the general population as we look to deploying these agents in the real world.
Cool. Alexander?
Yeah, so for me, a takeaway is like from this Q&A session is that we should explore more like sim-to-sim transferring and the overall like diversify more in different aspects and learn from a task where the tasks are similar in simulations, what the difference of simulations can bring to the task and to the approach, something like this. This is my takeaway.
Cool. Matt?
I think the biggest takeaway is that I'm glad there's a lot of collaboration here between like a lot of different organizations and a lot of people coming at this from different angles, and just the success of simulation, even in the past few years, has been pretty remarkable, to say the least. And I think that's looking to continue.
Cool. Shang-Chu?
Yes, I echo with a lot of the previous speakers, and I think it's really great that we can gather together among so many institutions and synchronize on the task setup and describe what is the simulation difference, why the difference, and reality is just not a simulator, for example. Then what is the difference compared to that? And I think we should really continue doing that, and I'm really glad to be part of this panel. A quick takeaway for the iGibson challenge this year, I think what we learned is that for navigation in dynamic environment, which is a little bit less underexplored compared to point map, for example, it's still an unsolved problem, and it's a multi-objective optimization problem, because you want to achieve the goal with the minimal time, shortest path, but at the same time, you don't want to destroy the scene or be too close to the pedestrians or even hit them, for example. So how to develop solutions and even metrics to measure success is still an ongoing work. That's it.
Great. And last but not least, Shivansh.
Yeah. From my side, the conclusion is not explicitly came up in the discussion, but I think we all are tackling very different parts of the problem, but eventually we have a similar vision and similar goals that we want to deploy robots in the real world. So we should not lose vision of it, because eventually everyone keep asking, hey, what we want to do? This is what we want to do. And right now we are solving small parts.
Awesome. Thank you so much for being here today. It was fantastic to have you. Next, we have the interactive challenge presentation videos and then at 5 p.m. we have the interactive challenge Q&A panel. Again, thank you so much.
Hello everyone, I'm Chen Chen. In this presentation, I'll talk about the SoundSpaces challenge we organized this year in collaboration with Una Jane and Kristen Grauman. Moving around in the real world is naturally a multisensory experience, and an intelligent agent should be able to see, hear, and move. And this motivated us to organize the first challenge on audiovisual embodied AI. More specifically, this year we targeted audiovisual navigation in 3D simulated environments. As the name suggests, this challenge is based on the SoundSpaces platform that we developed recently, and the prize for the winning team is AWS credits worth $5,000 US. Let's first get a taste of the simulation. SoundSpaces is a habitat-based audio simulator and enables audiovisual navigation for two visually realistic 3D environments, Replica and Metapore 3D. In this challenge, we only use a Metapore dataset due to its greater scale. For each environment, we discretize it into grids, and the room impulse response is computed for all pair of points on the grid, as shown in this figure. In the audio Go navigation task, there is a sounding object randomly placed in an unmapped environment, and the agent receives 1 second audio clip emitted from the source at every time step. The agent is tasked to navigate to the sounding object in the environment with one of the 4 actions: move forward, turn left, turn right, and stop. And the success is defined as when the agent issues stop action at the source location. In this challenge, we consider the unheard sound setting, where the model is trained on multiple sounds and tested on unheard sounds. There are 73, 11, and 18 disjoint sounds in the training validation test sets. Note that the environments are also split into disjoint sets, so it requires the model to generalize to both the unseen environments and the unheard sounds. In addition, we created a new challenge test set where the sounds and episode configurations are different from the public test set, and the best performing team on this split was announced the winner. For each episode in training validation and test, we varied the scene, start location, start rotation, go location, and the source sound. After calling the stop action, the agent is evaluated using the success weighted by path length metric. In this year's challenge, we used the audiovisual waypoint navigation model from a recent paper as the baseline. This is a state-of-the-art model on audiovisual navigation, and the code was made public before the challenge. The key idea in AV1 is to learn to set audiovisual waypoints end-to-end at different granularities. In addition, this baseline builds an acoustic memory to help infer go locations and decide stop actions. This year, 7 teams from varying universities queried us about this challenge. 2 teams were able to make successful submissions on the test set. Among the 2 teams, Freiburg Sound outperformed the AV1 baseline by a large margin and wins the challenge. Congratulations. Team Freiburg Sound used data augmentation to improve generalization to unheard sounds. They also find that auxiliary loss on the spectrogram reconstruction improved the performance even further. Next, we'll discuss future directions for SoundSpaces challenge and transition to the presentation recorded by the winning team. This is the first SoundSpaces challenge, and we are glad to receive lots of positive feedback and attention on this challenge. In the next challenge, we plan to add a track for the more challenging and realistic semantic audiovisual navigation task. In addition, we plan to make it easier for participants to participate by enabling the simulator to render on the fly. Also, we wish to test the winning team's method on a real robot in the future. Next is the presentation from the winning team. Thank you.
Hey everyone, it's Abdurrahman Younis, a master student at the University of Freiburg. I'm going to present today our approach that won the SoundSpace challenge. This is a joint work with Daniel Hunakam, Tim Virchohold, and Abhinav Balada. We call our approach mimicking real-world scenarios for better audiovisual navigation. In embodied audiovisual navigation, the agent's goal is to navigate towards sound source in unmapped complex realistic 3D environments, using only audio and RGB depth images. The SoundSpace challenge addresses the problem of navigation to previously unheard sound in unseen environment, as existing approach suffer to generalize well to unheard sounds. We believe that mimicking more complex real-world scenarios in the training process can help the agent to learn the task more effectively. We can mimic a scenario like a crying baby at the same location where the alarm went off by adding a second sound emitting source at a goal location. Another more common scenario like a ringing phone while there are people talking at a different location can be integrated into training by adding a distractor sound at a different location. A third scenario where there is a noise in the audio sensors can be mimicked by applying future-wise augmentation on the binaural spectrogram. We have also added an additional auxiliary task inspired by self-supervised learning, in which the agent is expected to learn how to reconstruct the current step spectrogram. This task induces the network to learn a better latent space. In order to integrate effectively the previous mentioned complex scenarios in training to provide the agent with a highly diverse training experience, we have implemented a training pipeline which does the randomization in 2 levels, episode level and the step level. Starting with episode level randomization, the pipeline would decide whether to include a second sound as a goal location or not, and if it chooses to include it, then it will need to randomly select that different audio from the available training sounds. It has also to decide whether to include a distractor sound in the current episode or not. In the step-level randomization, the pipeline starts to take random decisions like whether to include a distractor sound in the current step or not, and if yes, the pipeline needs to randomly select a different audio to act as a distractor sound. Then, it has to randomly choose where to locate it inside the environment. The pipeline has also to decide if it's going to apply a future-wise augmentation or not, and if yes, it has to randomly select which type of augmentation it will use. It can select whether to use time masking, frequency masking, or a combination of both. Our second main contribution is introducing reconstruction of the current step spectrogram as an auxiliary task for the agent to learn, as it provides the agent with a dense self-supervised learning signal by improving the encoded latent space to make sure that it preserves the crucial spectrogram features. We have used the mean square error to calculate the auxiliary loss. Here we show how we have integrated our approach with the current state-of-the-art model audio-visual navigation waypoints by Shen et al. As you can see, our randomization pipeline passes the current binaural spectrogram to the audio map and the audio encoder, which we have added an audio decoder after it to reconstruct the current spectrogram. Finally, we compare it with the original one in order to calculate the auxiliary loss. We show our result on unheard sound datasets, first on the challenge dataset, second on the SoundSpace dataset. Our approach has outperformed the state-of-the-art and increased the success rate by 18% on the challenge dataset and 21% on the SoundSpace dataset. We have achieved also a better SPL by 13% on the challenge dataset and 11% on the SoundSpace dataset. To conclude, more complex navigation tasks with strong perturbations and additional audio signals improve the performance on unheard sounds at test time. Reconstructing the current spectrogram is a useful auxiliary task for audio-visual navigation. Our approach has outperformed the state-of-the-art by a large margin in all metrics. These are the references that we have used in our work. Finally, I would like to thank you for your attention, and I would like also to thank the SoundSpace organizing team for providing this challenge, and especially Shangshan Chen for his unstoppable support throughout the challenge process.
Hi everyone, my name is Mohit, and I'm one of the co-organizers of the ALFRED Challenge at the Embodied AI workshop. And I'm very excited to announce the winners of this challenge. We had 6 participants, and there's been some amazing progress on the leaderboard. And today we'll be showcasing 2 of the top submissions and their approaches. But before that, let me give you a quick overview of the ALFRED Challenge. The ALFRED dataset is set inside the AI2 Thor simulator, which involves rich object interactions inside 3D household environments. The dataset contains 25,000 human-annotated instructions to achieve various goals by interacting with rendered scenes. Each annotation contains both a high-level goal, like put the green bottle in the cabinet under the sink, as well as low-level step-by-step instructions, like carry the green bottle to the first sink on the left. Here's another example from the dataset. The tasks in ALFRED are an amalgamation of various challenges in embodied AI, like following navigation instructions inside partially observable indoor environments, or grounding rich referring expressions that sometimes require understanding spatial relationships. Most tasks take around 50 low-level steps to be achieved, so the long horizon nature of these tasks poses a particularly difficult challenge for agents. In addition, agents also have to generate a dense pixel-wise mask to indicate which object they want to interact with. Some of these interactions are also irreversible, so you can't unslice an apple or unclean a mug. Together with these challenges, ALFRED brings agents closer to the real-world difficulties of embodied interactions. For this challenge, an agent was evaluated based on its ability to follow language instructions in both seen and unseen rooms. The top scoring submissions were ranked according to the best success rate that was achieved in unseen rooms. With that, now let's get to the winners of the ALFRED Challenge 2021. In first place, we have Hierarchical Language Conditions Spatial Model by Waltz Blukas, Chris Paxton, Dieter Fox, Animesh Garg, and Yova Artsy. This submission achieved an unseen success rate of 16.3%. And here's Waltz explaining how it works.
We introduce a hierarchical approach for solving long horizon tasks specified with high-level natural language instructions. Our approach takes as input only the high-level instructions and RGB images, and it does not use the detailed step-by-step instructions in ALFRED. Our approach consists of an observation model, a high-level policy, and a low-level policy. At each time step, the observation model takes as input the RGB image and constructs a spatial world state representation in the form of a semantic 3D voxel map that's visualized here in the center. Each voxel in the semantic map represents a region in space and encodes the classes of objects contained within that voxel. The semantic map captures the agent's understanding of the physical world around it. The high-level policy then takes as input the semantic map and the natural language instruction and predicts the next high-level sub-goal. The low-level policy takes as input the semantic map and the high-level sub-goal and predicts the next action to be executed by the agent. The high-level policy is a neural network, and the low-level policy consists of a combination of learned and hand-coded skills. This is a visualization of our model solving the task, secure 2 disks in the bedroom safe, showing the input RGB image, the predicted depth and segmentation, and the semantic voxel map. The agent here is shown as a black pillar, and the object of the sub-goal is going to be shown in bright yellow. That's the object that the agent intends to interact with. Now the agent first starts by looking for the CD and successfully picking it up, and then it's roaming around and exploring the environment looking for the safe. It eventually finds the safe and successfully manages to open it, put in the CD and close the safe, and now it needs to look for the second CD. It has imagined that there's a CD here on the ground, which there isn't, and so the agent tries to approach that CD to pick it up, but it fails. Now it's still looking for that other CD, and it's made its way back to the safe thinking that there's a CD to be picked up there. It's trying a couple of times, but eventually it realizes that there is not a CD to be picked up, and so it keeps roaming around looking for the CD, and eventually finds the second CD on the table, and now it's bringing it to the safe. The agent tries to open the safe, but it's blocking the door, so the safe cannot open. So now the agent retries from a different position, opens the safe, puts in the CD, and completes the task.
Coming in at a close second place, we have The Agent with the Big Picture by Byung-hee Kim, Suvash Bambri, Kunal Pratap Singh, Rusba Motagi, and Jonghyun Choi. This submission achieved an unseen success rate of 15.4%. And here is Byung-hee explaining how it works.
Hi, I'm Byung-hee. We benchmark our model on ALFRED, and we focus on 2 aspects: the limited field of view of the agent and different semantics required for task completion. For the limited field of view, the agent takes the egocentric observation as input, but this view is relatively small. And this small field of view often limits the agent's understanding of an environment, and this could lead the agent to poor performance. So we use surrounding views by gathering additional observations from navigable directions to enlarge the field of view of the agent. As illustrated in the figure, the agent takes the surrounding views from the navigable directions, including the egocentric view, and our model jointly uses the multiple visual features. For the different semantics for the task completion, while action prediction requires global semantic cues, object localization needs a pixel-level understanding of the environment. Because they are semantically different, we factorize the action prediction and object localization in separate branches, and we call them policy and perception branch, respectively. For each branch, we combine individual components that address the bottlenecks of various aspects. In the perception branch, we encode the language instruction, ground vision and language features, and predict masks using our object-centered localization method. Instead of directly predicting the mask, our object-centered localization predicts the target class and retrieves the mask instances of that class from a pre-trained mask generator. And in the policy branch, we encode the language instructions, ground vision and language features, and predict the sequence of actions. In addition, we propose a mechanism in an action policy branch to avoid unanticipated obstruction during inference time.
Now, going back to the challenge, what are some key takeaways? It seems like end-to-end learning with egocentric vision, especially in interactive environments, is still pretty hard. Trying to learn everything from sequences of raw RGB observations does not generalize well, especially to unseen scenes. So we saw a lot of submissions that made use of some strong semantic priors. These priors were trained inside training scenes to predict things like segmentation, depth, and pose. We saw that the winning submission made use of all these three priors to make an agent that generalizes pretty well to unseen scenes. We also saw a number of submissions that made use of hierarchical and modular approaches. In hierarchical models, there was a high-level module that predicted what the agent should do, and there was a low-level module that figured out how to execute that high-level action. Similarly, in modular approaches, the action and the perception part were compartmentalized, and this seemed to make a huge difference. With that, I would like to thank all the participants who submitted their models to the challenge. And I would like to thank our sponsors, Amazon Science, and I look forward to seeing you at the workshop.
Hi there, I am Dr. David Hall, and I'm going to talk about the Robotic Vision Scene Understanding Challenge in association with this CVPR 21 workshop on embodied AI systems. The Robotic Vision Scene Understanding Challenge was supported by the Australian Centre for Robotic Vision and the QUT Centre for Robotics. Before I get going too much, I would like to acknowledge that I am but a small part of the team that made this thing possible, so I'd like to acknowledge all of the work from all of our team members, both past and present, for making the challenge what it is today. So, what is the Robotic Vision Scene Understanding Challenge, and what is it that we wanted participants to do? Well, we split our challenge up into two distinct tasks, a semantic slam task and a scene change detection task. For the semantic slam task, what we wanted people to do was to have an autonomous agent that is able to explore an environment and map out various objects of interest within that environment. So things like tables, chairs, books, etc. And to create a 3D cuboid map of that environment, such as the one that you see below. Participants are then evaluated based on how well their 3D cuboid map matches the ground truth map for that environment. The second task is very similar, and that scene change detection has to traverse the environment twice, however. Between these two traversals, there may be some lighting variations, such as you see here between daytime and nighttime, but more specifically, there are going to be some objects which have been removed, such as this chair here, and there will be some objects which have been added, such as this monitor that you see here. And the goal is to create a 3D cuboid map, like we saw before, but only of these changes. What objects were added, which objects were removed. And then you are evaluated based on how accurate your map is to the ground truth changes map. We provided several environments for this challenge, two of which were kept as development environments where the 3D ground truth object maps were provided, and three where the maps were withheld for challenge testing purposes. For each of the 5 base environments, we created 5 variations of said environments for both providing variety to the challenge and for the scene change detection challenge in specific. And of these 5 variations, there was always 2 that were nighttime versions of these environments. As it is a fairly challenging task, and we were hoping to bridge the gap between the computer vision and the robotic vision communities, we provide 3 different challenge difficulty levels that people could participate within. The simplest is a passive mode with ground truth pose information provided. Here, the task is simplified down to simply processing the data that is supplied by a robotic agent. It moves between a set of predefined nodes and is provided with ground truth information. All that is required is to be able to detect objects and to map objects out into the scene. At the second difficulty level, we have an active control of the movement, but still provide ground truth pose. So now the challenge is expanded as you need to autonomously explore, navigate, and avoid obstacles, but you are still provided with ground truth pose information, so you don't need to worry about the localization challenge. All control is done using a simple API of rotations and moving forwards and backwards. Now, the most difficult difficulty level is active with dead reckoning. Here we provide the robot instead with noisy odometry information instead of the ground truth pose that was given before. So now the task is expanded to also include localization as a task to be considered as part of the robotic system. Now, because we had these different challenge tasks and difficulty levels, we were able to split up our prize pool accordingly and rewarding more heavily the more challenging tasks. So starting from semantic slam with passive ground truth mode all the way to scene change detection with active dead reckoning. We provided monetary prizes that were sponsored by the Australian Centre for Robotic Vision, and we had GPU prizes available that were sponsored by NVIDIA. So thank you very much to both those organizations for sponsoring this challenge. The challenge itself was built upon the BenchBot framework, which is our way of providing a simple API for robot control. This framework enables sim-to-real transfer for participants who were confident enough in their ability and wanted to experiment on their approach after the challenge itself. And it is a framework which is adaptable for many challenges, not just scene understanding, though scene understanding is the first version of this framework being used. The underlying sim being utilized is the NVIDIA Isaac sim, specifically version 2019.2, if you are interested. And more information can be found on benchbot.org if you want to use it for your own research. So we submitted 3 different baselines to our challenge leaderboards, and these baselines were baselines created without any sort of novel research being done, just the cobbling together of various simple pre-existing algorithms that are available. We did 2 of them for semantic slam passive ground truth and 1 of them for semantic slam with active ground truth. So our first baseline for semantic slam passive ground truth was simply using the tutorial code that was available on the BenchBot website. This created a semantic map using VoteNet and some basic filtering, and achieved an object map quality, or OMQ score, of 0.11. Object map quality is an evaluation measure that we created specifically for this challenge that I'm not going to get into right now, but simply know that 0 is bad and 1 is good. Our second baseline was a bit more complicated and but still just combined some existing methods and made some simple assumptions to get a better score. So we fused the output from a high-performing object detection system and fused that with a depth segmentation algorithm that was available to create object databases. We merged any overlapping objects from within this database when creating our final map, and then we post-processed the cuboids, the final cuboids that we had in our object map. So making assumptions such as big objects like tables and chairs had to exist on the ground plane, and small objects would be restricted in size. So we're not going to have giant bananas within a room, for example. And this simple cobbling together of existing techniques managed to achieve an OMQ score of 0.44. As you can see here, the results weren't perfect, so ground truth bounding boxes are shown in red, and our outputs are shown in blue. And you can see that it misses some objects and hasn't got correct alignment, but it was a solid starting point for people to build upon. We also created an active control baseline where we simply used the same mapping algorithm as our passive ground truth, but we implemented a random walk algorithm that was used until the robot crashed into something. And once it crashed into something, we said, all right, you're done. Let's make the map. This simple random walk used a laser scan to divide possible regions of movement into 5 distinct locations, and we moved in the direction which had the maximum average distance available. So, for instance, if zone 2 had the highest average distance, it would move towards zone 2. And this achieved a reasonable OMQ score of 0.37, despite the fact that when we look at its trajectories, the control was definitely not optimal. And this is why the active control of the robot is such an exciting area of active research, because there is so much that could be done to help the system evolve further from this point. So, in terms of the actual challenge itself, we opened on February 17th and ran until May 31st. We had a fair bit of community engagement, both through our GitHub issues and our Slack workspace, which is where people were able to directly communicate with ourselves and other participants to talk about this and other ones of our robotic vision challenges. But sadly, on our final leaderboard, we only had one external submission to our Semantic Slam passive ground truth leaderboard. But big congratulations and thanks to the Edith Cowan University submission for showing the interest in the challenge. Whilst they were on the leaderboard, they sadly were not able to exceed our baseline submission. But we did find out from them that what they did was a variation of the VoteNet approach that was available from the Benchbot tutorial code. So big congratulations and thanks to that team for participating in the challenge. So conclusions on this challenge and the future directions for this challenge and research. Well, first of all, it's definitely a very challenging area of research with a lot of potential yet to be unlocked. Very excited to see what might happen in the active navigation and exploration fields of research. Our object detection to 3D object map is still obviously not perfect, as otherwise we'd be getting perfect passive ground truth mode results. And it will be interesting to see what happens in terms of detecting changes in scenes for scene change detection challenge, as we did not see any submissions in that leaderboard. It is very exciting to see all the tools that are now available to help enable rapid research in the area of embodied AI and challenges such as the Scene Understanding Challenge. So beyond just the Benchbot tool that we have made available for this and other challenges, there are so many things that are part of this workshop that are exciting to see, and that will be interesting to see where this field develops in the future. For our challenge in specific, though, we will also be providing a version of our evaluation website publicly available for long-term research, so that people can continue to work on and develop algorithms for this specific challenge. In terms of ourselves, we will continue trying to contribute to research in this area, and we hope to perform some research ourselves in solving these difficult challenges that we have put forward to the rest of the community. Thank you for listening to the talk. Thank you on behalf of the entire team. If you're interested in this challenge or in any of our other robotic vision challenges, please get in touch. If you want to be part of our community that talks about these sort of challenges, please talk to us on our Slack workspace. Thank you very much for your time, and bye-bye.
Hi everyone, this is Chuan Gan, a researcher at MIT and IBM. I'm very excited to share our team's effort on building a world simulator 3D world for embodied intelligence. The long-standing goal of research in AI is to engineer a machine agent that can interact with the world. Such AI systems must learn to perceive and understanding the physical world around them in order to be able to manipulate objects and formulate a plan to execute the task. Because direct training model with real robots is expensive and involves some safety risk, there has been a growing interest in using 3D simulator to build and benchmark embodied AI and robot learning models. Here I list a few representative 3D simulators, including iGibson, Habitat, iTutor, Virtual Home, as well as Sapien. We also joined this effort to building a general-purpose world simulator named as 3D World, or in short, the TDW. This platform actually was born as an internal tool 4 years ago, and the initial idea was, by generating scene in a virtual world, we could have complete control over data generation with full access to all associated generative parameters. This would enable us to train much powerful machine perception system. And since last year, we make a strong push to open source this platform and also switch its main focus from passive machine perception to embodied intelligence, robot learning, as well as cognitive-inspired AI. To begin with, I would like to give a brief introduction about TW. So TW is a multimodal platform for interactive physical simulation, building on the state-of-the-art game developer platform Unity. Unity handles image rendering and physical simulation for us and allows for a very diverse set of use cases. Here, I summarize 3 key aspects of TW compared to other simulators. First, it's highly flexible and generally designed. So TW was designed to accommodate a range of key applications in AI, including multimodal perception, physical scene understanding, robot learning, and with the goal that can enable training in each of these domains using a single simulator. Secondly, it supports multimodal simulation, which allows us to create a synthetic image dataset at near photorealistic level and generating sound at a high level of acoustic fidelity. And the most importantly is that TW has advanced physical simulation abilities. It allows rigid body objects, soft body objects, clothes, and fluids to interact with. So there are multiple ways that we can interact with objects and generate physical realistic behaviors using TW. Users can affect objects directly through API command or indirectly through embodied agent. Users can even interact correctly in VR, picking up virtual objects using virtual representation of their own hands. And this platform also opens us a new opportunity for us to redefine a new embodied AI task in both photo and physical realistic virtual environment. So in early this year, we released the TW Transport Challenge, a visual guided task motion planning benchmark for physics to advance the physical release embodied AI. And we are also very excited to host this challenges at the CVPR Embodied AI workshop. And the motivation behind this dataset and challenging is that we find most of the tasks defined in currently virtual environments mostly focus on visual navigation, but pay little and no attention to the physical interaction. Since the ending goal of embodied AI is to build a system that can perceive and interact in a physical environment, physical interaction is clearly a necessary component for training home assistant robots. And concurrent to our work, several well-known researchers from computer vision and robotic communities also propose using rearrangement of objects as a potential testbed for embodied AI. So our dataset provides an example rearrangement task and with a clear evaluation metric and task definition that can be used to test embodied agent task and motion planning abilities in a photo and a physical realistic environment. So in this new embodied AI challenges, a robot agent is required to take action to move and change the state of a large number of objects to complete a complex goal in a photo and physical realistic virtual environment. Concretely, an embodied agent is randomly put in a simulated physical home environment, and it must collect a small number of objects scattered around the house and transport them to a specific location. In this example, that they need to transport ball and drug to the bag. The objective of this task is to transport as many objects as possible, given a limit interaction budget. We also position several containers around the house that can be used as a tool to transport objects efficiently. So without using container as a tool, the agent can only transport up to 2 objects at one time. However, while the container can help agent transport objects more efficiently, it will also use up some of the valuable interaction budget to fund this kind of container. So therefore, the agent must reason about a case-by-case optimal plan. And we created a TW house dataset to support this challenge. As shown in this figure, its home environment contains around 6 to 8 rooms, and the example including bedroom, living room, and kitchen. And this room are then fully populated with furniture and objects that all respond to the physics. And in this challenging, we using microbot as the embodied agent. We also implement several high-level physics-driven action API to enable the robot to interact with objects. So the researcher can using commands such as go to grasp, put into container to train their robot to interact with the object and complete the task. And the observation space in the challenge contains a first-person view, RGB images, and a depth map, as well as the semantic segmentation mask. The agent could using this observation to estimate autopsy map, and it can also obtain the object list based on the semantic segmentation mask. And we believe this long horizon task in the physical realistic environment pose several unique challenges for embodied agents that go beyond the traditional semantic operation. So the new challenge including the synergy between navigation and interaction. So the agent cannot move to a graspable object if this object is not in the egocentric view, or if the direct path is obstructed, for example, is occluded by a table, in the example. A second, the physical aware interaction. So grasping might fail if the agent's arm cannot reach the object. And third is about physical aware navigation. Collision with obstacle might cause object to be dropped and significantly makes the transport inefficiently. And last and most importantly, we really care about the reasonability of robot, and we design some two use case and hope the robot can have some common sense to succeed in this task. Here, show example about how the data set look like. A robot agent is required to find a small number of objects that scatter around the house, pick them up, and transport them to a desired final location. And again, to complete the task, the robot agent must plan a sequence of options to change the state of many objects in face of this kind of released physical constraint. So we truly believe that this work simulator as well as benchmark will take a meaningful step that to empower research to develop a more human-like intelligent physics-driven robot for the physical world. And again, I would like to thank all the collaborators from MIT, IBM, Stanford, and please also check our project webpage for more detail and also the recent update.
section of our workshop. It's a QA panel with the 5 challenges in our workshop, which is AI2 Thor rearrangement, ALFRED, robotic vision scene understanding, SoundSpace, and TDW transport. We're really glad to have all the challenge organizers here. Just a disclaimer that even though we call these live panel interaction challenges, not necessarily all the challenges have the interaction component. We also touch upon multiple very interesting topics such as scene understanding and mapping, language understanding and grounding, and also audio simulation and audio visual navigation. So it's a very exciting. And let's get started by having each of the speakers give a very brief introduction about themselves and 2 or 3 sentences introducing their challenge. So why don't we start with AI2 Thor? Luca, you want to go ahead?
Great. Hi, everybody. I'm Luca Weiss. I'm a research scientist at the Allen Institute for Artificial Intelligence, or AI2. So the AI2 Thor rearrangement challenge, essentially you want an agent to take one scene configuration where a bunch of objects are in particular locations and reconfigure it so that it's in another configuration. So there's all sorts of challenges in terms of high-level planning, sort of understanding interaction and movement of objects, physics, all that good stuff.
All right, next we have Mohit.
Hi everyone, my name is Mohit. I'm a PhD student at the University of Washington, and I'm one of the co-organizers of the ALFRED Challenge. The ALFRED Challenge involves following language instructions inside an interactive environment, which is the AI2 Thor. And it involves basically a task like, clean all the mugs and put them on the table or something like that. And these are really long horizon tasks, so it takes like a long time for agents to figure them out. They're irreversible actions, so you can't unclean something or you can't unslice something. So there's a lot of interesting challenges in figuring out how to do things, especially in like unseen environments where you've never been before.
Great, David.
Hi, I'm Dr. David Hall. I'm a research fellow at the Queensland University of Technology and part of the QT Center for Robotics. And our challenge was the Robotic Vision Scene Understanding Challenge, where essentially a robotic agent had to be able to explore an environment and map out that environment in terms of objects of interest, tables, chairs, etc. And the secondary objective was to be able to then identify what objects had changed between multiple traversals of the same environment. Yeah.
Cool. Next we have Changnan.
So hello, my name is Chuang. I'm a research scientist at MIT and IBM Lab. So I'm a co-organizer of 3D World Transport Challenging. So a task that requires robot agent to move and change a large number of objects to fulfill a complex goal under a photorealistic and relative also physical realistic environment. Yeah.
Right, last we have SoundSpace.
Hello everyone, I'm Chan. So I'm a PhD student at UT Austin. I'm co-organizing this workshop with Una here. This is the first SoundSpaces challenge for audiovisual navigation, where an agent is tasked to find a sounding object in the environment. So this is motivated by real-life scenarios. For example, someone might calling for help, and the robot needs to find that person and give him help. Or like, for example, baby is crying and the robot needs to find the baby and attend to him. So this requires the robot to understand both the sight and sound in order to complete the task. Yeah.
Cool. And we also have Jonathan. Want to give a quick intro?
Oh yeah, sure. Hi, I'm Jonathan. I'm an assistant professor at CMU in Language Technologies, and I'm here to take credit for Mohit's work on ALFRED. All the smart stuff comes from him, and then I just put my name at the end.
Awesome. And also Onat.
I'm Onat. I'm a PhD student at the University of Illinois. I'm also interested in the general embodied space, and Changan and I worked on the SoundSpaces simulator and tasks. So I'm here to represent audiovisual navigation as well.
Great, awesome, cool. So I will kick off. I hope I didn't miss anyone. I'll keep up with the first question from Slack. It's kind of a spicy question, so it's good to be the first one. This question is about the action space during the task setup. It seems that a few of the challenges use these kind of magical discrete actions that can pick or place objects. So the question is, if we are using this kind of actuation mode, are we confident that when we are making progress on this benchmark, we are making actual progress for real tasks on real robots? And if not, then is there any improvement we should make for these for the current benchmark so that we're getting closer to that? Anyone want to first take that?
Yeah, I can take a shot. No one wants to go first with this one. No, it is a hard question because the discrete spaces are not the realistic setup for a robot system, but they are a useful, at least I find a useful tool for getting research started in very complex areas. So there's certain tasks where the main task itself is so high level that it's difficult to it's difficult to get that done, let alone all of the complexities of setting up a robot system to work in continuous space, etc. And so it's really a good tool for being able to start thinking about such problems. And I also think that there's advantages to be gotten from this, because it depends on how you're doing your solution. If you're doing a solution that will only work under the exact settings of the benchmark, then it's only going to be really good at that benchmark. But if you're developing tools that can be expanded upon and utilized, so if you're doing a 3D mapping thing, if you've got a good 3D mapping subsystem that can then be applied to a real world system, it's still a benefit. And at the end of the day, when it comes to benchmarks and challenges, you don't really want to set them in stone. They are there to exist until the research output has sort of been used up within that space, and then you create a new challenge, a new benchmark, and you keep trying to push research forward. So yeah, so at the moment they are a means to an end, not the final solution, I would say.
Yeah, and just to add to that, I mean, lots of roboticists are working on the interesting robotics problems, right? There are other problems that if we don't work at them now, we shouldn't do things sequentially. Like if we have to wait till actuation and manipulation is all perfectly solved, and by the time we're done with that in 30 years, we'll be nowhere near getting to any of the other problems we might find interesting. So it's definitely true, and I mean, AI through Thor is I think one of the leaders of maybe using higher level actions. I mean, I think that's because the types of problems that we're interested in really working on are the more high level planning ones, right? And I think it is we can sort of see both directions kind of coming towards each other. I mean, like AI2 Thor now has like Manipula-Thor, and so you have an arm that can move around and grab things. So I think they're approaching each other, and seems pretty clear to me that we're going to gain from having done both directions simultaneously.
Yeah, I also
okay. Go ahead.
Okay, so I also want to add a few words. I mean, on this part. I think the TW transport challenge, even though it received a lot of attention, but it's keep getting rejected by both CVPR and CV, and also the reviewer keep challenging that. I mean, how this kind of interactive action, why this is useful. So when we design the transport channel, actually we want to do a balance about physics. Doing a balance about the physics-aware interaction, and also the kind of high-level reasoning and planning. So I want to make a little bit clarification, because the high-level action space of TW transport, and it's a little bit different. So this I actually double confirmed with Lucas, I think last weekend, is that actually TW transport challenge is definitely using a real physics. We're using physics to drive the physical arm. That is we are trying to using a non-degree freedom of articulated arm, and trying to using inverse kinematic to draw. To establish a joint with object and to achieve that kind of grasping. And it's a little bit different from the AI2 Thor that is also very good at trying to using a magic and the effector that when we close enough trying to PR. So we definitely trying to thinking that make a balance in between that have some physics aware and also not ignore the most interesting of reasoning and hierarchical ability that this kind of real random challenge trying to pose to. And I definitely agree that if you want to do that kind of high-level planning, well, taking care of the low-level control is definitely a real-world problem. But this problem, but I would say that for them, you want to building a robot that really can do in the household. It might be another 5 or 10 years, but it doesn't mean that if you, at the first slide, you need to do all of this stuff and put them, and then to take care of the opportunity. Because there's always have some people will ask whether this will be transferred to real. But the fact is that if you now start doing any abstraction here, you will never start to thinking about transfer to the real, right? Because this is a really long-term problem that you need a platform and data set to start with, right? And you have some assumption and simplification and do that. And also, I want to also emphasize, even though we have such abstraction and simplify the problem, there's still, no algorithm and no model for them on the transport challenge. No model can achieve over 50% transport rate. So this problem is already hard enough, right? That so for current model to work on, and nothing that, to be honest, I think that can be for them the real arrangement that can be direct transfer to the real. I think it's really far away. But that doesn't mean that we cannot, doing some simple learning and thinking about what's the best for the high-level planning and integrate the perception and the planning that, and also the reasoning doing something, right, and make progress in the field. So this is my thinking. Sometimes we should not think about, okay, this one will not directly transfer rule, but there's a reasonable step that trying to thinking and also imagine that what is missing in the then someday we can make really progress on this one.
Yeah, just to add on to that, I feel like right now this action space is kind of like a necessary but not like a sufficient condition. So just because you can solve it on this doesn't mean it will work in the real robot. But the question is, can you just even solve it in this simulated setting, right? So like for the ALFRED challenge, the best model with like perfect manipulation, perfect navigation, actuation for navigation, achieves like 16%. So there's still like a lot of unsolved challenges just in terms of like grounding the language and also visual understanding. So before we actually put them on real robots, so there's still a lot of things for us to do.
Just one more thing
to add.
Oh, you go ahead.
Go ahead. Okay, I'll just quickly make the point. I can realize that this is a sensitive topic for many of us, but one thing which we should remember is the reusability of a module when you're deploying that. So there's options framework or hierarchical reinforcement learning policies or any of these abstractions which have hierarchical nature in it. The lowest module, which is a sensory motor control in this case, is reusable across tasks. So why should we keep resolving it in every task? If Changar and I want to work on multimodal sensing and going beyond language and vision to audio and vision, why should I resolve sensory motor control? I'll create the sub goal for the robot and then let roboticists take over. And this abstraction isn't something which I'm just cooking up. This is something which roboticists themselves have done, where they found that higher level policies always benefit from task description of what you want to solve, and the lower level policies benefit from how you want to solve it. And how you want to move your arm from A point to point B is agnostic to whether it's a task that SoundSpaces does or it's a task which rearrangement does. So I think that abstraction is very well justified, and we leave that to the roboticists to take care of, and we can focus on multimodal sensing, we can focus on long horizon tasks, we can focus on multi-agent tasks, and anything which builds on that module that can be reused again and again.
Yeah, and speaking as a roboticist, I was actually sort of bring up that kind of thing in that it's like for our challenge, we created a benchbot system which is designed to work in sim and in real. Just takes all the ROS stuff can happen in the background, and you could just plop this API on top to be able to go, yes, move forward by bar meters will be sorted for you, because we have the sensors and the basic navigation technology to be able to do that. So it's not like you couldn't apply it on a real robot. You just need to have the system in place that can interpret all those underlying lower level things for you. So yeah.
add a feedback loop on top, and then you have a better system. The two systems are talking to each other in a better manner.
Jonathan, you raised your hand.
Oh, just very briefly, since I think we've covered a lot of this, I think I just want to maybe play slightly devil's advocate in favor of the question and say that we are defining APIs effectively, and those APIs are not necessarily actually implementable. And so it is an important question, and it's a related part of that is what are the things that we therefore cannot capture. So what are the kinds of things that, for instance, I'm coming at this from the language side, so we're like the most abstract ridiculousness perhaps, but what are the kinds of concepts that if you don't have, for instance, a deformable object, and if you don't have interactions that encounter that, then that semantics is just not in your space. You cannot learn it. It is not present. And so we are making strong simplifying assumptions. I think people have argued why that's worth doing, but I think it's also just to sort of throw a bone to the original question in some sense, it's an important question to continue to ask every single time that we have these types of meetings, to make sure that we're staying honest and that we are actually making progress with these benchmarks towards something that eventually does close that gap instead of defining our own benchmarks. So that was all.
That's a very good way to wrap up this question. Thank you, Arthur. And I intentionally posed this relatively provoking question as the first one to start a discussion. Okay, then let's move on to another very important component of task setup, which is goal specification. It seems like different challenges specify goal differently. Some challenge use, for example, a sound source. Some challenge use, for example, an experience of a walkthrough of the environment. And some use language, for instance, and also the steps between. So the question is, why do you choose the goal specification that you have? What is the rationale behind them? And what do you think would be a goal specification, a good form of goal specification going forward for embodied AI tasks?
I feel like that really depends on the task, right? Like, for example, for audiovisual navigation, I mean, the task, like our motivation from the real life is like someone is either screaming for help or baby is crying. So in that case, the natural goal is like the sounding object itself. So that's why how we define this goal. And I imagine like for some other navigation tasks, for example, object navigation, the goal is just to find the object. So it's natural to define that object itself as a goal. So yeah, I feel like this is a very task-specific question, and there is not a general answer to this question.
Actually, it's an interesting question from the previous panel. Like when you're doing tasks as different as, for example, Chandra mentioned. Now you're doing an audiovisual navigation task. The source has to be audio, and it's not just the goal definition, but also the input. You're hearing and sensing a different modality altogether. You cannot have any other goal there. So we have it easy, but I think the question more generally could also be defined as intermediate sub-goals for navigation. That why do point goal, then object goal, room goal, and multiple goals? Why not come up with a common definition? And I think that might be interesting to answer for the panelists.
Yeah, so within the rearrangement challenge, I mean, so you basically have an initial goal or room configuration, so objects are in a certain position, and then another room configuration where the object's in a new position. And the idea is the agent has to run around the first room, and then when it gets put in the second room, it has to undo it, right? It has to basically move all the objects. So this is a bit of a weird way, if you think of it initially, to sort of specify where objects should be, right? Maybe I could instead give you a natural language description. The cup should be on the counter, the bread should be under the sink or something. Or you could imagine even giving with every object, bread and then coordinates, sort of like in a point goal-esque approach. And I think these are all sort of valid approaches for specifying the goal configuration. But sort of as it was brought up before, the goal, or how we specify the goal, is really tightly coupled to what we'd like to encourage the agent to learn, or what we require it to learn. And so we were very much interested in sort of having a two-phase setup where you really have to understand from images, like object locations. You're not given that, where you have to do long-term planning, where exploration is a component to whether or not you're able to actually complete the task. And so I think in the future, we will have rearrangement or variants of the rearrangement challenge where the specification is different, and what we learn and what the challenges are will be very different because of that specification. So I don't know if there's a final sort of gold or ideal specification for all challenges, but sort of as I think Una was sort of hinting or maybe said, I think it's important that these specifications are at least somewhat tied, or can be somewhat tied to what is actually actualizable in the real world, right? So, it's definitely possible to put an agent into a room twice. It might be less possible to give it a natural language instruction, and it seems very impossible to give it like world 3D coordinates of every object where you want it to be.
Yeah, I think there's also this other component, which is the nice thing about the spread of tasks here is that you actually want all of them. So I think that, they've all been chosen for specific research reasons, but if we were actually had a household robot that we were going to teach things to, there are certain things that are easy to convey in language, and there are certain things that are not easy to convey in language, right? So if I was teaching, the example I use from as an old data set is basically like if I was teaching someone to knead dough, like trying to explain that in language is really cumbersome. That's definitely something where I'd like to just demonstrate it, or I'd like to, maybe if I was, the room rearrangement, for example, if I was like trying to explain the kinds of core I wanted, and it's like, and doing that in language is this incredibly complicated and frustrating process, but just showing you what I meant is clearly easier. So for each of these things, these are all things that the single agent should be able to do. And so we're all just sort of trying, I think, to basically come at it from different angles, and then eventually we should have a single model that is basically agnostic to the type of input, to the type of goal specification. Sort of understand whether it's in language or whether it was by demonstration that we had something in mind, and these. So this is kind of a nice collection of those to start off with.
Yeah, to add on to that, I would say like for some sort of universal goal specification, you need some sort of universal task, which is kind of very hard to define for embodied AI, right? Adding on to like what Drew was saying in the previous panel, right? Like for the black hole thing, there was like one goal. They wanted to, like everybody, all the organizers had like one thing. They wanted to take a photo of a black hole, like, but for embodied AI, it's kind of hard to define like a single problem and like a single line to say that everybody wants to achieve this. And this is how you're going to achieve it. And then it might be easier to like specify a goal, but I doubt if we can sort of like pinpoint on exactly what we want to do.
I think it's also very easy to be wrong about what the right goals are, at least from a practical standpoint. So when I first heard about the point nav challenge, I must admit, I was like, this is dumb. Like it's way too easy, right? You have a GPS coordinate at every step. Like obviously you can just solve it, go to the direction of the GPS. It wasn't easy, got a lot of research behind it. I was totally wrong, I'll admit it. So sometimes the things that are not actualizable and easy and sort of strange can be super useful.
Can I ask a follow-up question to the panel? Right. Yeah. So one of the things that I've noticed about sort of tasks and goal specifications, so if you track the history of, object detection type problems, there's key point estimation, and then you start adding in affordances and depth from single image and other things like that, and you follow the parallel progress in the NLP literature of not just sentiment prediction or machine translation, but entailment and other such problems. Pretty quickly, what happens is that there tend to become, you go from single task benchmarks to multi-task benchmarks like Glue and other systems like that. And after a while, it becomes clear that, look, there are some similarities here, and we can create benchmarks where either we force you to just participate in a bunch of these tasks and we will not allow you to measure progress on a single task. Or the other route you take is that here is a common task where we think this is at the trunk of everything that's downstream, which is core to some sort of representation learning in that domain. And when progress gets made on this, everything downstream goes up. So what are thoughts by people on this panel on where are we heading? Are we heading towards, do you in your competitions imagine adding multiple tasks, or do you imagine that there'll be some natural convergence toward the trunk, if you will?
I mean, obviously language is the goal for all of us. No, I'm just kidding.
Yeah, I totally agree that the language is more like a human robot. You're trying to, I mean, if it's better for some, I mean, household robot that the human wants to specify the goal, and the language is it might be the most straightforward way. And I think there's a basically what we are trying to resolve is taking the language goal and then translate it to the robot language. A robot has their own goal that it would, I mean, to transfer this kind of like natural language and then using that one that and transfer to robotic goal that they are trying to learn and navigate or complete the task. Yeah.
Yeah, sorry, my language comment was actually just a joke, but I think that I think that it falls under, and this goes to the sort of the previous question that you were extending. It falls under sort of social context, I think, for me.
Yeah,
so,
but I'm not sure that we really need the natural language. I mean, couple this natural language understanding with embodied AI, or we can, build something in between. For example, like visual reasoning, that is some image clarity, trying to building some function program that pass the language to in the middle something that specify the goal that you can do using some semantic parser that couple the language understanding and the goal understanding. So this part, I'm not sure that you need to end-to-end learning language understanding and embodied strategy, or you have first understand language and pass them to yeah.
Yeah, sorry. That's so I'm gonna use a social understanding as sort of like an umbrella here, right? So like if a child didn't have strong language abilities, was trying to get their robot to do something, they would use a very different mechanism for demonstrating the goal, right? But the idea is that you would still want the robot to understand that the reason that they weren't using language or the reason that they were pointing or whatever else was because of their understanding of the world and what they thought was helpful. And so I think there's this kind of aspect of sort of modeling your interlocutor, modeling your collaborator, which is sort of theoretically present in all of these, but maybe not explicitly modeling in any of these. And so language is one way that you communicate that. It's sort of a social construct, but so are all the others, right? And you really want to, I think, even in these other cases, your move to is increasingly underspecified, right? So for example, if you were doing, I'm going to keep using rearrangement or something like this because it's an easy example, but like you may not actually complete the rearrangement, right? You could imagine basically being like, I put a couple of things that have some sort of pattern to them, and then I sort of stop and I'm like, you get it, right? You sort of want to move to that kind of context where it's sort of understanding what your intent is, similar, with each of these things, even if it's not actually completely specified. But I'm a biased party.
Dhruv, to clarify the question, so is it that are we going in the direction of having multiple tasks on which we all present our numbers on versus having like one main task which is sort of all encompassing? Okay, so I kind of hope it's not the latter, in the sense that I don't expect, I feel like there are a lot of interesting domains and it would be silly to try to sort of push them all together, right? Like I would like to have an embodied representation that would work for like a drone flight and a navigation robot and a robot that's cooking in the kitchen and whatnot. It seems like there is some sort of fundamental representation that encodes interesting things about the world and how they move and how they interact, that should be shared among all these. So I think the practical standpoint is going to be really hard to create a benchmark that would allow you to test across all of these. And it would be a sort of a paradigm shift to thinking about building sort of dynamic representations which work across multiple tasks and action spaces and whatnot. But that's sort of the direction that at least I would like to see it going, because I don't really see there being a singular task which encompasses everything.
Yeah, that makes sense. But I just want to draw an analogy here again to computer vision, like, disembodied computer vision or NLP, where when people publish the next version of MOCO or SimClear or whatever, the next representation learning paper, they are solving a representation learning problem, and then they demonstrate on a couple of like downstream problems like image classification with linear protocol or whatever. And we sort of even if a paper doesn't go all the way, we kind of buy that if you are reporting strong improvements on this protocol, that yes, object detection will follow, and yes, key point estimation will follow, and yes, other tasks will follow. And I'm wondering if will that exist for embodied AI, that if you show me language modeling works really well, then I buy that a bunch of other things will work well as well.
I think part of it is that we've got a situation at the moment where all our embodied tasks, as we mentioned before, are all task specific. I like the idea of there being there are some things that an embodied agent will just need to be able to do. Can it navigate around an environment? Can it safely go from point A to point B and things like that? But I find that one of the cool things about embodied AI is that there is such a task-specific focus, because there's all the subcomponents, right, to making an embodied AI system work. With our challenges, we try to distinctly break those down so that we went, okay, only care about this bit. Now add on this bit. Now add on this bit, to try and make things a bit easy for people, so they can start at a nice low-level way of looking at things. But the cool thing about embodied AI is that you can just have, it's like a robotics task. Everything is focused towards the task. So there'll be small components. You could even say that any increase in object detection performance is going to be good for some of these embodied AI tasks, because they need to understand what it is that around them before they can interact with them, et cetera, et cetera, et cetera. So I feel like they are core elements, but I don't think, I think trying to create a core task around some of them, or have a challenge that is specific around that is, I don't know, maybe not the right direction for embodied AI, I think, because I find that the task element is so very important.
I also wonder if we're at the right time for doing multitask things, because I haven't really seen, I could be wrong, but I haven't seen really one model that works on room to room, but also somehow works magically on ALFRED. And it seems like most of the solutions we have right now are kind of domain specific engineered things, which are specifically designed for solving the problems specific to that domain. And this could be one thing, could be none of these are kind of set up as an integrated challenge. Maybe if we do set it up, maybe people will solve them, right? If you come up with simulators, maybe people will solve these things together. But part of me also wonders, are we kind of ready for doing all these kind of multitask things?
Which brings us.
What about I'm sorry. Go ahead. Are you moving to a different question?
Yes, but you can. But please wrap up if you want.
I was wondering, I was thinking of actionable, having worked at different groups in this space. I was wondering if can RoboThor or Thor release a task dependent waypoint generation, and then something which they used for object nav or point nav reused as the low level trunk task, as if I may reuse that terminology. I understand this can't happen, as Mohit pointed out, this can't probably happen at this stage for across data sets, and that's something which the last panel also discussed about. But can Habitat, for example, when they're defining a complex task, reuse their object nav module and release two numbers where you have to use this frozen weights, and you can tune whatever task dependent waypoint generation you are working on, but using this module as a waypoint navigator. And there's a lot of work, even Changan has some work on waypoint generation, and waypoint is a task agnostic way of representing subgoals. And I was wondering if I'm responding a question with a question that would different stakeholders here for Thor or for TTW or for Habitat, will they be happy to reuse their own tasks from the previous panel as sub modules to their own, because they don't seem to right now. Or we can leave it at the question stage and not answer it.
I think that's a fair question, and I think there is some effort already with. I know Eric Wyman's released his point nav model from the DD paper, which is a good starting point if all you want to do is semantic free navigation for reusing the perception module. We have the individual episodes out both on point nav and object nav, but it's a good question that we could just create point nav episodes from the object nav episodes. So it's a good suggestion. I can take that up with Alexander.
Great. Then there's a lot of food for thoughts on that front. We will switch gears slightly to the topic of generalization. I think we talk about generalization to novel tasks are definitely extremely challenging, and we're not there yet. But we do see different challenges or adopting ways to measure generalization to novel objects, novel scenes, and also novel sound, right? In each of your challenges. So if you don't mind, could you share some of your insights there? Like when do you see there's a huge gap between training and test set, and how do participants or your baselines address these gaps?
So, okay, so in the rearrangement challenge, it's a very hard challenge, right? So we only have a certain number of scenes, and there's a sort of a lot to do. So for our baselines, the only way we really found that was proficient to train them, especially in the two-phase variant of the task, was to use some sort of imitation learning. And imitation learning, especially on these limited number of scenes, massively overfits. So we've tried little things to improve generalization, but I think this is still a huge area in which there is such a big gap between really high performance in train versus really low performance in test that, yeah, I suspect the next progress on the leaderboard will be some sort of domain randomization, augmentation type stuff that just blows everything else out the water.
For ALFRED, there's a huge gap between performance in seen rooms and in unseen rooms. So the best success rate in seen rooms is like something like 44%. But for unseen rooms, it's like 16%. And the challenge, which basically the submission that won the challenge, basically trained a lot of priors. So things like depth estimation, segmentation masks, and also like pose estimation. So they essentially did kind of like a lot of like strong semantic priors for the agent. So it can sort of like figure out what to do in like completely unseen environments. It seems like throwing these agents in with just like RGB input and trying to learn everything just through raw sequences of RGB sequences, especially if your tasks are like super long horizon, is still pretty difficult. Although, I mean, it could change in a few days or a few months, who knows, but at the moment, it still seems very hard to just do everything end to end.
Yeah, from our challenges perspective, we made sure that the objects that were trying to be detected in our scenes were ones that were from existing, computer vision data sets, so COCO, just to make things simpler, so we didn't, have to worry too much about the complete transferability. But at the same time, it was interesting because when we can only really speak about our baselines at this point, but when we did our baselines, all we did was that for the two environment sets that we had for development, we just looked at those and kept on trying to improve the score on that by going, okay, what's a simple assumption we can make? Chairs are on the ground, tables are on the ground, etc. And finding small little bits of information like that did transfer well between scenes, despite the fact that the scenes were very different looking between the development set and the testing set. So yeah.
So for SoundSpaces challenge, so we test the agent on both unseen environments and unheard sounds. And we found that like the generalization from heard sound to unheard sound is pretty bad. Like the performance on unheard sound can be like 40%, no 40%, 0.4 SPL, and then the performance on unheard sound can be like 0.3 SPL. So it's pretty bad to generalize from like heard sound to unheard sound. And some of the participating teams have like tried to use pretty much like data augmentation techniques to improve the generalization. For example, by either inserting unheard, like some distractor sounds in the environment to prevent from like overfitting to the sounds in the training set, or use some kind of adversarial training to help the model to generalize better to unheard sounds.
In the TW transfer challenging, when we designing the challenge, it's more like a task motion planning benchmark, and we don't find any evidence that it's purely reinforcement learning, hardware reinforcement learning can do even well in this training environment. So that's why we propose some hierarchical combining, it's mapping and planning, and as well as it's also so we also using a little bit learning to train baseline. Like it's more like a neural slam based approach. You try using learning that to find some waypoint and set as a sub goal and to doing separation. We found that in the training side, it definitely can be better than a random operation, but we don't find clear benefit when it transfer to the testing task compared with the frontier operation. That basically you build a map and randomly choose a point as a set goal. We don't find a clear advantage in the testing side. So so my point of view that maybe that use some data augmentation, more training step, and also my environment for pre-training, it might helpful to improve the generation of the learning-based approach. But for at least for the the theta transfer is challenging. That it kind of requirability of reasoning and high-level planning, and we don't find evidence that the purely learning approach that is can do well even in the training environment. Yeah.
Cool, awesome. Thanks for the discussion. That's very enlightening. And we moving on from generalization, I want to ask a question on Slack that is more towards getting solutions to these problems. So the question is, mapping has been an extremely powerful tool in obtaining high sample efficiency performance in navigation tasks. What similar inductive biases do we need for interactive tasks? Is 3D semantic mapping enough? If not, what else?
So I think at least the downside that I see with many semantic mapping systems, even in 3D, is that they are not very robust to changes in the environment, right? So I think this is a big push that's hopefully happening in that domain. So for rearrangement, for instance, we had some semantic mapping in 2D, and for the models that we were looking at, all of them sort of make the assumption that if you see an object and you say it's there, you're going to say it's there forever, right? That's never disappearing from the map. And of course, this is pretty bad in rearrangement where you pick up objects and you need to move them around. So I guess I would like to see some sort of semantic map, but that is somehow enriched with an understanding of sort of physical properties and understanding of at least like the sort of Newtonian physics, right? Things fall, but eventually we're going to have to be pushing into the direction of understanding that objects can be sliced and burnt and all this. So I think those are the types of object-centric physical biases that or inductive biases that I'd like to see. I don't know if these would extend to other tasks as well.
As we move from navigation to interaction, I think knowing what comes beside what becomes more important. So going back to our long-lasting goal of getting a robot, making our robot to get coffee, or make any changes to coffee, it needs to know that a coffee is supposed to be fetched in the kitchen, or a coffee room, or next to the sugar should be kept next to something else. So there are implicit, when you talk about inductive biases or inductive priors in general, using this sense of this knowledge, common sense knowledge, as some people call it, or any sort of world model of what comes beside what, or what happens if I pour sugar. Would it sprinkle or would it pour down? Those are information which, and as the agent starts interacting with these objects as opposed to just statically navigating in it, they would need to know what to expect when something goes wrong. And I think this sense of common knowledge, which lots of groups are working on, and representing them as graph structures and learning priors on top of it, would be helpful when we move from the scope of navigation to interaction, I guess.
Yeah, I want to echo that. I think that basically one of the things that's important is that we're talking about interaction as if it's a general concept, but we're all actually working in constructed worlds. So these are not interacting robots that are under the sea or something like this. So the space of physics and the space of sort of interactions is actually very limited, and not just is it limited, it's limited to be exactly what humans would do. So we're working in these socially constructed environments, cabinets are at certain heights, tables are certain places, all this other kind of stuff. And so the notion that we would come into this tabula rasa, which is I think what most of us tend to assume, is somewhat strange, right? Because even a human in some sense doesn't actually come into something tabula rasa, right? So, and I don't mean in the sense of like evolutionary priors, I mean in the sense of like where your arm is just physically located on your body. If you were going to push a door with your arm, you're probably not going to go poke it in the bottom corner. It would be very strange for you to do that. You're going to probably just run at it. And we live in a constructed world, and so therefore that's going to work. And so I think that this notion, so just building on what I was basically saying, like I think that like having this understanding built in to these systems is actually going to potentially be really beneficial, and in terms of search spaces, in terms of priors on objects, in terms of things like this, because we're not solving a general robotics problem. We're solving a robot in a human constructed, human constrained environment task. And so we should, try to see how we can do that without sitting down and writing a bunch of rules. That's not what I'm proposing, but something in that's sort of guided, at least in that way, that's sort of aware of those constraints.
Something tangent to that also, I would say, I think something that's universal across all interactive agents is having some sort of action-oriented representations rather than like object-oriented representations. So it's not just that this is an object, it's mostly about like what can you do with the object and like how does the state change affect the object. So it's things like reasoning about like affordances, like what can you do with that object, and not just like detecting the object. I think that is also something that is common across all interactive tasks.
I guess also one thing. Oh, sorry, go on.
Yeah. Oh, sorry. So yeah, I also think that I mean, currently most people talk about the semantic 3D perception. I think another perspective is about is really about the physical thing understanding. I mean, for example, in the transport challenge, actually, when we design the challenging that we're trying to building, the house environment that all the object is respond to the physics, and also when you design a dense house, that's something. Some ISO is very narrow, and actually, it's a little bit amazing that I found that when we training a navigation robot agent. And we didn't find a good algorithm that for them there's ISO is a little bit narrow, and to determine whether the physical robot can pass it or ISO or not. It really depends. I mean, this is really complicated task. For example, some objects is movable, is very light, and to mass nothing. I mean, a robot can go into it, and maybe another object will be collect other. But for something maybe very heavy, and the robot will just start here, and it's also hard to go out. So this is when we design the train, we haven't think about the problem, but when we do that kind of physical aware how to design and using that kind of physical driven high level action, that so we find that actually instead of semantic understanding, physical understanding is really important, and it's a little work that. Even some recent neuroscience are thinking about, what we can do in this kind of space.
So one thing that also seems important as we move to more sort of social interaction and whatnot, yeah. I don't think we'll ever have an agent that will learn tabula rasa about sort of theory of mind or like human emotional states or anything like this, right? It seems really important to have those types of inductive biases so that we have human robots rather than robots.
Adding to the semantic part of this this bit, I think so. One of the improvements we are planning to add to the SoundSpaces challenge in the future is to have like visual embodiments of the sound. So currently, like the sound doesn't have any visual embodiment. Like there's no telephone associated with the telephone ringing sound. So we are thinking of like having the objects related to the sound. For example, if you hear the flushing, it must come. Like for example, if you hear the toilet flushing sound, it should come from the toilet. So that kind of association or inductive bias should be really important for the object, for the agent to navigate to the correct object and finding like the target.
Right, that's something which we can incorporate on the dataset creation side, as opposed to just like, for example, what I mentioned was something which the agent should know about, while this is something which we can do when we're creating these datasets, that they are socially grounded in some sense. Another thing which comes to mind is like a friend's work on learning affordances when you're dealing with interaction. That there is a schoolwork from Tushar on like AI to Thor where they learn affordances on the objects, and it makes a lot of sense. If you're starting to grasp things and move things around, you need to know what you can hold on to and what you can grasp and so on. So there are different low-level actions that become important, and knowing that is a good prior or inductive bias to have when going into the wild, west.
Awesome, thank you. Moving on from solutions to evaluation, I think there's a question asked on Slack and also on YouTube actually. So he's asking about typically, programmers spend a lot of time setting up environments, running other people's code, and replicating results. Can we set up a norm that we can share Docker images so that we can always do apples to apple comparison? What do people think?
Yes.
Great.
Yeah, I mean, I really love the idea. I think the reason, or at least in part of the reason that this doesn't happen, are generally like practical considerations, right? So AI2 Thor doesn't run well in a Docker container. It's just, it requires you have an X display set up. Hopefully that'll change soon, but as it currently works, it's a huge pain. And then I know we tried to set up a Docker container for Habitat. And I mean, so one of the big problems or the pains of starting up Habitat, I think, is downloading the data, right? You have to get permission, you have to do it. And if you create a Docker container, you can't include the data set in that because it's not like, it's legally not allowed. So I think those are some of the reasons. I mean, we could definitely do it much better as a community, making code more reproducible. I think there are steps when things are impractical, you can at least maybe have like a Conda environment that will set up nice and easily. And we could, yeah. So I would like to see this more. There are some practical considerations, but yeah.
Yeah, and it's also slightly hardware dependent as well, because like we had all sorts of issues when it came to the GPU side of Docker when trying to set up the benchbot environments and everything. So one of my coworkers who did most of the benchbot stuff was saying that the Docker, the Docker it will just work is a lie, and you need to do a lot of jiggery pokery to actually get that to work. So love the theory. Would be interested to see if we can overcome the engineering difficulties to get that to happen.
Yeah, actually, CVPR transport challenge that we spent a lot of engineering effort, and you definitely already put in a Docker container that people can feel free to use that one. Yeah.
Great, awesome. With last bit of time, I would love to wrap up with like a blue sky question. There's this blue sky submissions from Coral for the terms. So if you really have a lot of engineering resources and that can upgrade your simulator, what kind of features do you want to add to your simulator, and also what kind of dream tasks you want to tackle that might be unlocked by these new features that could really push the field forward, for instance?
I'll go first. I want human backprop in the sense that I want to, when I have an iteration, and this is just like a thought experiment, but we always, like, I think I've been in so many project meetings where someone has said, I want to backprop through humans. And if I have like the blue skies, I want to backprop through humans. I want to like take this checkpoint and deploy it in the real world, get infinite feedback or like good feedback, and modulate my learning better. So the entire field of embodied AI is a hack in trying to simulate that and not have to backprop to humans or through real reports, I guess. Maybe I set the tone too fantastical sort of.
No, I'll take your lead and run with it. I think that, yeah, there's sort of two ways to interpret it, and it's a question of how blue sky we're getting. I think that when if I think on something that's sort of in the middle there, it's somewhat similar, which is sort of an AR kind of situation. So I think that there is this kind of frustrating thing, which this goes back to, I think, that basically the first question about APIs, is that we have a different API for our agents than any human would ever have, or any robot for that matter would ever have. And so that disconnect is frustrating. And so that means that if you wanted to basically have a human step in and correct something, if you wanted to collect, runs inference where you actually had a human in the loop or whatever it might be. There really isn't a way to do that right now. And that's not just, partially that's an engineering thing, which is, we need AR sort of compatibility or whatever it might be or something to this effect. And part of it is also just that tech is not pervasive, right? It's not like we all have HoloLenses at home or something like this that we can just plug into. So there's a few pieces there, but I think that's kind of the baby step, which I think is very similar in spirit, which is that we want to get a human in the loop somehow. And then once we do that, then there's a whole bunch of other stuff we'd like to close the gap on, right? But that's I think that first step is being able to at least run inference with humans in the loop.
And maybe in an active setup, in the sense that if it would be awesome to have a robot or like an agent be stuck at some point. Let's do everything in simulation where the robot is stuck at some point and needs feedback as to what would be the optimal step here in an active learning setup. And that's when a human who's like sitting online and playing video games is like, okay, maybe I'll teach this dumb robot how to do things. And if I have good resources, I would have an online learning AWS Turk, the Turk Turkers running at all times, where whenever my agents are stuck and they ask for help, some human steps in and like, okay, I'll teach you how to do.
And even just confirmation, right? I think So any language is almost never unidirectional, right? And so, from my perspective here, similarly, like it doesn't make sense at a certain point to be learning that way. You always are learning with confirmations and corrections and so forth. So yeah, but I totally agree.
I love the idea of some sort of active feedback, but I also just, in terms of ad challenge at the very least, would love more just variety of environments of robot setups, so you're not having to go, okay, it always has to work on this robot that is exactly at this height, which will always see things at this perspective. Want to be able to give people a variety of things. Want to be able to have the lighting change over time, so that you're not looking at the same scene in a static lighting environment, so that if a cloud comes over the sun, then suddenly your lighting is slightly different. You just need to be able to cope with that. Anything that just brings the system closer to what the reality of what a messy world we live in would be just great.
I would love to see sort of full, rich, super fast local physics that is, it allows you to simulate at more than, like tens of frames per second per object. I mean, I think there are just so many problems which become so much more difficult because because physics is so hard and so slow. So if, even rearrangement is part of this, that, it doesn't get the 1,000 FPS that we get for like point nav or object nav. And it just makes it harder to run experiments parallelly. It just makes everything harder. So I think having that kind of really well engineered physics system that cares about the things that we actually care about would be super valuable, and then enable sort of projects across the board.
Yeah, sorry,
go ahead.
Yeah, for me, like every year, I like one of my favorite things to do is go through the SIGGRAPH videos of the latest simulations every year, and they have like some amazing thing every year, like cutting bread or like folding cloth and pouring like non-Newtonian liquids and everything like that. If you could somehow get them into our simulators with a full house, I think that would be kind of cool. But it would probably take like 5 days to render one frame or something like that.
I think, I agree with that. I think like for SoundSpaces, one of the bottleneck is on the acoustic simulation, especially how to simulate the materials of different objects, of the seating of the walls correctly, so that you can hear the sound very, very realistically. And that's have been proven very hard. Like you cannot sample the material very correctly into a simulation, and also like model different bandwidth correctly. I mean, there is a trade-off. Like either you can model them at low resolution with ray tracing based solution, and then or like higher resolution with waveform based solution, but very low FPS. So I think like an ideal acoustic simulation we would love to have is like high FPS and very realistic acoustically.
Cool, awesome. With that being said, we were almost towards the end of the session, so I would love to ask each of the panelists just to say one or two things that are the key takeaways you want the audience to leave with. We'll do the reverse order, so yeah, it will be Chang'an from SoundSpaces.
Yeah, I think the biggest takeaway for me, like from the challenge itself, is like in order to generalize to more like more unheard sounds or more novel sounds, the agent needs to like deal with more challenging scenarios. For example, there is a distractor present in the environment, or like there is an attacker in the environment, which makes the generalization much easier.
Great, Chuang from TW.
Sure. I think that the takeaway that I feel that the bottleneck of currently embodied AI that other people actually detect is really about the static simulation, either the speed and accuracy trade-off, and also the ability to transport to transfer the cool technique from the, for example, the simulation and the coffee community to that kind of embodied AI environment. I think this will, if something that, the technique happen that we can working on more really exciting. For example, many people talk about soul body manipulation and also for the sound that for them can do the physical object localization that this kind of cool thing. Yeah.
Great, David.
Yeah, so from our challenge in specific, I'd say that the exploration aspect of an autonomous agent to be able to find the various objects within the scene and fully map it out semantically, that is a really unsolved problem that I think would be very interesting with some great areas of research. For embodied AI in general, I'd say that we are still like at the early stages. I really look forward to seeing how things develop as we get more continuous spaces and make things closer to reality. And that we'll always need to make sure, as we said at the beginning, that we are keeping in mind that sim to real transfer at the very end of the day, which will be interesting to see how things progress there.
Awesome. Mohit? Oh, you're muted.
ALFRED, I would say generally for generalizing to unseen environments, you still need a lot of semantic priors. So you need things like instance segmentation and depth estimation and pose estimation. And it seems like doing everything end to end, which is RGB sequences, is still pretty hard.
Last but not the least, Luca.
I'm gonna take a really high level view. So my two takeaways are interaction, it's incredibly hard, but it's what everybody should be working on. And we need to build sort of dynamic representations that allow agents to sort of generalize beyond different tasks and beyond action spaces.
All right. So with that, we have concluded the last section of our second Embodied AI workshop at CVPR 2021. I would love to say a big thank you for all the speakers that take time out of their busy schedule to prepare the talk and also have an amazing Q&A panel in the morning. We also want to thank you for all the challenge organizers here and also in the previous panel who had done all the heavy lifting to prepare the simulator, set up the tasks, run the evaluation, set up Docker, etc., etc. We also want to thank the paper authors who submitted their papers and also present them nicely in our poster session. We really hope that you had a lot of fun. And finally, thanks for all the audience for tuning in into our live stream since very early in the morning and also ask a bunch of amazing questions on our Slack channel. That would be it. We look forward to seeing you again next year, CVPR.
And I just want to say, Anthony, Chengshu, German, Joanne, Luca, and Eric, thank you for organizing this workshop. You folks led the proposal effort to coordination with challenge organizers to putting together this event. Thank you. This is really nicely done.
Thank you.
Thank you.
Seconded. Thank you.
Thank you.
Yeah. So hope to see you physically next year.
Yeah.
See y'all next year.
See you.
Bye.
Bye.